All right, should we start? Great. A minute early? Oh no, we'll wait then, because people are watching from all over the world, so I don't want to disrupt the schedule too much. All right, so we're going to stick with the schedule. 14 minutes of talks, and then is it 1 minute warning or something? Okay. But I'll give you 5 minute, 1 minute warnings. All right. Good morning, everyone. We're excited to kick off the third day of WAFR 2022, and we couldn't ask for a better speaker than Dylan Schell from Texas A&M. Dylan, take it away.
Thank you, Ken. Am I being picked up on the microphone, right? Yeah. Great. Thank you. So I'm going to talk about non-determinism in combinatorial filters. The primary object of study in this paper is a concept of a filter, which is an object, it's an abstraction for a computational process that consumes a sequence of observations and produces an output for each sequence of observations. Those outputs can be sufficient statistics or statistical summaries, or we're going to look at cases when the outputs from the sequence of observations are actions. And we're interested in processes that are stateful. So as observations arrive, they incrementally switch state and you get a new output. So to make this sort of more concrete for why we care about this in a robotic setting, we would like to reduce the number of states. So this is why it's talk about minimization. But to make this concrete, suppose you've got this little robot, it lives in this environment, you're trying to get to a goal region G, and it has a bump sensor and a couple of these navigation actions. So this 5-state filter is an encoding of a policy which says, wander along until you bump into something, then take a turn right, then carry on, turn left till you reach the goal and terminate. So this is a filter because you've got edges labeled with observations, and then you've got vertices which are labeled with outputs, which in this case happen to be actions. So in this talk, we're interested in operations we can perform on these particular filters. We're not that concerned about where the filters come from. So if you have a more complicated setting and you have a fancier algorithm that's going to search in policy space, what we care about it is at the end, you get this sort of 3-state filter, which has observations on the edges and outputs on the vertices. And we ask questions about how we can make manipulations. So specifically, we would like to minimize the number of states involved in these particular filters. So if you look at this, or when I look at this, the first thing I think about is an automaton. And the idea of classical automata reduction is of something we all learn in our undergraduate CS theory classes. And there's a problem of taking a deterministic automata, minimizing it. And the idea is that you would like to find a smaller automaton which is equivalent in the sense that it has the same language. And the Meyer-Hill-Nerode equivalences tell us kind of how to do that. So we'd like to do the same thing for filters. So take a deterministic filter and reduce that, squeeze it down, compress it to the smallest one. But the notion of equivalence is going to be slightly different here. So we're going to talk about the idea of output simulation. The concept that we would like is a notion of functional replacement. So suppose I have a filter. Well, so here's our definition of output simulation. So there's 2 filters. I'll say a filter G output simulates a filter F. If G can take any input that F can take and produces an output that matches F's. So more sort of visually, think of a filter as a map from a function from sequences of observations to outputs here. Well, something that output simulates this would be something that realizes the same functional map. But it only has to realize the same functional map on the set of inputs, so you're actually free to provide me a filter that can take more inputs if you like. That's perfectly fine. We're not going to get those strings in the environment, so that's not a problem. Turns out this little difference here gives us a different hardness category for the minimization of filters as opposed to automata. That's kind of interesting. The second thing in the case of deterministic automata is that we can compress them to a deterministic automata as an output, but we can also consider the question of what if you try to give me a non-deterministic automata? And there are good reasons to study this because there are examples of non-deterministic automata which are much smaller than their smallest equivalent deterministic automata. So here we have one which is 16 states, and the non-deterministic one here only has 5. And you can see it's non-deterministic because if you start with a B, trace a B from that first state, you've got 2 choices, and you have to make a choice for that. But these 2 have the same language. And so there's sort of, if you really care about minimizing, it seems like non-determinism is a good thing. It's an opportunity to minimize further. And you can see there's a big, big difference in number of vertices. So does this make sense for filters? Is there a notion of a non-deterministic filter? Well, it's quite natural, actually. If you go to this particular scenario and you imagine that there was another goal region, now maybe you can update your feedback policy so that when you get to that first T-junction, you can decide to go left or right. So I can encode that by just putting another output on that particular vertex. Maybe that's vertex multi-outputting form is a little strange, but you can think of that as also just splitting the incoming edges, and we're having traditional tracing non-determinism. So it seems like the idea of non-determinism is a thing which could make sense for filters. We have to just make sure we know what we mean by this equivalence of output simulation. So same situation as before, but now with multi-outputs, we can have some input which can map to more than one output, right? So we saw orange and green. So we're going to do as before, which is we allow something which output simulates to be more generous in its input set, but also we're going to allow it to choose one of the outputs or some of the outputs which are consistent with the ones which are given in the input filter. So it can choose either, it could choose both. So to update the definition, all I've got to do is to say it has to match, it should produce an output which matches one of F's. So you're free to use this, and this is an extra degree of freedom which your compression algorithm could try to use to do some minimization. So the first thing one might look at is to take an example of a case where there was a gap between a non-deterministic automaton and turn that into the filter case. And this is the case we just looked at, and I've just colored it. And again, we have the 16 state and the 5 states. But it turns out if you try to compress the 16-state filter, you get a much smaller deterministic filter. Because there's yellow everywhere, and you're allowed to pick one output, so you just pick yellow everywhere and you're done. And so one of the questions is, okay, does non-determinism in filters for minimization actually buy you anything? And the answer is yes, but you need different examples from the automata example. So here's a very simple 3-layer tree. It's deterministic, tracing deterministic, but it has multiple colors. And you can minimize this to get a deterministic minimizer. That's the smallest one, 14. But if you allow non-determinism, you can exploit that non-determinism to get something which is a little smaller, 13. So actually you get something from this non-determinism in the case of filter minimization. So again, the non-deterministic filter is smaller than the deterministic one. Okay, but hang on, not so fast. So let's go back to this tree example. So I'm going to add a couple of extra vertices here. And that's going to be our sort of our deterministic input. Now, when I make the non-deterministic minimizer, this is what I get. It's just as before, but now I've got the C and the orange and the blue here. And let's trace a string. So let's trace a string AC. So if I trace the string in the top filter, I get blue, and then I get violet or teal are the valid outputs. And the bottom one indeed output simulates that. If I trace A, first of all, I've got a choice on the A. If I decide to go left, I get produce blue, and then I produce teal. If I choose to go right, I produce blue or I produce violet. So that's all good. This indeed output simulates. But now what happens if I trace ACC? If I happened in the non-deterministic filter to have gone right, I've got an issue because that's going to crash, right? So in standard automata theory, you just say, okay, well, rewind and try again, right? To make a different choice. But these are actions, right? So causally, you've just done something in the world from your policy. You can't rewind that because there's potentially a side effect in the world. And you could say, well, maybe you can repair that. Just give me an edge labeled with a C that will get me orange, and so I can proceed. But if you do that, you'll notice that I can save ACC, but then I'm going to break BCC because that needs to go to blue, and there's no choice that I can put there for that. If I put that edge in, I'm going to violate output simulation. So this motivates the central definition in our paper, which is the idea of a type of non-determinism where the output choices are not going to matter. So we call that a string single outputting filter. So a filter is string single outputting. If it doesn't matter which way you trace them, however you trace them, you always end up with the same output colors. So in this case, if the string was going to crash, you could roll back, but you could roll back without having to do anything in the world because the outputs you gave were consistent with those. Sorry, should be string single outputting. Yes, thank you. String SSO. And what's interesting is that you can interpret this both in terms of backtracking or in terms of superposition. So you could trace multiple vertices as you proceed downwards. So this is what we call when we say non-determinism subject to output commitment. And it's clear that all deterministic filters are string single output filters. But you can also construct non-deterministic filters that are not string single outputting. So there's the subset relation. And so it's a sort of weak form of non-determinism. So we get back to this picture, and now I say there's a new class of non-determinism. I can put this in the picture, and I can ask, well, is this weak form of non-determinism actually useful? And this is the question that we answer in this paper. And the answer is yes. In fact, I can give you an example. One of the first results in the paper is here's a filter, which if you minimize it to get a deterministic output, you get 23 states. If you minimize it to get a non-deterministic output, you get 21 states. And if you allow SSO non-determinism, you get something strictly in between. So the next question we ask that we turn to is we say, well, okay, so this is a class which is potentially interesting if you want to do minimization subject to the fact that you're going to use this filter as a plan. What's the hardness of doing this compression? So the green results are kind of prior known results, but the main theorems in the paper are these two p-space completeness results for filter minimization from a deterministic filter to an SSO output or deterministic filter to a non-deterministic filter. So I'll just briefly talk about how that's achieved. So I'm going to just abbreviate them as DF to SSO or DF to NDF. So in order to prove that both of these are p-space, and they kind of go together, so I didn't break them out. I'll just list them as a sort of single result, and I'll mention the differences. So to get a completeness result, we need to prove that they're in p-space, and we also need to prove that they're p-space hard. So the first step to prove that they're in p-space, you might think, well, that's not that difficult. But first of all, you think about there are a lot of strings, that there are infinitely many strings. And then if you start to make combinations of these with non-deterministic objects, they're like, when you determinize them, they're exponentially large. So there's a little bit of work to show that you can do this in polynomial space. But we're able to leverage a recent result in our ICRA paper, which showed a more general result, which is that filter minimization from a non-deterministic input to non-deterministic output is in p-space. So, we can inherit that upper bound. And if you're going from a deterministic filter to an SSO filter, you have to do a little bit of extra work because you need to verify that this thing is indeed a string single outputting filter. And the trick there is you make some product automata. In this case, you've got to make a product with itself and to check that there's some consistency with that. So that gives us the fact that it's in p-space, but to prove that it's p-space hard, we need to go back to the definition of string single outputting, the definition of output simulation. And it's two criteria, right? The first one is that for every string that F can take, G needs to be able to take that too, which we call language inclusion. So it's a requirement that G includes that in its language. And then the second is that it has to produce outputs which are compatible. So we just look at the first condition, just language inclusion. That's kind of enough for us to get hardness. And we do a reduction from a special subclass of NFAs. So in NFAs in general, there's sort of three categories of strings. Strings that are going to reach an accepting state, strings which are going to crash, and strings which are going to just reach no accepting state. And the standard semantics are that crashing and not reaching any accepting state, those are just outside of the language. But in the case of filters, we're not producing, we don't have accepting states, and so only the strings that crash are the ones which are outside of the language. And so in order to make this bridge, we use this result on the subclass of non-deterministic finite automatas that have all states that are final. So we're only talking about crashing is the only way that things can be outside of that. There's also an extra sort of technical requirement that the input alphabet have at least two symbols in it. And then the basic idea is to show that if you want to show the language inclusion between the deterministic filter and the non-deterministic filter, then you take you construct it, you take the automata, you construct that, and you turn it into LF, and then you use this single state filter that we saw from before that takes the whole language, and you just have to check this. As long as you color everything yellow, and now it's just a question of whether the languages are strictly included. And this goes through directly for the construction actually is using SSO filters everywhere. So this goes through there as well. So that gives us both of those steps. So we know that they're p-space complete. Also, because of this sort of technicality, it turns out that there's the subclass where the input string could have cardinality 1, so unitary filters, and it turns out that those are actually in P, which is kind of an interesting side effect of that. So far, I've proposed this category of SSO filters and then discussed sort of why I think they're interesting and then shown that they don't seem to be any different in terms of hardness. So we kept digging to try to find out if there's any difference. Is there any difference? And there is indeed a difference, but it isn't in the language inclusion requirement. It's in the output compatibility requirement. Okay, so let me quickly get to my dirty laundry slide. So this paper has only definitions and hardness results. We don't know of any algorithms for, no direct algorithms for minimization of non-deterministic filters. So, yeah, you know, the A in WAFR is algorithms. We haven't provided any of those. You know, so the idea of SSO really makes sense if you're going to act on the outputs of the particular filter, but they may have some interpretation for estimation tasks, and we don't really have an interpretation of that if it's a passive estimation task. So maybe we need to think a little bit harder about why you might use these filters more generally. One of the things they've looked at is we don't actually go back to the original planning problem and ask whether there are other ways to solve the planning problem. We're just taking the input-output specification that's in the filter. So there are other ways you could potentially compress plans if you know that there are plans and you have a definition of a world and the planning problem itself to be smaller. And the other thing is, of course, we're assuming that we've got explicitly described states. And often the way we produce policies these days is implicitly using tree searches and online methods. So there's a question about how far these results apply. So in this paper, we studied a class of a new class of non-deterministic filters with a constraint. And they have this nice property that, like standard non-determinism, they afford the ability for state reduction, but they allow us to not have to deal with this problem that causation forbids unwinding in the world. And so our results are some new hardness results and sort of a better understanding of the relationship between the hardness of language inclusion and output compatibility. Thank you, Ken.
Thank you very much, Dylan. That is excellent. And you stayed perfectly on time. And so we're going to hold questions for Dylan until after we hear from the other three speakers. Oh, he's got the mic on. Okay, great. So the next talk is with Basak, Vadim, and Steve. Who is presenting? Basak is on video. Okay, great. So do you know how to do that? To turn on the video? Okay, great. All right, so Steve is here. I saw him. Yeah. Oh, great. Vadim is here. So you'll be ready for questions. Excellent. Okay, good. So Basak will present, and we'll switch over to the pre-recorded video for that. And ready to go? Okay, great. Thank you. Thank you. Thank you, Basak. And our third speaker this morning is Michelle, Ani, I believe that, and Alec. Do you have the virtual one? Or? I think we have it. Okay, Janome. Okay. So I can just present it. Oh, you have it? Okay, great. All right. While he's setting up, I just want to make a quick ad for postdocs. If you if you're interested in a postdoc or you have a student who's interested in a postdoc, please let me know. I'm interested in hiring a couple. All right, ready to go? Oh, okay. Great. Michelle's going to present this. And then for the next paper, the Howie Chosit paper, who's presenting that? Oh, you're here? Great. Okay. Perfect. So just go ahead and come up right at the end. And we'll...
Slight delay while we make sure the folks watching online can hear the talk.
Non-zero.
Sorry.
Due to this mic. Online shoot, online.
Hey, I'm sorry to interrupt. This is Howie from the TV land, and we're not sure if people are speaking now or not. We just see, oh, something changed. Hello, can anyone hear us? Can anyone on the chat for online also hear me?
Let me.
This is test two and test two. This is test one.
My fault. I apologize. From this computer?
Yeah, whoever said my fault, I apologize. You sound
Yeah,
great.
I can totally do that. What's about it like? Actually, I need to. Have the presentation on that pocket.
I can email it to you.
Yeah, can you email me? VRMA.
Thank you. And then you'll play it. Oh, yeah. I'll just play that.
Yeah.
It looks like it's might take a minute to arrive.
Yeah. Can you show me?
Here, it says it's not there.
Yeah, I got it.
Okay.
Hello, can people hear? Again, I'm not sure if they're talking or not.
Hello, my name is Michelle Ho, and I'm a rising fourth-year undergraduate at Princeton, and I will be presenting on towards a framework for comparing the complexity of robotic tasks. Let's consider the following pairs of tasks.
So we should move forward to approximately where it stops.
Do you remember?
Use a policy that solves task 2 to solve task 1. To formalize this intuition, we introduce encoders and decoders. Let's consider a space of tasks that include a task 1 and task 2, such as a drone navigating through cylindrical obstacles or trees. We also have observation spaces for both tasks, such as images from the drone's camera, and action spaces, such as motor.
It's not the same? Okay.
Towards a framework for comparing the complexity of robotic tasks. Towards a framework for comparing the complexity of robotic tasks. Let's consider the following.
Oh,
Hey folks, sorry, technical difficulties. We've discussed with the co-chairs and we think that we're going to jump into the presentation where we had where I screwed it up. So my fault that for the people in the room, I kind of butchered everything. But after I butchered it, we figured we would loop
Hello,
everybody
my name
in
is
online
Michelle
so
Ho,
that
and
they
I'm
would also be able to hear. But to try to keep kind of on schedule, we're going to jump in where we were in the talk previously. So my fault. Apologies, everybody.
No worries.
I don't remember where to start from. So, is it this slide? Okay, I'll start from this
The
slide.
environment at time t. We also define the initial state distribution, such as a distribution over the location of a drone and the obstacles in environment, as well as a sensor mapping. We also define a policy pi, such as a neural network, which maps sensor inputs like images to actions like motor torques, with a set of all policies defined by capital pi. Then we consider a robotic task to be described by a reward function, with reward accumulating over time. The reward is described by the equation shown, where R star is the chosen success threshold for completing the task, as well as the upper bound on the reward. And we define a task as a partially observable Markov decision process using this tuple with a state space, action space, observation space, dynamics, sensors mapping, reward function, distribution over initial state space, and a threshold for success, with calligraphic capital T representing a set of tasks. For example, a task could be a drone navigating through an environment with randomly placed obstacles. Policy pi star is admissible on task T if the policy reward is equal to the success threshold. Thus, the set of all admissible policies on the task are all the policies which achieve this reward success threshold. To define our notion of reduction, we draw from ideas from the theory of computational complexity. To review, a Turing reduction is defined for decision problems A and B. A reduces to B if an oracle for B can be used to compute a solution for all instances of A. So with this, we present the intuition for our notion of reduction. Task 1 reduces to task 2 if you can use a policy that solves task 2 to solve task 1. To formalize this intuition, we introduce encoders and decoders. Let's consider a space of tasks that include a task 1 and task 2, such as a drone navigating through cylindrical obstacles or trees. We also have observation spaces for both tasks, such as images from the drone's camera, and action spaces, such as motor torques for the drone's propellers. We use H12 to denote the space of functions from observation space 1 to 2, and G21 to denote the space of functions from action space 2 to 1. Then a encoder function, H, would be a function in the space H, and decoder function G would be in the space G. Then we can use these encoder and decoders to transform the policy that solves task 2 to solve task 1. As shown in the diagram, given an observation space of task 1, we use the encoder to transform it into an observation in the observation space of task 2. Then the robot can use the policy it knows for task 2 to produce an action in the action space of task 2 based on that transformed observation. Then a decoder transforms this action into one that lives in the action space for task 1. Thus, using a policy for task 2, task 1 can be solved. This definition is written formally here. G of pi 2 of H, where pi 2 reaches the success threshold for task 2, lives in the set of all admissible policies that solve task 1. We then prove some properties for reduction. We show that reduction is reflexive, meaning a task reduces to itself, antisymmetric, meaning if task 1 reduces to task 2 and they are not equal, then task 2 does not reduce to task 1, and transitive, meaning if task 1 reduces to task 2 and task 2 reduces to task 3, then task 1 reduces to task 3. Using these properties, we also prove that reduction is a non-strict partial ordering. We also define task equivalence, which is when task 1 reduces to task 2 and task 2 reduces to task 1, and show that this is an equivalence relationship. Complete proofs can be found in our paper. I will now discuss some examples of our notion of reduction. Let's consider a robot that lives in a 2D grid world, and its task is to navigate through obstacles to reach a goal. We show that if the robot knows a policy to navigate to the goal from the map on the left, it can use that policy to navigate to the goal from the map on the right. The encoder function would rotate the map so the observations from the left task correspond to those of the right task. The policy then selects an action, and the decoder would transform this action to the corresponding one required for the original task. Therefore, the task on the left reduces to the one on the right, and vice versa, making these tasks equivalent. In another example, we have a robotic arm with a task to grasp a random object from a different camera location. If the robot knows a policy for grasping an object from one camera viewpoint, the encoder is able to transform the observation to another viewpoint to correspond to observations from the known viewpoint. Thus, if this is possible, then we would have a reduction between these tasks. And since it can go both ways, we could have task equivalents for many camera viewpoints. Still, it may be difficult, however, to use this notion of reduction to compare the complexity of two completely arbitrary tasks, such as grasping an object and avoiding obstacles. So how could we compare these tasks in this case? Since our reduction is a binary relation that does not capture how complex a particular task is relative to another, we also present a quantitative measure of relative complexity. We define the relative complexity of task 1 with respect to task 2 with this equation. Notice that the equation includes the supremum over admissible policies and the infimum over encoders and decoders. We also prove useful properties for our definition of relative complexity. So it is bounded between 0 and 1, and therefore also non-negative. It is also monotonic with respect to the encoder and decoder spaces, meaning increasing their sizes must decrease or not change their relative complexity. We also make connections between reduction and relative complexity. Reduction is equivalent to a relative complexity of 0, and a positive relative complexity is equivalent to no reduction. But please refer to our paper for complete proofs. We present an algorithm for estimating the relative complexity based on adversarial training for robotic tasks in reinforcement learning contexts. We can frame the optimization problem as a two-player zero-sum game where an adversary chooses an admissible policy pi2 to solve task 2 to maximize relative complexity, but the player wants to choose an encoder and decoder to minimize it. Our method is based on best response dynamics, where players update strategies based on the best response to their opponent's choice. We use gradient steps to approximate the solution, since we parameterize the policy, encoder, and decoder of neural networks. Though the full algorithm can be found in our paper, I will highlight two main steps, which are repeated until convergence. First, we update pi2. We want to maximize relative complexity, but remain an admissible policy for task 2. So pi2 is trained to succeed on task 2, and g of pi2 of h is trained to fail on task 1. The latter is scaled by an adversarial tuning parameter alpha to weight the terms relative to each other. When the parameter is too low, the policy on task 2 may not be adversarial enough to prevent g of pi2 of h from succeeding on task 1. So we increase the parameter while ensuring that pi2 is still solving task 2. Secondly, we update the encoder and decoder to minimize relative complexity. And the losses here, L1 and L2, are left arbitrary to allow for the use of various reinforcement learning techniques in experiments. After training, using the trained pi2, g, and h, the relative complexity can then be computed. We demonstrate the use of this algorithm with some reinforcement learning examples. Using OpenAI's GYM's cart pull environment, we define two tests, balancing the frictionless pull against gravity up and balancing it with gravity down. The policy is given the system state vector and selects an action, either push left, push right, or don't apply a force. For every time step that the pull is balanced in the desired direction, the policy receives a reward of 1, the maximum of 200 time steps for the episode. So the success threshold is the same for both tasks, 200, as that indicates that the pull balanced for the entire episode. To approximate the relative complexity of balancing up with respect to balancing down and vice versa, we use our relative complexity approximation algorithm with Q-learning. When varying the adversarial tuning parameter, we see that when the parameter is large enough, the value settles to approximately 0.8 for the relative complexity of balancing up with respect to down, suggesting that balancing up does not reduce to balancing down. The relative complexity of balancing down with respect to up is close to 0 for all values of alpha, suggesting that balancing down reduces to balancing up, according to the previously established equivalence between reduction and 0 relative complexity. In other words, we can use a policy for balancing up to balance down, but not vice versa, which matches our intuition. We also approximated the relative complexity while using different encoder and decoder spaces with varying model and complexity by varying the number of hidden layers. We see that there is no significant change in the approximate relative complexity when the observation encoders in H have more hidden layers. However, when the number of hidden layers of the action decoders in G increased, we see a clear decrease in the relative complexity of balancing down with respect to up, indicating that balancing down reduces to balancing up only for a more expressive G. We also see that relative complexity of balancing up with respect to down slightly decreases for a more expressive G. By a property of monotonicity, increasing the hidden layers of H and G should result in a monotonic decrease in the relative complexity, which matches these results. Another example uses the OpenAI Jim Majoku Walker 2D environment. Tasks are defined with the goal of walking at a particular speed. Thus, the reward function is chosen such that the maximum reward of 1 for the time step is when the robot travels at the goal speed with a maximum episode length of 1,000 time steps. Since the challenge of maintaining a particular speed may vary between different tasks, the threshold for success may also vary. Thus, to define the reward success threshold, we train an individual policy to travel at speed v first, then let RV star be 95% of the individual policy reward on the task of walking at a speed. With this example, we use soft actor critic with our relative complexity approximation algorithm due to a higher dimensionality and a continuous action space. The figure shows the relative complexity of walking at various speeds between 0.6 and 1.4 meters per second with respect to walking at 1 meter per second. We swept through a large range of alpha values, or the adversarial tuning parameter, for each computation and chose the largest one, which resulted in an admissible policy for walking at 1 meter per second. These results are, of course, conditioned on the choice of the encoder and decoder spaces, but we see the relative complexity may be larger when the velocity for task 1 is less than 1 meter per second and smaller when it is greater than 1 meter per second. The plot suggests that there exists an admissible policy for walking at 1 meter per second, which cannot be directly transformed to walk at 0.6 or 0.8 meters per second. But no such policy exists, which prevents a transformation to a policy for walking faster. Our framework, of course, comes with its limitations. For instance, approximating relative complexity is a slow convergence, and we also require admissible policies for both task 1 and 2 to compute relative complexity, which is problematic if that's hard or not possible for one of the tasks. Additionally, our results are conditioned on the choice of encoder and decoder spaces, and this quantifies the difficulty of the reduction, not as simply as polynomial or not polynomial time reductions. The value and interpretability of the relative complexity measure thus depends on how easily one can interpret the expressiveness of the encoder and decoder spaces. In future work, it would be interesting to allow the policy from one task to be used as an oracle to solve another task more generally, rather than the specific encoder policy decoder architecture we use. We could also use our notion of reduction to establish equivalences between broad classes of tasks like complexity classes P and NP in computational complexity. We could define relative complexity with different metrics like data efficiency or difficulty of finding a policy. On the algorithmic front, we could use a different algorithm to estimate relative complexity instead of best response dynamics. To summarize, we've defined a notion of reduction between two tasks, which captures the ability to solve a task with a policy for a different task. We also present relative complexity that quantifies how complex one task is compared to another, and we provide examples for both and present our own relative complexity estimation algorithm. Our results demonstrate consistency with intuitive notions of complexity for these tasks and empirical correspondence to theoretical properties. Thank you for listening.
Thank you, Michelle. Okay, great. So you're coming up to plug in again. Hopefully this will go smoothly. And this is from Evelyn at Carnegie Mellon. And then we'll give her 15 minutes and then we'll do the Q&A and hopefully we can catch up during break. Good. Sounds great. Thanks.
Okay. Hello. I'm Evelyn. I'll be talking today on the optimality and robustness of ergodic search. So first off, what exactly is ergodic search? It's a method for searching and information gathering, usually when you have some given prior assumption on how the information is distributed in a search space. This information is encoded into a probability distribution, which you use to search.
Hey, Evelyn, sorry to interrupt.
The
I
goal
don't think we can
of
see the slides.
producing ergodic trajectories is to produce trajectories such that the spatial distribution of the trajectory and the information measure is minimized. We do this by minimizing the ergodic metric, which is shown on the left, and it includes a difference between the spatial distribution of the trajectory and the information measure with respect to their Fourier coefficients. So the result of like ergodic trajectories is trajectories that spend space in an area corresponding to the information measure present. So it should hopefully spend areas in high information density areas for longer and then spend less time in areas with low information density.
Hey, Evelyn, can you hear me?
Given the
Evelyn,
ergodic trajectory,
Evelyn,
we
can
can
you
then
hear me?
collect measurements and then re-update the information measure. So ergodic metric has been empirically shown to outperform other methods in various tasks such as target localization, area coverage, information gathering, and also learning. And it has also been shown to perform well with respect to distractors. The goal of this work is to understand why exactly ergodic search does well in such tasks and under noisy conditions, to better understand what other sorts of tasks ergodic search would work for. So now on to our prior work. Our
Evelyn,
work
can you
has
hear
two
me?
main contributions.
Evelyn,
First
can you hear me?
contribution is with respect to optimality of information gathering. The goal is to understand when to use ergodic search and also figure out a relationship between information gathering and ergodic search. In terms of prior work, Dressel has worked under the assumption of linear information submodularity, where the act of information collection depletes the information present at a linear rate. They have done work in analytically showing how ergodic trajectories inherently account for linear submodularity, and also empirically demonstrated trends between ergodicity and information gathering. There's also various other experimental evidence for different tasks, as mentioned earlier. So the goal of our work is to understand exactly what optimizing for the ergodic metric optimizes for by proving an equivalent optimization, which we show to be consisting of an information maximization term and plus another penalty term. And through this equivalent optimization, we show how ergodic search inherently accounts for exploration and exploitation. The other contribution of our work is with respect to robustness of ergodicity to distractors. The goal is to understand performance guarantees with respect to bounded errors and to hopefully show that we can avoid costly robust optimization techniques and just use ergodic search directly. There's also prior work with respect to ergodic search performing well under distractors, as mentioned earlier. But the goal of our work is to prove the exact mathematical relationship between ergodicity and distractors. Okay, so now on to the actual meat of the work. We showed how ergodic search inherently accounts for information depletion and show that it also accounts for exploration and exploitation. We do this by showing an equivalent optimization to minimizing the ergodic metric, which consists of two terms. The first term is an information maximization term, which is also an exploitation term that calculates the information present along the trajectory according to the given information measure mu. Though this term itself does not account for information depletion, it by itself tries to encourage visiting areas of high information density. The other term is a self-overlap penalty term, which consists of a Dirac delta function to impose large penalties when points along the trajectory come too close to each other. And the function of this term is to deter the revisiting of already visited locations. So this work helps fill in the missing element between ergodic search and information maximization. And understanding more about the right-hand side term and equivalent optimizations in general can be used to understand what tasks ergodic search is well suited for. We empirically tried to demonstrate this equivalence by finding trajectories to optimize both of the metrics. And we found that they produce similar behavior of exploring areas or visiting areas of high information density, so the exploitation of the prior information, but they also continue to explore other areas, so they should still try to explore. Now, with respect to robustness, what we did is prove that the ergodic metric is inherently robust to Fourier coefficient errors. These errors can arise from measurement error, modeling error, and update frequency. What we did is we proved the exact relationship between Fourier coefficient errors and the result on ergodicity. So here is the bound. The bound itself does not matter so much as what we can do with it. So what we can do with the bound is if we have some desired difference of ergodicity that we want to achieve, some accuracy, for example, then we can solve the bound to find what range of like Fourier coefficient errors we are allowed to have. And of course, you can also go the other way of relating Fourier coefficient errors directly to ergodicity. We show similar bounds with respect to trajectory tracking error and then later also modeling error. So trajectory tracking error would be, for example, if you have a given trajectory, but maybe you have some measurement noise. For this example, we showed small measurement noise and then ranging to larger and larger measurement noise. So the ergodic trajectory is shown in blue and then the noisy trajectory is shown in orange. Again, we proved another bound that relates the trajectory tracking error to Fourier coefficients. And then using the previous result, we can relate it then back to ergodicity. So we also showed a similar bound for modeling error. So this occurs whenever you have like incorrect information about like how the information is distributed. Maybe you think it's distributed according to some other distribution, or maybe the information that you collected is just incorrect. We showed that the ergodic metric is inherently robust to modeling error by proving a similar bound that relates the modeling error to the actual difference in Fourier coefficients. And then again, using this bound, we can relate it back to ergodicity. So for example, if you have a ground truth bimodal distribution, maybe you have an incorrect assumption that the information is actually unimodal, and you try to construct an incorrect model using sampled points from the ground truth. We then would end up trying to create ergodic trajectories according to our assumption model, which is the unimodal one. But then it would end up being executed in real life on like the ground truth model. And what we did is we calculated the ergodicity on the assumption model and also the ground truth model, and found that it doesn't really matter that much in ergodicity because the models are not that different. So in terms of future work can work on demonstrating other equivalences to different information theory things. So we already demonstrated the connection between ergodic search and information maximization, but maybe there's also connections to things, for example, like entropy reduction. And then there's also future works to be done with respect to robustness. So this work was actually done to help prove properties about variance of ergodic search. I was initially looking at like communication constraint ergodic search, but I believe this work is also applicable to ergodic search with respect to an information map that you're updating as time goes on. The way that the robustness bounds can be used is with respect to determining an optimal optimal update frequency of certain things by basically, again, back solving the bounds that I provided earlier. So now onto the dirty laundry side. The main dirty laundry with respect to optimization is, while I proved an equivalent optimization, I never really related how the equivalent optimization ended up corresponding to actual real world tasks. And that was like one of the main goals of this. But the equivalent optimization is a lot more intuitive in figuring out what ergodic search does. And I think future different equivalent optimizations that we can prove will help us gain a better understanding of what ergodic search is optimizing for. And then the other big dirty laundry is with respect to the robustness bounds. So we tried some empirical results and we ended up finding that the bounds are actually pretty large overestimates in all three bounds. So for each of the three bounds, we have like ideas on how to improve the bounds. For example, for the ergodic metric bound, we're thinking of including a component of the ergodicity to help bound it better. And also, we think the trajectory tracking error bound is very loose because our bounds do not rely on any assumptions with respect to agent dynamics. But if you use agent dynamics, then you can get a lot tighter bounds. And then also with respect to modeling error, there's a lot to be done with respect to relating models produced, for example, with maximum likelihood estimation to the actual modeling error. But yeah, that is all for me. Thank you.
Thank you, Michelle. Okay, sorry. We will invite the authors of all four papers and their co-authors up front, and then we'll also encourage the respondents to fire away with questions. We have 15 minutes for this, and I will start a clock, and we're happy to take the first questions. And maybe to warm us up, I'll throw one in myself. So I'll start with Dylan. So you showed a really nice new class of forms for the filters, and you gave an example where there was a clear advantage in that specific case. So you must have used some kind of algorithm to do this, but you said in the end that there was no algorithm. Since it's p-space hard, then there must be some kind of exhaustive search method that would work for this. And I'm curious what you used to generate that example.
So two things. The example that I showed only a small gap. We actually have some of the examples where there's a gap which is bigger than any polynomial, which is kind of a more involved example. But how we came up with those was we were trying to come up with an algorithm for a reduction in another situation, and we looked particularly at a constraint formulation, and we observed that the constraint graph had some interesting properties. Specifically, it was not quite planar, but it was orientable. And then we asked, how is it that we could construct a situation where the graph would not be orientable? And we kind of made up an instance, and then we realized that this would break that algorithm. And we realized that this was sort of representative of another class. So we actually don't have any implementation really at all. We looked a little bit at some of the techniques that are used for automata reduction to the non-deterministic case. And of course, there is, through the reduction in the proof, there is a way that we could indirectly compute some minimization from that. But other than that, we just kind of scratched our heads. And some of the other examples involve prime number constructions and things like this. So we don't really have a very good computational perspective on that.
Thank you. Okay, thanks, Dylan. Other questions from the audience? Okay, great.
Yeah, I have a question about the comparing the complexities slides. Yeah, I mean, it is very interesting work, but I want to ask about how practical it is, because it seems that you guys have to learn both the policies for both, right? I mean, for both the tasks, and but it would be more practical if we don't have to do that, and we still have some way to kind of know like what would be the relative complexity of the task without have to learn both the tasks, without have to learn both policies for the task, and maybe it is more practical, like finding a way to kind of using a policy in one task, to learn the policy in another task. So do you have any thoughts on that?
Great. Yeah, I mean, it's a great point. So I guess I'll just, one note is that in the reductions, you don't need to, I guess, have the oracle for one task to show that it reduces to another. But in the relative complexity, since it's sort of a two-player zero-sum game that's really intractable for any like reasonable size policy spaces, it's a great point. We don't have a good algorithm for doing that, but that's definitely something that we're interested in doing. And as you said, yeah, I mean, using like sort of the policy as a subroutine, not explicitly like one-to-one, time step mapping, is also part of future work that we're definitely interested in. So, I mean, we don't have any great ideas, but if you have some, let us know.
Any other questions? Yes.
I have a question to you. In the examples, you had found the argmin for the minimization of the metric. So what's the algorithm for that? Like, how did you find the path that minimizes the? Yeah, I wanted you to put up the slide, the number 5, but I think it's too late. You have this theorem of equating two argmins, and then you have examples of these paths. So how the question is, how do you find these minimizers?
It's basically just like any trajectory optimization sort of algorithm that like where the optimization objective would be either the ergodic metric for like the one path, and then the other metric, which is like 2 times the information maximization term plus the penalty term. So like specifically for me, I used like the Cassidy framework to produce like the trajectories. I'm not sure if you're asking.
Do you do that in the Fourier space or in the?
So for the ergodic metric, it would require like computation of the Fourier coefficients. But then for the other term, it doesn't require any sort of computation of Fourier space. Yeah.
Okay, I have a question for Evelyn as well. Evelyn, it was very helpful to actually see your definition of ergodicity in terms of information gain. And I'm wondering that, can you say anything about computational complexity here? Because computing maximal information gain is known to be very tricky. So I'm just curious, how is that also then applies to ergodicity?
So in terms of like the metrics, like computing the ergodic metric, it would be like linear with respect to the time horizon, but the equivalent optimization term on the right-hand side, while the information maximization term would be linear with respect to the time horizon, the penalization term ends up being quadratic with respect to the time horizon. So the right-hand side term ends up being pretty bad to use for like optimizing for long time horizons.
So when you say pretty bad, I mean, can you characterize the time complexity, or when in the experiments that you did, is it fairly computationally demanding to find those?
Yeah, like when I was like trying to produce trajectories for like the right-hand side term with like the information maximization with the penalization term, I ended up having to like compress time horizons because it wasn't able to compute for longer ones. Yeah.
All right. Good. Thank you. Other questions? Yep.
This question for Vadim. So there was this mention in passing in the talk about some kind of logical language for specifying tasks, and I'm really curious about that because I think that's one of the most important elements for sort of algorithmic extensions of the kinds of things you're doing here. Particularly made me think of, she stepped out, but Hadassah's talk yesterday, right? These kind of temporal logic things are in a sense a logical way of specifying subsets of the history information space, right? You're doing like some partition and more general kinds of things, right? So I wonder if you could comment a little more on how you represent those tasks and what the implications might be of that in terms of actually computing some of these things.
Yeah, good question. So when I was thinking that we were developing this labeling idea, the more concrete idea behind this is that the states in the state space are actually, each state is actually, could be a mathematical structure that has description, like a first order structure, for example. And so you basically have a time parameterized class of first order models and labels. So these, which in Dylan's work are these multi-labels, and in our work, we also call them labels. I guess sometimes we call it relabeling. But that instead of just colors or elements of some random set, these could be formulas of a language that describe those particular structures. And so then you can write formulas, and yeah, I mean, modal logic can be employed, like temporal logic or other modal logic with quantifiers, it's possible to get to a place where this and this formula will hold, or it's necessary to get to that type of, and so on. And so then you have these transition systems where the labels are not just some labels, but they are actually formulas describing those states of the world. And then you can ask about like definability, and the definability hierarchy would like potentially play together with the complexity hierarchy. And so then figuring out a plan to get somewhere would potentially depend on the complexity of the formula describing the goal. And also then finding these minimal reductions of these filters and sufficient refinement and so on is then also also be restricted by the definability demands. So for example, in Dylan's talk, we saw that not only might we be interested in searching for minimal automata, but actually minimal automata with certain extra properties, deterministic, non-deterministic, and so on. But also we could ask, can we find minimal reductions which are in some sense definable in some logic? So because in the end, that's the real challenge for a robot in a chaotic environment. I mean, there are certain things the robot can internally describe, and then things that it cannot describe. And most things it cannot describe. And so it can happen that even though the task is actually well definable, the policy or the minimal sensory the minimal labeling with certain properties might not be definable in the same logic. And so then we can get into this kind of interesting.
Okay, thank you.
Okay, good. We have time for another question. Yes, way in the back.
I have a question for Professor Dillon. So thank you for the presentation. You gave examples where non-deterministic string single output filters were smaller than deterministic ones. Are there examples for the other side as well, where deterministic are smaller than non-deterministic filters, or is it shown that one is always better?
Well, in the case of, so you can make bad filters, but if we talk about the minimizers, then the one set is a subset of the other, and so it includes all of it. So I guess in the way we understand non-determinism, you look at something and you say there's two edges that are leaving, but usually the class of non-deterministic filters include all the deterministic ones as well, and so that precludes that as an option in the formal definition, as opposed to the informal way we talk about them.
Okay, quickly, I'm just curious for the four of you, in terms of these models, I know you mentioned uncertainty in the context of the POM-DP, but I'm curious, I mean, uncertainty seems so foundational to me, and I'm curious how you think about that in the context of these models. So I'm open for any of you.
I guess one of the advantages of having a POM-DP definition, especially.
Just talk closer.
Yeah, one of the advantages of having a POM-DP definition, at least for the policy, it's sort of like pre-specified. So if the policy can deal with, like the sort of oracle policy can deal with disturbances, then like you can use that as an oracle and not really have to worry about it. But I guess if your input encoder has noise, then that's sort of a whole other set of challenges. I guess we assumed in our setting that you don't have input noises because that all sort of happens in computation land. But that's definitely something to think about.
So I would say that noise is it's a human construction. In the end, what the robot has is observation sequences and has to choose actions. And if you choose to hypothesize probabilities or other stuff to give some representation, you're welcome to do that, but that's part of the sort of human imposition in trying to make sense of that circumstance. And I think that that's a little bit of what's in some of the philosophy and some of the approaches where we look at the starting point as a sequence of observations or sequence of observations and actions. And that's the fundamental thing you have. If you want to believe in probabilities, you're welcome to. But
oh, that's radical. That's radical, Dylan. All right. Well, I think this is good fodder for the coffee break and lunch, because I will disagree with you on that. I think that we have a problem because the data we're getting is not necessarily reliable. So that's what I want to say. You do get data, but that could be data that's not consistent with the state of the world. But anyway, this is something we'll talk about. Thanks. Let's thank all of our speakers for this. Okay, great. So I'm going to turn the floor over to Dorsa to introduce our spectacular keynote speaker.
All right. Okay. Thanks, Ken. So we are about 15 minutes over, but I think we are going to continue with the current program, and we are going to do our keynote. And then after that, we are going to jump to coffee break around 11. We don't have coffee right now, so that's the thing that we need to do. All right. So as Oliver is setting up, let me start introducing Oliver. So it's my pleasure to introduce Oliver Brock, our keynote speaker of the day. So Oliver is a faculty in robotics at TU Berlin. He did his PhD at Stanford, and then after that, he spent some time at Rice, and he was a faculty at UMass Amherst for a little bit. He moved to Berlin around 2009, where he's now running the lab on robotics and biology. He's done quite a bit of foundational work in grasping, manipulation, robot learning, but his interest is pretty diverse. He's done work from building robot hands all the way to doing computational biology work, which is really interesting. He's been recognized by many awards, including he's an IEEE fellow. He was an RSS president from 2012 to 2019. And he also really likes building systems, like really good systems that actually work. So I think in 2015, he won the Amazon Picking Challenge, which was really impressive. One interesting point about Oliver is a little bit briefly he left academia to do a startup back in the day, and this is the All Advantage startup. So at the time they were thinking about buying Google, and this is when Google was small, and they were thinking about, oh, maybe we'll use the search engine as part of our system, which is really impressive. But he decided to come back to academia, work in robotics. And today he wants to talk a little bit about some of the key elements that go into foundations of robotics and if we should rethink them. So with that, welcome, Oliver.
Thank you. Thank you very much for that great introduction and sharing my moment of failure with the rest of the world. This is on the internet, right? Just checking. Yeah. So my presentation, first of all, let me thank the organizers for giving me the opportunity to speak here. WAFR has always been a sort of a meeting and a venue for research that I completely admire. So it's a great honor for me to be here. I think which I tend to do, I bit off a little bit more than I can chew. And so I want to talk about what basic elements form the foundations of robotics. And the brief answer is, I don't know. But I'm going to try to turn this around and make this somewhat informative. So if we talk about the foundations of a discipline, I think it is helpful to look at other disciplines. And one of my favorite examples is chemistry. Mendeleev came up with this beautiful table at the end of the 19th century. And it really kind of exemplifies, to me at least, what I think the foundation of a discipline should be. So you all know this from high school. I don't need to explain that there's a lot of knowledge encoded in this. And it turns out if you take this table, then 5 equations, 5 chemical reactions kind of describe almost everything, right? So what happens with the table and these 5 type of reactions is you can basically span chemistry. Okay, so what did this do? It took some very deep knowledge of how chemistry works and it encoded it in a way that we can apply to new problems, right? It operationalized some deep understanding of the structure of chemistry. And, wouldn't it be cool if we could have that for robotics too? But, that's not the end of the story. I saw this presentation by he's a quantum physicist, and he said, well, the periodic table of elements is garbage. This is the way it should look because this is much simpler. Right? These are the 4 quantum fields, and in some sense, everything around us derives from these quantum fields. Obviously, I would fail to give you 5 reactions, right, that take these 4 fields and then explain everything. And so I guess the lesson here is for the chemist, this would be useless, right? In some sense, it's equivalent to the periodic table of elements, but it would be useless as a tool to start attacking new problems. And so I think what we're looking for in robotics is, either this, if you want to do quantum robotics, or the periodic table of elements, if you want to do chemistry kind of robotics, right? So we're looking for a representation of the underlying structure of the problem at the right level. Okay, so what do we have in terms of foundations of robotics? I'm going to give you, obviously going through some of the work that has come out of my lab, some answers that are really just questions, right? So I'm gonna start talking about regularities, and I cannot really give you an exact definition. I'm going to give you examples, and maybe we can discuss. I'm going to try to leave space for discussion. What we really mean by that? So regularities, I think, are important. I'm going to talk about these first. I'm going to follow up with the consequences, right? If regularities are kind of the elements in the periodic table, what would be the consequences for robotics? We'll talk about how to compose them. If we have these regularities as elements, how can we start composing them? And how can we construct them, right? I mean, how can we create new elements in that table that are useful for us? Okay, so I'm going to start with regularities. And this is kind of a play-along part of the presentation. You guys can all join in. First, I'm going to show you a video of this woman on a train, and please pay attention to her pupils, right? You guys have, everybody knows this, right? You sit in a train and you watch somebody and their eyes kind of keep jumping, right? This is fixation. Your eyes are tracking a particular point. In this case, it's outside of the train. And so you're tracking that while you're moving yourself. And this is what I'm going to refer to as fixation. Your eyes are locked onto a point in space while you move. Now, underlying, so I'm going to show you something that I think is new in robotics. People that study human vision system have known about this all along, but I think it's a very, really cool trick that I'm going to call regularity. So you guys can, again, play along, right? So translation, if you're moving left and right, this is pure translation. The observer is moving left to right. Things in the back are going to move less than in the front, right? You can call this a regularity if you want, right? And this is basically what's underlying structure for motion. Right? There's a big field, structure for motion. You can do this. Rotation is different because pure rotation is basically just shifting the view of the camera. There is nothing that changes, right? The scene just moves in front of you. So all points here move exactly by the same way when you rotate. And this is why people in structure for motion are trying to get rid of rotation. It's a nuisance. But there's an interesting observation. If I want to now fixate on some point, this is the blue dot here, right? If I don't want to, I'll force you to fixate on this. And I ask you to translate, but since you're fixating, you need to use rotation to compensate for that, right? So there's a very specific balance between how you laterally move and how you rotate so that you can keep the blue dot in the center of your image. What happens is that what you're effectively doing is you're picking your rotation of a magnitude, the disparity, right, that results from the rotation of the magnitude to compensate for the disparity that comes from the translation. And so the point stays fixed. So basically, this is what's happening, right? And you're kind of adding the two vectors together, and the vector for the blue dot adds up to 0. That's how you keep fixated on something. So this is an interesting regularity, I would say. It's structure for motion, but it's more specific because you're required to fixate on that point. So it's an additional constraint. And you would say, well, what's the use of that? Well, let me tell you. So here you see a plot. On the x-axis, you see the distance to a target. On the y-axis, you see the error in the distance measurement. And I forgot to tell you, when you fixate, you can use the rate of rotation as a measure of the distance, right? So you're not using the disparity, that structure for motion in its pure form, and that's the red curve. Or you can use the rotation, right? And that's the greenish curve. And you can see that the error is consistently lower than the error with pure structure for motion. So that's interesting, right? I constrained my problem. I made it more limited, and well, maybe not so surprising, the error gets reduced. Now you might say, well, this regularity must be super complicated, and actually, no, it's not. It's really, really simple. I'm not going to go in details, but just showing you that there's nothing to it. It's trivial. And you can use this because it so actively combines perception and action. You can use this to come up with visual serving frameworks that respond to moving obstacles and even to moving target locations. This all very naturally integrates. And now you see kind of this head bobbing of the end effector to estimate the distance based on the rotation angle. So I'm just showing you one random video here. I'm going to wait until it actually has picked up the cube to show that that kind of works. It's bobbing, but then it will go for the kill. So it works also in other scenarios with that would be otherwise difficult, and. Yeah, I mean, that's kind of interesting. It works in scenarios that would be difficult for traditional vision. Like this one, for example. There's an obstacle here that's reflective. And obviously, we know that this is kind of a no-go for computer vision. Well, if you do this kind of the second picture encodes the visual motion direction, right? And so you can see that even though it's reflection, what I actually see is far away out there in space, using this fixation trick, you actually get the right specification that this part is moving to the left. The fixated object is always the red cube. Another example is you have this mesh here, this see-through, right? You can fixate on the cube, and you will still see that the mesh is moving in front of it. Try to do this with traditional kind of vision. Another example, translucency, right? Same thing happens. You can actually see that there's an obstacle. Or here, the whole table is a mirror, and there's like a transparent glass in the back with something on top that gets reflected in the mirror, so it looks like it's super in front. But you can see here it's black, which means it's basically at the same height as the fixated object. So you can classify this. This all comes for free, right? So you took structure for motion, you added a constraint, and all of a sudden, the traditionally difficult things in computer vision go away. That's kind of cool, right? I think. So that's what I mean by regularities. Right? You try to understand what's really going on in the problem, and as a result, you're rewarded by physics with something that actually solves your problems much more accurately and more robustly than you could do it before. So, yeah, and this particular irregularity is interesting because it really couples action and perception, right? I mean, they cannot be separated. They're really part of the same thing. And to me, as a roboticist, that seems very natural, right? Especially if you compare this with the philosophy of traditional vision, like in the sense, plan, act framework, where the actions are completely separated from planning, right? It's a very different kind of view. The person who did this work, or is still doing this work, is Aravind, a very smart guy. And I want to, I said this is going to be play along a little bit. I'm going to show you some visual illusions that I think have strong relation to what I just told you and that exemplify that humans actually do this. So here you can watch Mario and this little turtle move, and I think you will see that they're moving up and down and left and right. But very soon the background will stop moving, and then you will see that they're actually performing circular motions. So your brain is so fixated on the scene, right, that you're perceiving the motion relative, right? This shows that we're really geared towards doing fixation. Here's another one. You can look at the question mark there, and you will get the very convincing impression that something is moving in this image. Actually, nothing is moving. And this is showing that the way your eye detects motion is by motion energy at the edges. And this is also consistent and super helpful if you're doing fixation. So these are basically little portals into your own visual system that confirm that this is what's going on inside the human brain, including the whole visual system, of course. Okay, so I hope I could convince you that regularities are interesting, and if we could come up with a periodic table of them, maybe we could make some interesting progress. But what are the consequences? I'm going to show you here this robotic system that is trying to open the drawer, and Manuel, the PhD student who's doing this, is very mean to this robot. I mean, it's yeah. But the robot eventually, after Manuel gets tired of being evil, will eventually succeed at opening the drawer. Now, you might wonder, what's behind this? This kind of seems to be relatively robust behavior under very adverse conditions. Well, so that's finally, no, not yet. So this, you can imagine, right? It keeps going and then eventually it opens up. At the bottom of this, obviously the task consists of 4 components. The first one is to make contact with the drawer. The second one is to slide down until you reach the handle, to grasp the handle, and then to pull it. So this could be a plan that a planner generates, right? But we've seen that when Manuel is around, this plan is worth nothing because he creates different situations that, so you can now make a contingent planner that accounts for this, right? So if you're in the slide down phase, but somehow he pulls away the drawers, then you need to go back to make contact. And so you can come up with these branching contingent plans, but you can see that this very quickly becomes untractable. So I'm going to propose something else, which is to completely get rid of any kind of sequentiality, right? So, but basically what I'm saying is that these states, make contact, slide down, and so on, are intrinsically linked to particular regularities in the world, and that we can detect these regularities, and when the regularity occurs, we just start executing it. And these regularities compete with each other. So we start with make contact, we go down, slide down, but that fails, so we make contact again, and so on and so forth. So we immediately, we continue this until we succeed. This is what you saw in the video. So there's no planning, right? So by using these regularities and by just building a system that contains 4 regularities and that can look at the world and say, I should use this regularity, it just succeeds under very robust, it's kind of crazy, right? By taking something away that we've worked on for many decades, we're making the system more robust. And I don't know if that means that we're in the way of robust systems, but we can discuss that. Of course, does it work for all tasks? No, it cannot, right? I mean, that makes also sense. It works for all tasks where there's no perceptual aliasing. We need to have a unique mapping from what we see to one of these regularities. Yeah, but I mean, the goal would be to enlarge this space of tasks that don't have perceptual aliasing, and the answer is identify new regularities. Use new regularities to disambiguate these states. So what are the consequences here? Well, I think that this shows that there might be an alternative to our view of defining states, defining actions, and defining transitions, right? This is kind of a different view where we have this bag of things and we don't need to explicitly define transitions. So I don't know. It also questions the boundary between planning and control, because something that we would traditionally consider planning, which is the sequencing of actions, can actually be read out from the world. So the planning here is performed by the world. So the world is really, really helping us. And again, Emmanuel, this is him. He did this. So if we have these regularities and we have some kind of way of sequencing them without sequencing them, can we come up with more complex regularities from simpler ones by composing them, right? This is the question. Because not everything is going to be at that level of physics that I showed you with fixation, right? Things could be at much more abstract level. Regularities can occur at higher levels of abstraction. So I'm going to show this to you in the context of, and this is old work from a former PhD student of mine who's going to start at UT Austin, I think this fall. So our whole world is full of objects that contain these degrees of freedom that are linked to their function, right? You can look at all of these objects, and all the internal degrees of freedom of these objects are relevant to actually using them. So a robot that operates in the world needs to be able to detect these degrees of freedom. And I'm going to show you a brief video just to explain what the video is going to look like. On the bottom right, you see actually a camera pointing at what the robot is seeing, and on the left, you see the model that the robot is building. You see here like a tool drawer that's opened with a little box inside of it that's also open. And you see in green indicated prismatic joints and in red revolute joints that are detected from the stream of images. So, you start by opening the fridge and you detect the revolute joint at the joint there. The robot turns around, looks at this tool chest, drawer gets opened, and so you can see that this, and the cones that you see estimate the uncertainty. So you can see that this works very robust, and this is entirely deep learning free, right? There's no big data set. This just works based on an algorithm. So what's behind it? Of course, I wouldn't be telling you if it weren't, again, regularities. And these are super simple regularities. One is feature motion. It's just the motion of features in the image. And you see this, with a little book being opened there. Then there's rigid body motion at the next level, and this kinematic model, which is what you saw being displayed. Again, the regularity here is spatial coherency, right? Things are moving together because they are on the same object. So that's a regularity in the world. Rigid bodies formed by themselves, a way how things can move. The features in your image move, depends on rigid body motion, and then these bodies get composed into kinematic models. Now, the key here is of composing regularities is that you see the little blue arrows. Every regularity can help each other. If you understand that two rigid bodies are connected by a revolute joint, then that is information that can help the rigid body estimator estimate the trajectory of the rigid body, because they need to stay connected. They cannot just drift apart. So you're taking very noisy data, and let me just interject here. I completely agree with what you said, and I'd be happy to discuss with you and Ken over lunch. The data comes in noisy, but we have to somehow deal with this. And so every one of these phases, if you want, every one of these regularities makes the data more solid, and we can feed the information back. That's where the robustness comes from. So the dream is that we create from these little estimation blocks, each of them is a regularity. We create this language that we can start using to compose much more complex things. Right? This would be the whole. So in some sense, this would be the generative rule, as you saw with the 5 rules for chemical reactions, that we can add to the robotic table of elements. And so we've actually done this, and here is one system that we've built. It has actually 4 sensor modalities that are being fed into the system, and it outcomes, an estimate of the world around the robot. And here you see, again, the robot view on the right and an external view on the left. What you're going to see is that the robot opens the drawer and it estimates the joint and how far it has moved the drawer. And then the light's going to be turned off. Right? And so all of a sudden, the robot cannot work anymore, but they still have encoders, right? And so you can compensate for the very noisy information from vision using your own encoders. And so you see that it starts moving, it finds the prismatic joint, estimates the distance that has moved, and the light turns off. On the external view, you see now the night vision. And then the light turns back on, and you can see that the distance was estimated continuously. And this is not something that you have to program into this. The regularities notice that there is certain noise on their sensor and merge the information accordingly to the noise. And so once vision fails, you just trust your encoders. So this was just one example of how you can take these regularities and you can start composing them, right? And this is all done by hand right now, and it's just one use case if you want. But the question is that maybe a reasonable way to program robots by taking regularities and by starting to compose them? Yeah, so Roberto is the student that did most of the work I just showed, and Vito, Manuel, and Aravind, the two on the right you already saw before, are kind of all working together on kind of expanding this. I wanna show you that this actually has strong ties to how people think the perceptual system of humans work. So here's a picture from a review paper from 2002 that is called Hierarchies and Reverse Hierarchies in the Visual System. And you can see, on the right, you see these three regularities that we were using. There's kind of this architectural resemblance of how they describe the human perceptual system, starting with edge detectors all the way at the bottom, going up towards really recognizing kind of abstract things. And they're saying how there's obviously information flow. You recognize face by first detecting edges and turning that into a face. But by expecting a face, you can also propagate information down and disambiguate things from your expectation. And this is exactly what happens also in our system. And of course, again, the visual illusion to illustrate that this is going on inside of your head. I'm going to show you a picture. There's a black dot in the middle, and please just look at that black dot and see what happens. So what's happening is that you should see like an afterglow of color once you see the outline of the four-pronged star. Right? So you should see the complementary color. So when the star was green, the afterglow should be reddish and vice versa. And so this is, it used to be explained with the receptors on your retina get tired and deplete in chemicals. And so, that's just an after effect of chemistry. But it turns out, if you look closely, the area in the middle is shown as gray, but your brain fills in green or red. Your brain or your eye has never seen that, right? So this shows that there are two things that you estimate separately, the shape and the color. And when you're triggered to sort of remember the shape, it fills in the color that somehow was estimated for that shape, right? So this shows that your brain is estimating two things, or your visual system is estimating two things that get combined in your perception. Another example of this, again, there's a white dot in the middle now. Please just look at that white dot. You see, you know what you see. And so your perception should be that the dots are changing color. When they start spinning, that gets suppressed. And when it stops spinning, it starts changing color again. If you look at the bottom, the title of the paper is Motion Silences Awareness of Visual Change. So the dots blink the whole time, but when they rotate, you don't perceive it. So again, you kind of have two competing things that you're estimating, and one is more urgent, like something jumping at you can kill you. Something just changing color is just funny, right? So it's more important for you to perceive the motion, and it suppresses the other motion. Yeah, of course. Yeah, just track one dot now. Yeah, right? So interesting. And there's many, many more. I mean, I had to, yeah, these things are fascinating. So we talked about regularities. We talked about the consequences. We talked about composition. What remains is construction, right? So now we want to create new elements. I'm going to show you a regularity. So here you see a hand holding this donut-shaped wooden piece. And at the bottom, you see a plot showing you the actuation levels of two actuators in the thumb. And you can see that the actuation level changes during the first half second and then remains constant until the end. And you also see that the only change that happens in actuation is in the thumb. So any motion that you will observe in the index finger will not have been actuated. Actuation starts, it stops, but the system continues to move. So we inject some energy in the beginning, but there is a regularity encoded in the morphology of the hand that robustly releases that energy into this rotating motion. And this works for different shapes, different orientations of the hand, and so on and so forth. So it's something that is uncertainty rejecting encoded in the hand. You know, you might want to call it a self-stabilizing manifold in the space of behaviors of the hand. So by building hands and by programming them, we can come up with new regularities. Let me show you how we program the hand so far. We have this hand that has 14 different actuators, and we have these little musical mixing boards that we use to actuate each actuator, and we kind of program it this way, and the program then looks like this. On the x-axis you have time, on the y-axis you have the actuation signal, and you see here two plots of the actuation signal changing over time. All of this was programmed by moving these sliders. And this is entirely open loop, right? So the outcome of these programmed primitives is behavior like this. Open loop, right? And I mean, the video actually runs for a couple of minutes. I'm not going to play it all, but you see that the motion kind of looks very natural, and it's open loop, right? So it's sequencing a number of primitives that are so robust that somehow the sequencing works. Yeah, and maybe, well, no, I won't mention this now. Maybe I'll mention it later. Yeah, so this works. It kind of looks pretty natural almost, right? The way this gets manipulated, but how robust or how robustifying is this regularity really? So we tested this. We tested it by running the exact same open loop program on all of these objects, different shape, different weight, and so on. And the exact same open loop program succeeds with all of them, right? And that must be something that the hand contributes to, because the motion that results must be different. It's the hand that contributes this extra thing on top of what we program. Just to show off a little bit, here we basically then continuously executed this rotation skill. I fast forwarded to the failure because that's the most interesting part. But this is the 146 iteration sequentially of this open loop program, right? And here something bad happens, and then the cube drops. Ugh, that was it. But 446 times before that, right? And so then the question arose, well, you know, is it quasi-static? Is it dynamic? What does it matter? So here is the execution of the same skill in 0.8 seconds, right? I mean, that's difficult to even watch. And now comes the execution of this super slow. And we won't watch this, but the point is that this strategy, this regularity that we encoded into the hand is super robust, even to vast differences in the dynamicity of what's going on. Yeah, and here is another example. We show with this white dot and the arrow the initial configuration of the cube. And then we start executing the same skill, this rotate followed by a shift. And you can see that for a variety of initial positions of the cube, this works very robustly. Not only does it work robustly, it provides this convergence of these different starting locations onto a much smaller set of states. So there's uncertainty reducing power inside the hand. Yeah. So this all to show that there is something, right? There is something that we add by using the morphology of the hand. And maybe I'll do mention this as a little side discussion while I play this video again. No. So you probably have seen a very similar demo from OpenAI a couple of years ago, right? And I want to point out that they have kind of taken the exact opposite approach. Here, we're taking the approach with how little sensing and programming and learning can we get away, how much can we push into the hardware itself. And they kind of came from the opposite end and said, well, you know, we're going to make simulation, several years of simulation, lots of data, a domain randomization, and we're going to generate so much data that we can learn how to do this, right? So I think that this shows that the problem of doing these in-hand manipulations is rather or more easily addressed on the hardware side. But the next question we have to answer is, how do we actually generate these regularities? Because this was hand-coded, right? So somehow this is then where learning and all of these tools come in, right? How can we find these regularities? And you know, so we started looking at that, and we started doing some deep learning on this, and it actually didn't really work so fabulously well. And so I want to show you what actually was super simple and worked well. But before that, I want to just show you the people who did this. Stefan Pullman is the main person behind the hand, and Adrian and Aditya did all the in-hand manipulation. So the question is in the room, right? How do we actually generate these regularities? How do first of all, this is important. These regularities consist of the morphology in the hand and the hardware and the control, right? So this immediately points to the fact that we need to do co-design. We cannot just design a universal hand and then come up with some control. We need to think of these two things as two sides of one metal, right? And so I think co-design is something that will really become important to robotics in the future. It already is, but even more. So yeah, the question is, how do we come up with these regularities? And I'm now going to focus only on one part. I'm not going to talk about co-design. I'm just going to talk about the control, because that's kind of the question that comes out of the comparison with OpenAI. So what we usually do in robotics, I think, is that we have some way of measuring the error, which is E here. We have some kind of change that we want to apply to the actuation, which is this delta A. And we just come up with a Jacobian, right? And well, just come up is easily said, because a lot of modeling goes into the system before we can actually compute a Jacobian. And the hands that you saw, they're flexible. Good luck coming up with a model of that. And good luck computing a Jacobian of that model, right? So somehow what we used to do, and that's why we have hard robots with joints, because that makes it easy to compute these Jacobians. So that doesn't seem to work anymore, or does it? Well, the good news is it still does. The Jacobian is still the key, and we can make it work in a very, very simple way. But we need sensing. We need to actually put sensing on the hand so that we can come up with a Jacobian that's directly in in the transformation space, in the deformation space of the hand. Right? So we're
Jacobian of what?
exactly. Yeah, of what? Right? This is exactly the question. I don't know, right? I mean, so we used to have it of a kinematic model, and now we have this soft robot with millions of degrees of freedom, and we can try to model that as a kinematic thing. But yeah, so well, Jacobian is just a mapping between two spaces, right? So this is the way I refer to Jacobian, and the question is, where do we get it from, right? And this is what I'm going to show you. So we can get it directly from very quick interactions with the object. We can see how does our actuation, delta A, relate to the error defined in some space of deformation. So first we need to sensorize the hand. And this is showing you a sensor that is sensorizing the thumb, the mobility of the thumb. And you can see that you move the thumb, and these sensors can measure very robustly the deformation. There's another type of sensor, strain sensor, that you see here on the finger. And again, you can kind of measure, even though there are all these many degrees of freedom, these deformations actually live on some lower dimension, much lower dimensional manifolds. So you can reconstruct from few sensor readings the shape of the hand. And so here's one very, very simple example of how we do extract such a Jacobian directly from interacting with the object. So here's 3 different objects in the same hand. The goal is to rotate it in the visual plane that you see as much as possible clockwise, right? And so what you will see in each 3 cases is the robot kind of tries little motions, measures the deformation, and from that derives the Jacobian. How does my actuation relate to the deformation? How can I reduce the error by changing the actuation? So it's very simple numerical, extracting it directly from the hand. So this is the playing around. And then it understands how actuation relates to deformation and moves these things. And you can look at the Jacobians that result from these 3 objects. And they're slightly different, obviously, because the objects have different diameter and different shape. But you can extract them very, very quickly. And so the idea is now that maybe you can have a library of these Jacobians. And when you have an object in your hand, you can very quickly identify, I move it a little bit, does it behave like the first, the second, or the third object? And you basically just have this database of Jacobians that you can retrieve immediately from some minimal sensor experience. Yeah, and the last one. Yeah, so I think Jacobian stays with us, and it becomes even completely simple because we don't even need a model. We can just use the whole world as a model and get the information that we need out of it. This is Adrian who does this. One last thing, I talked about co-design. When you include the body in the whole mix, interesting things can happen. I pointed to the fact that we really depend on sensing if we want to do this interactive extraction of Jacobians. And here you have one way of sensing. This is a cut of a finger, right? So these are pneumatically actuated. So it's the air chamber that we inflate to actuate the finger. On the right, you see a loudspeaker, and on the left, you see a microphone. And so we play a little sound inside the finger that we record. And just like a violin, like a Stradivari, you play the same sound, it sounds very different than like some cheap violin, right? Even though it looks the same. So somehow sound is very good at disambiguating states of matter that it interacts with. And so this is exactly what we leverage here, that if there's a contact somewhere, so you can reconstruct the temperature of the environment. You can reconstruct where the finger is contacting the environment, what the force is, and so on. You can reconstruct the shape of the finger. You can do all of these things using this acoustic sensing. But I want to show you just one application, which is reading Braille. Right? So wouldn't it be cool if using acoustic sensing, we could read Braille? So we tried this. We bought one of those Braille displays, and it's actually a challenging tactile sensing problem. The pins are 2.5 millimeters apart. They only have a 0.7 millimeter height, and the force with which the pins are being pushed up is just 0.17 Newton. Right. So this is a challenging task, and we put our finger onto the Braille display, and as you see in the bottom row there, we show different patterns. And the question is, can the finger read Braille? Yeah, so this is a confusion matrix, and you see a very strong diagonal. So yes, the answer is you can read Braille with a classification rate of 96%, which I think is higher than in humans. Humans have context, they read like the whole word, but I think individual letters, you don't get very high, it's probably above 90, but I think this is competitive with humans at least. So yeah, if you look at what goes wrong, it's P and S and Q and T that get confused, and you kind of see that there's only one pin difference, and that pin is surrounded by elevated pins, and so that kind of masks out that. And we also have the suspicion that this top left pin is the weakest pin in terms of force pushing up, and so that makes it then difficult to distinguish. Yeah, so this acoustic work is Vincent who did this. So construction, right? I showed you that we can actually encode regularities in hardware. I showed you that we can use regularities encoded in hardware for sensing. I showed you that we can extract software regularities from very little interaction with the entire system. And so if we, and we don't, but if we understood how to do all of this, I think it would be plausible that we can actually create very competent robots that interact with the world, leveraging the power of both the hardware and the software. So before I come to a close, I just want to briefly mention this research center that's called Science of Intelligence that in Berlin is studying kind of questions like this, and overall the question, what is intelligence, together with people from neuroscience, psychology, behavioral biology, and people like us. So I think there's a lot of very interesting things going on there. And if you're interested in what's going on in robotics in Berlin, Marc Toussaint and I have created a website called robotics.berlin, coolest URL in the world. Where it's very sparse right now, but we're trying to kind of put on all the content that we have going on in robotics in Berlin. So to conclude, I admire chemistry, right? Because they have this compass consisting of this periodic table of elements and these template reactions, and any chemical problem you want to address, these are your first go-to, right? You can use this to help you solve problems. I want the same thing for robotics. And I don't know if anything that I've talked about today will serve as anything similar to the periodic table of elements. But I just wanted to kind of point out that we should question some of the assumptions that we've been making for a long time. And we should always have an eye on this periodic table and ask ourselves, are we in the progress of developing something like this? Are we making progress towards really generating a foundation for robotics that allows us a jump start on addressing completely new problems? So I think that's all I wanted to say, and I thank you for patiently listening to me, and I look forward to discussion.
All right, questions for Oliver?
Thanks, Oliver. Great talk. I had a question on the Jacobian part, because it seems like the Jacobian you compute is going to be specific not only to the object, but also to the configuration of the fingers at the time. And as soon as you move, the Jacobian is going to be invalid. So I wonder how you can actually make this tractable to store a library of all these Jacobians.
So basically, the Jacobians become Jacobian is a function of time. They become trajectories in Jacobian space. And this Jacobian gets, as you point out correctly, it gets updated, every time step. And so, yeah, I mean, you get, it's just in a higher dimensional space, you get these trajectories of Jacobians for certain manipulations. The hope would be that the hand itself provides kind of a regularizer on this, so that even though the hand configuration varies slightly, and even though the object might vary in size or shape slightly, you still get a very robust behavior tracking, as we've shown with the open loop, so not adapted strategies, right? So those work for a variety of objects, and the hope is that basically the morphology and the softness of the hand provides this funnel around all of these Jacobian trajectories. Does that make sense?
It does, but well, maybe we should talk more about it later. But I just had a quick philosophical questions as well. So I think you talked a lot about the analog of these rules, right? All the composition and all the stuff you're doing there. But I didn't get a clear picture of what the analog of the periodic table is in robotics. Like, what are the elements themselves?
It would be these regularities, right? It would be these regularities that are relevant for a particular problem. So you could, I mean, I don't want to push the periodic table analogy too far, right? But let's have fun with it, right? So I think, we need periodic tables that are different for categories of problems, right? This is all chemistry, but we're trying to, I think, address vastly different applications, or even scenarios, if you want, of physics, right? We have nanorobots where the interactions with the environment are very different than for macro robots. So I think we need periodic tables that contain the relevant regularities for all of these different tasks, and then we need to be able to compose them. But I'm just saying that for the sake of discussion, right? I don't really. I'm not sure if it's a plausible path, but it seems to me at least as plausible as what we're doing now.
Okay. Yeah. I mean, it's just a little bit unclear to me, because the regularities that you talk about are so task specific, whereas the periodic table is like inherently universal. So I didn't. See how we're doing.
So I mean, I showed you the regularity of fixation. Thank you. Right. So that regularity is universal for everything. I mean, that regularity is it. But it's not an element that exists, right? It's again it's a formula with variables, and it's a regularity that exists in a high dimensional space. So as we try to generate temporally extended actions, we need to represent the temporally extended relationship of things. And that's exactly what this example of the fixation did.
Okay, I would call that more of a pattern that can apply to things rather than a specific element that you can.
It's an analogy, right? Let's call it pattern if you prefer that. Okay. But there's no patterns, I mean, the elements. So yeah, it's an analogy, right? And you're.
Okay, great.
Okay, so we'll do Vadim and then Kostas and then Ken, and then there's another question.
Thank you. Very inspiring. Are you aware of work by Gibson in the 70s?
Absolutely, yes.
Yeah, it reminds me a lot of that. And I think these things actually are, universal. And not as universal as the chemistry, because chemistry is like very universal. But this thing, like Gibson makes a case that every living organism will perceive invariants that are relevant for its own movement. Like every mammal, every lizard, even every insect will perceive planes on which it can walk, and it will perceive obstacles which harm walking, and so on. And so he claimed that that we're not actually perceiving colors and shapes. He said it's a mistake. We actually perceive things where we can walk. We perceive invariants that are related to our abilities to move in the world. So, any
Absolutely.
thoughts?
Absolutely. I mean, I admire Gibson, even though he kind of fell out of favor in the current world of psychophysics, the psychologists that study these things. But I totally agree, right? And I would even go one step further. I think if we reset evolution and all the species would evolve again, fixation would come about, because it is inherent in the physics of our world. We'd actually have to change the physics. If extraterrestrials came to our planet, they would use fixation, big claim. But, because it actually is the right thing to do. It solves the problem more easily than other things. So it's now a question of what you mean by universality, right? And I don't know whether there are gradations or not, but I think when I talked about the quantum, right, and the periodic table, the question really is not one of principle; it's one of usefulness, right? So the question is, what can you do with it? We don't need to compare, I think, universality of elements versus regularities. The question is, can you actually use them to do useful things?
Thanks. So,
Yeah.
oh, Kostas first. I'm sorry. Go ahead.
Yeah, indeed, great work across so many aspects of robotics. I have two questions. One is more broad and the other one is more specific. The broad question is, do you have a brief definition of regularities that I can take back to my students and say, that's what Oliver talked about without examples?
Yeah. So I do. It's on my iPad. I was prepared for that question, but now I forgot. No, but basically, it's a manifold, right? It's a lower dimensional manifold where I have it written down. It's so I think it's premature to come up with a definition, right? Because this is just a bunch of examples, right? I think we need to look for these patterns elsewhere. And then we'll see. But I'll try. So it's a lower dimensional manifold, right? In a task, action, sensing, time, space, and it captures a relationship between all of these different dimensions that is relevant to the task, and that is easily detectable in the evolution of the world system in such a way that it can be used to reduce uncertainty that's introduced by all kinds of things, right? So it must be robustly detectable, it must be task relevant, and it expresses a relationship between action and perception and time that is helping you to advance towards the task. That's not a definition, I know, but that's kind of, I think, what a regularity is.
Yeah, thanks. I think it's good to have it. Can I ask specifically about the problem where your group member was torturing the robot and trying to open the... You said, if something goes wrong in the second step, then you have to go back, and you showed kind of an exponential explosion if you try to think of this as a plan. At the same time, you could just put loops back from each node to the previous one, right? And the sequence still has to be respected for the task to be solved.
Exactly. It's equivalent, right? So it's again, it goes back to the representation of the periodic table or the table of the four quantum fields, right? Everything is equivalent ultimately, right? So yes, I mean, it's not just back to the previous node. You need to connect all nodes with all nodes, right? Because you can, right? So you have a fully connected graph.
Can you jump forward there? So you can.
Yes, you can. I mean, he could have come in and opened the drawer for the robot, right? That can happen. So you would have to have all connections. And then the idea is, why do you represent this connectivity when it's universal, right? When you can jump from anywhere. So you need a criterion to jump from one to the next. And the criterion, you have it. So there's no value in representing this universal traversability.
Great, thanks.
Thanks, Oliver. I also wanted to commend you on the always provocative nature of your talks. This one is no exception, and I think that I really have to commend you the example with the rotating cube, getting that kind of number 446 rotations or so.
146.
146. Okay, but no matter what, I mean, it's very impressive. You got more than two.
Exactly. Yeah.
Yeah. So that's really intriguing. And so I also have this question about the terminology. I think regularities is maybe it's the translation between languages too here, because I hear it sounds a little, I mean, I hear invariants, affordances in terms of Gibson, and then what Beakey talks about synergies for grasping. So I see these different terms and I'm trying to understand how you're thinking about them as different here. I do think there is something very definitely there in that there's this phenomenon in tasks. And if you can identify these elements, let's call them, then there's an analogy that comes to mind. First, let you answer about the terminology.
Yeah, I mean, awesome question, because I think that's exactly what we should do as a community, right? We should try to narrow down. I mean, also the question for the definition is great, right? We should try to narrow things down. So let me start with synergy. All right, synergy, I think, is something very specific. It's a coupling of active degrees of freedom, right? So this is just a technical thing, has nothing to do. I mean, you can have a synergy in a completely non-constructive way, right? So regularity for me it could be expressed as a synergy, but it would have to be a synergy that actually does something useful, right? I mean, synergy just says, I couple actuation degrees of freedom in a certain way. Right, so I have a lower dimensionality signal, and I expand that because I know the correlation between all the actuation signals into a higher dimension. Right, so that's to me very technical. Regularity is more semantic. It actually means it's helpful, right? And then invariant, you said?
Invariant and affordances.
Affordances, maybe. Yeah, I mean, to me, an affordance is something from the perspective of an agent, right? So an affordance is an opportunity for an agent to instantiate some kind of controller on features of the environment given their embodiment, right? So this affords grasping, and that includes possibly many regularities, right? It's already kind of at a different level of abstraction. It is something that I can reason about to help me understand the world, right? So it's I think the regularities I'm talking about are kind of really in the world, physics, whereas this is including the body, and the body is conditioned, right? I can instantiate, I can use regularities given my particular body. So it's also much bigger. That one is much bigger for me than regularities.
Great. Okay, good. This is interesting. So I see Alon had his hand up, and I want to make sure he has time. So, but I'll just say this analogy, which strikes me in database design, there was this idea that if you just took all of the attributes, if you could boil down to the attributes, that you could synthesize the structure of the database using these functional dependencies. And there was a lot of hope that this was an alternative to the other classical way of designing databases, which feels more ad hoc and intuitive. But what that ran into ultimately was that it was very difficult to specify the functional dependencies. So there might be something analogous here, that if we had the elements, still finding the functional dependencies between them may be the challenge.
Yeah, so I think that's also a good point. The compositionality I try to show is an incremental one, right? So again, it is an analogy, right? So I think what happens with our periodic table of elements is that there's layers to it, right? You have the basic ones that are like the fixation that I showed, right? I don't think even that one was composed of translation and rotation, right? But maybe there is some atomic regularities, and then you can build much more complex ones of them, right? And so you're right. In principle, if we don't have any structure, all problems are intractable, right? So I would hope that the actual world, and we're all proof of this possibly being true, that the world contains enough structure so that the regularities can be built on top of each other in a useful way without becoming like a house of cards. right? So that you actually build a robust foundation and every layer on top of it remains equally robust without kind of having this, is it going to tip over kind of question. But I don't know if this is going to happen, but we'll see. Yeah.
All right, great discussion, but I suggest we move the discussion to the coffee. Sorry, Elon. The two questions over. Okay, go ahead quickly. Sorry, students here.
First of all, the periodic table and the music analogies are very clear and very inspiring. I should let you know in the audience that the regularities, people were here saying it's ambiguous, so we are confused. Let me suggest that some of the key examples, the drawer manipulation and the cube manipulation, has to do with grasp mechanics. It was suggested by some roboticists to use the notion of basins of attraction of dynamical systems. Specifically, the cube, when you handle it with your fingers, you hold it in what we called basket grasp, which is gravity-based caging that Ken Goldberg and myself happen to be involved in. And you mentioned that you have a reduction of uncertainty. Surely, it's convergent to the local minimum of the gravitational potential energy. So we might think about what people have done, like Daniel Kodicek, chaining basins of attraction.
Absolutely, this is exactly what we do, right? This is exactly what we do. We even call it that. So I presented a particular perspective on this here, but this is exactly what we do. If you look at the papers, there's funnels that are leading into each other, and dynamic systems is absolutely underlying all of this. Absolutely correct. Yeah.
All right. Okay, thanks, Oliver. And yeah, thanks for the great talk. Let's thank Oliver.
Thank you.
Yeah, I think there were a couple of questions on this side. They can kind of like find you during coffee break. So let's take coffee break until 11:25. And there is going to be a lab tour starting at 11:25. So if you're interested in lab tour, hang out at the registration desk. If you're not interested in lab tour, you can come here. There's going to be an NSF talk. Yes. 11:25.
Thanks. Thanks. Hmm? Oh, I thought I was going to keep that.
Thank you.
Thank you.
How do I turn this on? It's here. So,
We can maybe talk about. NRI sunset that will affect the full amount of financial. Yeah. So you guys.
And you can answer.
Okay.
I think Eric has.
We'll give you some numbers to make you happy.
X, okay, so X is, okay. Fair enough. Okay.
Where is this recording share?
So I think we're ready to start.
Oh, I'll get out of here.
Am I good to go?
Oh, wait, am I supposed to get the mic too? Okay.
I can have this.
Okay. Yeah.
All right, thank you.
We also have.
All right. Thank you, everyone, for attending. We are here from the National Science Foundation to talk to you about the different programs that NSF has in robotics. It gives me a great pleasure to be at WAFR. I think WAFR was one of maybe the second conference that I attended as a PhD student. So I'm glad to come here, perhaps in a different role for today. My name is Erion Placu. I'm a program director at NSF. I'm a rotator at NSF, and I am with the SciENS Directorate and the Information and Intelligence Systems Division. And I'm joined together with my two colleagues, Irina Dolinskaya and Jordan Berg. You want to introduce yourself briefly? Yes, please.
Okay, my name is Irina Dolinskaya. As of last week, I was program director in engineering. This week, I started as the new deputy division director in SciENS now, in the Computing Communication Foundation division.
I'm Jordan Berg. I'm a federal program officer in the Civil Mechanical and Manufacturing Innovation Division of the Engineering Directorate.
Thank you. So today we're going to talk a little bit about NRI, the fact that NRI was sunset, and spend most of the time talking about foundational research in robotics and some other programs that are at NSF that are robotics related. So as you might have seen, there was a DCL letter that was issued that announced the sunset of the National Robotics Initiative, which was in its third iteration, Innovations in Integrations of Robotics Program. And NRI has been going on for quite a number of years, almost 12 years. And over this lifetime, NRI has invested a lot of money, around $250 million in over 300 pioneering research projects. And NRI has been a collaboration between NSF and a number of federal agencies. So the good news is that NSF remains committed to supporting and growing a thriving robotics community. So even now we don't have NRI anymore, the NSF supports remains there. And now we have the foundational research in robotics, and this will serve as the main home for robotics research at NSF. And we'll talk more about FRR, but just generally, FRR is very broad. It welcomes proposals in a broad set of topics, including proposals that focus on integration. A unique feature of NRI was the collaboration between NSF and various federal agencies, and FRR will try to build on this pattern and continue having or building these partnerships with various federal agencies. And as those partnerships are going to be built, we are going to announce them as the time comes. And the mechanism for announcing these partnerships will probably be through Dear Colleague letters. And there will be updates in our Foundational Research in Robotics program website. So now we are going to switch gears and talk a little bit more about foundational research in robotics. So Irina is going to get us started, and then we are going to continue. Thank you, Irina.
All right, works, yeah. Oh. I'm hearing echo, right? Is that normal? Okay. All right. That's fine. Okay. So I will talk. It's okay. All right. I will talk about the foundational research in robotic program, since that is now the flagship, the robotics program at NSF. So definitely this community should know about it, should think about what projects you want to submit, and definitely submit proposals coming in. So to make sure that you fully understand the program, so weird. It's a program jointly run between engineering and computer scientists. So it is really a unique program for National Science Foundation because it is a core program, means we don't have annual solicitations with deadlines and specific requirements, how many PIs can submit and what specific themes you have to address. It's a core program, means it's a program that has intentionally a very open-ended description of the type of robotics proposals that we want to fund. And I will talk about that more in a minute. But besides that, that's all it is. So you really just follow the standard NSF PPPG. This is a proposal award and guide, whatever that's basically the standard guidance for submitting proposals to NSF. So it is, as I mentioned, program cross-director between engineering and science. Actually, I guess we haven't updated. As I mentioned, I just moved to science this week. But you can see there's 5 different divisions participating and 2 directorates. And we'll talk more about, the question we often ask, well, which division do I go to? Who do I talk to? And again, the goal, which, and I think we've successfully accomplished for this program, it's a one unified program. There is no, is this a size engineer, size robotics proposal? Is this engineering? We really created this kind of unifying one home, and we'll talk more about that. So what actually kind of FRR supports, right? So we support foundational advances in robotics. And the goal of creating this program and the goal of how we set it up is to bridge this or bring together the silos between the computer scientists working in robotics or the engineers and really bring it together into just one robotics research community. And I'll talk more about how we do it at every stage of how we run the proposals, how we review proposals, and how we actually make their words. So as I mentioned again, it's intentionally very broadly defined program, but we do need to define what robot means for this program. And again, you'll see very open one, right? So it's intentionally very broad. It's defined as an intelligence embodied in an engineered construct. And we define a little bit more, give you a little bit more definition of what intelligence and the engineered construct means. But again, it's intentionally quite broad. So think about, NSF loves to fund really out-the-box kind of innovative ideas. So think about, if you're thinking of a robotic system and you want to stretch some of those definitions, absolutely come and talk to us, right? This is something that we are open to. So the next thing that we need to talk about, okay, what is actually the project doing? So as I mentioned, the robot needs to be there, and I'll reiterate it again. And then when you're looking at the advancements, so there's intelligence part, there's the embodiment part, the kind of the engineered construct part. You don't necessarily need in every proposal be innovating both sides, right? So you could be saying I'm using existing engineering kind of configuration, but I'm really advancing the intelligence aspect of it, or the other way around. And of course, we welcome proposals that do anywhere in between on the spectrum between the advancing those. And I should mention that meaningful experimentation validation on physical platforms is encouraged, but it is not a requirement. If it doesn't make sense for your specific proposal, if you're really making advancements in foundational, algorithmic foundation aspects of robotics, maybe doing, validation on physical system, it really doesn't make sense. It's not needed to validate and show that you're making advancements. So please don't feel like you have to add it or you have to do it because you think it's going to, improve your, like it's kind of, hidden fine print that you have to do it. No, we really encourage it when it makes sense, but when it doesn't make sense, that's perfectly fine. So what is responsive to FRR? So, and we've actually recently updated the program description for this to actually explicitly include these 3 questions in the program description. So if you go on our program website, you'll see them. But basically for every proposal coming in, or when you send us a project idea, what we asking you, well, we will be asking kind of the project, what are the answers to these 3 questions? First, is there a robot? Right, so I talked about what the robot is defined. That's kind of, we want to make sure that there's actually a robot that has engineering construct and an intelligence. At the end of the project, will a robot gain a new or significantly improved capability? Is it going to be able to do something new that it wasn't able to do before? Right, so that's kind of where the fundamental advancements in robotics, kind of how it's measured. And final, and this is the important one, because this is where I think I spend most of the time talking to the PIs to help them navigate what is responsive to the program or not. Is robot essential to the intellectual merit of the proposal? So if I were to remove the robot, would the innovation there, the publications, the presentation, the conferences, will they still hold up? If the answer is yes, it means it wasn't really an essential. It might have been a very neat, convenient, a demonstration example, but the advancement was not fundamental to robotics because I could have removed robotics and put, I don't know, cloud computing in there, right? And the same advancements will hold up. Then it's not an FRR proposal. Okay, so there's something inherent about the robotic system that you are studying that is integral to the advancements in the proposed work. Is this where you take over? Or is it still okay? Okay, I think this is. Oh yes, okay. So before submitting proposals, really encourage you to write a one-pager, the white paper, kind of the project summary, the same summary you write up before submitting project to NSF, and send it to robotics.nsf.gov. Remember I said our intent and what we've done within this program was created kind of this unified one program. So all you really need to do is send a one-pager to robotics.nsf.gov, make sure it has, clearly kind of articulates the overview, the intellectual merit, and the broader impacts. And it's a good idea to actually explicitly answer those 3 questions, right? Because that will actually help you make sure that you're framing your project in terms of those 3 questions. So now this is, I think, an important slide to really understand what happens to your proposal when it comes in. So all proposals arrive to us in one spreadsheet, so to say, right? So we get sometimes questions, well, which of the 5 divisions should I pick? Should I pick it here because it's more controls? Is it more, intelligence? It really, really does not matter. So all of them, don't even spend more than a second deciding which of the divisions, just the systems are set up at NSF, you have to pick a division, pick any one of the 5 divisions, it will end up in the same place, okay? So once we receive these proposals, and as I mentioned, the proposals accepted on, there's no deadlines, okay? So you can submit it anytime, you can submit one today, you can submit another one next week. Okay, so as proposals come in, as we get enough proposals on a kind of a specific topic, not too specific, but we get enough, then we might start putting together a panel. Okay, so we have panels year round. Again, we get a question, when should I submit it to make sure it's reviewed on the next panel? Well, we're not going to have a next panel until we get enough proposals, so just submit it whenever it's ready. Once the proposals come in, we pull them into the panels, and we intentionally make sure that the panels is a mix of computer science and engineering type of proposals. We actually have a good metrics of how we can measure, so we intentionally actually kind of bring this together. It will maybe have a general thematic, theme like locomotion, but it might be different where they're actually making the advancements. Every panel for FRR is co-run between engineering and computer science program director. So like Erin and I ran some panels together. So we really work as a team to invite reviewers. The reviewers we're inviting for each panel are intentionally a mix of computer science and engineering backgrounds, because we really want to bring those together into one room, have the discussions, and really have evaluating each proposal holistically from that perspective. Now, again, it doesn't mean that you have to advance both computer science and engineering every single proposal. But if you're claiming you're going to be advancing, let's say, computer science aspect of it, the intelligence, we want to make sure engineers look at it and it still makes sense from the embodiment, the engineering construct that you're using there. So your proposal most likely will be reviewed by a mix of computer science and engineers, regardless what your topic is. Once the panels are concluded, again, the entire working group, and remember we had a list of the program directors, the entire working group gets together and all 10 of us go through proposal one by one and discuss what we would like to fund from this program. So it's really a joint kind of decision. And then once those decisions are made, and you will actually see that every single award that FRR has made also gets co-funded between engineering and science. So we worked really hard over the past 2 years internally to eliminate all of those boundaries between computer science engineers, with the goal to do the same in the research community. I think this is what, and now Arian will pick it up.
Well, I don't have that mic, so I think I don't have the echo problem. But so Irina talked about proposals, and she focused most on unsolicited proposals. So these are the proposals that you can submit without any deadlines at any point in time. But FRR is also part of career proposals and research initiation. So now, for the first time, you can also submit, or for the second or third time now, through FRR, you can submit proposals that are entirely about robotics. So for unsolicited proposals, people like numbers. We cannot give any exact numbers, so we have some range of numbers to guide your thinking in terms of formulating the budgets. But the good news about FRR is it does not have any explicit limits. So that means that you need to put a budget that is properly justified in the context of the proposed work. So whatever that number ends up being, that's the number that you have in the proposal. And then the panelists are going to look at that number and the proposed work and see if it makes sense. And if the two make sense, then it is perfectly fine. So you should not artificially inflate your budgets, and you should not artificially deflate your budgets. You should ask exactly what is needed to carry out the proposed work, and that should be sufficient. So if you look at the words that FRR has made for the last 2 years, it turns out that the budgets are, roughly speaking, around 150K to 250K per year per proposal. And the duration is about 3 to 4 years, but FRR allows proposals up to 5 years. And you can also think, if you have an idea that is self-contained, is very well contained, and doesn't require 3 or 4 years, you can submit a proposal for 2 years as well. That would be allowed in FRR as well. If your budget goes more than the numbers that we have there for 250K per year, that's perfectly fine as well. You just need to properly justify the budget. So that's the message that you want to take away, that the budget should be properly justified. And we have robotics@nsf.gov. You can use that email address to also ask questions about budgets. If you have a rough idea of what the budget is going to be and the scope of the work, you can mention those in the email, and then we can have a discussion with you about it. The other important program is the career program, especially for starting investigators or those that have been at the university for a number of years. So the deadline for careers is July 27, 2022. So make sure that you submit your proposals before the deadline. And the FRR is participating in a career. So what will happen is that all career proposals that are about robotics that are submitted to FRR are going to be paneled together. And then we're going to group them according to their theme, and then they were going to get evaluated into different panels. Now for careers, there's a strict limit. The budget duration is 5 years, so you cannot change that. And the budget for FRR is between $500,000 and $600,000. That $600,000 is a stricter limit, is a strict limit. You can exceed that in some really rare cases if you are doing some new activities and so on in terms of outreach activities or educational activities, but that would require prior permission or permission from a program director. So for all practical purposes, keep that 600,000 as your upper limit. And the typical budget for a career proposal is a support for a graduate student, some travel, publications, some materials. Now, the important part about the PI for the career proposal, we do require at least 15 days per year support for PIs. So do make sure that you have that for yourself to show that you are actually committing time to the career proposal. Science and engineering also have this research initiation to help PIs that don't necessarily have the support from their university or from other federal agencies or from NSF. So for this year, for this coming year, the SIZE has the Research Initiation Initiative, or CRRI, or CRI, however you want to pronounce it. Well, it's supposed to make researchers happy. So the deadline is September 19th, 2022. I want to point out that there's a slight change from last year, and the CRRI requirements have been changing from year to year. So for this coming year, the requirements are more explicit, and it's limited only to those that are affiliated with or are not affiliated with R1 institutions, so R2 and beyond. It also allows for nonprofit, non-academic institutions. The budget is $170,000 for 2 years, and the purpose of CRRI is to enable researchers to jumpstart their career. And next, I think Irina is going to talk about ERI.
So as I mentioned, we're trying to minimize the distinction between computer scientists and engineers working on the robotics research. So that's why we have the engineering research initiation, which is kind of a counterpart to the CRRI. It's very similar deadline. The budget is slightly bigger, but the intent is the same, right? So this is a smaller kind of almost like seed initiation type of awards. It's also for non-R1 researchers from those institutions. There's another webinar coming up. Those webinars for all ERIs, it's not FRR specific. I'll just mention that there are 2 new revisions this year in the ERI. First is it now allows you to have a little bit of a senior personnel support. So if you need a little bit of mentorship, or maybe you need to go to someone else's lab to get access to something you wouldn't usually have, now that is allowed. And another thing that expanded is you can use larger sizable portion of this award towards equipment purchase. So we realize that in some of those schools they're under-resourced and you really want money to purchase robotic equipment. So now that is allowed in this year's revision.
Thank you. Thank you, Irina. And one point that I forgot about CRIs, you cannot submit CRIs and careers. So you have to choose one or the other, essentially. And now Jordan is going to talk about international partnerships and then other robotics-related programs.
The echo. So all things being equal, NSF typically prefers to spend taxpayer money in the US. And generally for unsolicited proposals and stuff, if you want to bring in an international partner, you have to jump through some hoops to explain why all things aren't equal. But an exception are these international partnership programs, because actually in these NSF side, NSF will provide money to the US partner, and typically the overseas research agency will provide it to the overseas partner. There's listed here some of the opportunities, some of the current opportunities. These change, new ones appear. Typically they're different because they reflect the needs of the overseas partner. Some of them are standalone grants, some of them are supplements to existing grants. So basically, I would say if you're interested in working with a collaborator in a particular country, you can go to the OISE, the Office of International Science and Engineering Programs, and you can look at what's available. these are available, Israel, the US, Ireland, Northern Ireland, the UK, the Czech Science Foundation, NSERC, Canada, and recently US, India funding opportunities. So again, some are for standalone proposals, some are for supplements, and all the rules are different. You just go to those. In this case, you have the DCLs or the solicitation, and you can see if what you're interested is supported. Okay. All right. So Irina and Arian talked a lot about FRR, and I'm going to talk a little about not FRR. So there's a lot more not FRR than there is FRR. So I'm not going to talk about all these things. I'll just say this may not be obvious outside of NSF, but intellectual merit is always evaluated in the context of the program and the context of the mission of the program. And so the mission of the and by the way, this is all of the Robotics at NSF page. So everything you're going to see is available from that page. So as Irina Arian explained, intellectual merit in FRR is about building better robots that do things that robots never did before in some context. And so if you're building a robot that does something that no robot has ever done before, FRR is a good place for you. But maybe you have doubts, or maybe the robot, as Irina explained, isn't essential to the project, or maybe you just feel like you got a better selling pitch, you got a better elevator pitch with a slightly different intellectual merit, right? Because, okay, I'm not sure if everyone agrees, but I'll say, we don't think that, there's a ground truth that represents exactly what your proposal's about. I think we all recognize that you can write the same proposal, or you can write the same ideas in different ways. That's up to you. And so ultimately, if you think there's a better way to sell your idea, you should pick the one you want to sell. So let me just talk about a couple of other ways you can sell your idea. So I guess I should also say that FRR arose in part because robotics research was spread over a huge range of programs at NSF, and it was kind of hard program officers kind of get frustrated because the same proposal might show up in different places, and it just wasn't clear where robotics should go. It could go in a lot of different places. And so now it should, if it's robotics in the sense that Irina and Arian defined, it should go to FRR. But the places where robotics used to go are kind of still like to see high quality research. If it's demonstrated in robotics, that's fine. So RI, the robust intelligence, so as Irina said, the FRR program looks for intelligence embodied in an engineering construct. If you really just want to talk about the intelligence part and you don't care about the engineered construct, then RI is a good choice. If you are looking at interactions between robots and people, and you're really not necessarily building better robots, but you're trying to understand that interaction, then HCC is a good choice. The CCRI program, not to be confused with the CRII program, although they may be homonyms, they're pronounced the same way, I don't know. So if you're familiar with MRI, the Major Research Instrumentation Program, you could think of this as in a case where you want to build infrastructure and your proposal is going to be mostly about building infrastructure for computing, but not so much about the research project itself. This would be an appropriate program, CCRI, I'm sorry. Smart and Connected Health. So these are programs where the intellectual merit is about improving health, is about transforming health with computation and connectivity. And so if there's a robot in it, but the robot isn't essential or the robot isn't the center of the intellectual merit, Smart and Connected Health. If you are, if you're interested in building better rehabilitation systems, if rehabilitating a patient is your focus and not necessarily the robots that's doing the rehabilitation, then DARE cyber physical systems. So this one's a little tricky, but basically, because robots are cyber physical systems, but so, and I should say that these little blurbs that are just copied from the Robotics at NSF webpage come from the program directors themselves. So the CPS program officers provided us with this description, and what they told us for CPS is the intellectual merit in a CPS proposal should be generalizable to cyber physical systems more generally. If you're demonstrating on a robot, that's fine, but your proposal should make clear what this means for a more general cyber physical system. For DCSD, it's similar. You could think about it as RI, but for control instead of for AI or ML. Or you could think about DCSD would also support things like the mechanical, like novel, ideas in mechanical computation or something, and morphological computation. My machine to motor nexus is about the interaction between technology, between smart machines and people, and not so much about the smart machines. And then future work at Human Technology Frontier, it's a kind of a complicated program, but basically it does consider robotics, automation in general, robotics and AI, but it has to be, if you're looking at how robotics will transform work, will change an occupation in the future, then future work would be a good choice. All right. That's it. So good. Thank you.
Just one more last thing before we go to questions and answers. All these slides are available on Robotics at NSF website. You can find all the slides, and you can even find the recording of a webinar that we held on June 2nd that is very much in content similar to the presentation that we gave there, that we are giving here today. And there are a bunch of questions that people asked when we gave that webinar, so you might find those questions also informative. So now we are open for questions.
Okay. So I appreciate the initiative to bring these there's so many programs and to unify them. I want to raise a concern that is from my experience, which is that there's fairly different communities in terms of the SICE community and engineering. And so my experience has been, over the years, I've submitted to engineering, but always received very different reviews. That engineering has, in a sense, it's very hard to put your finger on exactly what I'm trying to get at here, because I think there is some overlap. But in some sense, engineering emphasizes controls, and in a sense, it's this difference between cyber physical systems, which came out of engineering, is still there, but hasn't. It appears in conferences like CDC and others, whereas this conference and ICRA to some degree and others, there's a community of roboticists that largely have settled into SICE as their natural home. So then when the reviews and the panels, I look around and I see people that I know or I'm familiar with their work, et cetera. But when I connect with engineering, it's a very different group, and I often don't even know them. Now, what you're proposing is going to put them, I was hoping you would say is we'll put you on a panel just with one or the other, but they'll all go through the same gate. But what I heard just now is that you're actually going to have these panels be mixed. So what I worry about, and I hope it's not true, but I just want to say, I'm curious I guess my question is, to what degree, based on the experience you have so far of mixing these panels, do they reach consensus? Is there a sense of, can you tell us some of the things that you've learned and would help us, maybe some great examples of proposals that were successful under that? Because I think many of us, and I think my first reaction is, now I'm afraid because my proposal is going to be reviewed by this other community, and all it takes is one or two people in that room, as I know, to shoot it down. So I'm curious how we can avoid that and what your advice is.
I feel that engineering, the honor of engineering should be, anyway, so Ken, so first of all, it's not really a proposal. we've been doing this now for 2 years. And if you want to point to successes, I would say you can look at what's been funded under this program. But so what you describe is exactly the problem that we feel we have, if not solved, at least mitigated, which is because in the past, when a robotics proposal came in, you had to ask, where should it go? Should it go to RI? Should it go to DCSD? And how do you make that decision? Well, is it about machine learning? It should go to RI. Is it about control systems? It should go to DCSD in engineering. And it wouldn't be with only other robotics proposals. It would be with other controls proposals or other ML proposals. And so exactly what you describe is what happens. And if you accidentally got shunted into the wrong panel because program officers make mistakes, you would stand out and you wouldn't have much of a chance. So there are no control systems panels. There are no ML panels. There are only robotics panels. As Irina described, those draw on a mix of computers. So we actually have some stats. We see how many proposals have been previously submitted by this PI, say, to SciSce, and how many to engineering, and every panel balances. So you see the little line, every panel balances to the best of our ability, like SciSce, what would have been SciSce community PIs and engineering community PIs. I mean, so when you say roboticists naturally found a home in SciSce, I would say roboticists unnaturally found a home in SciSce, and that was a problem. And so this is our attempt to address the problem, and hopefully it makes things better and more transparent, and it makes it much less likely that you're going to end up in the wrong place, because there's only one place to end up. And if there's a control systems person who says, control systems, then there's someone, maybe you, to say, shut up, this is great. And there's a SciSce program officer and an engineering program officer listening to all this. And hopefully, the best ideas win, no matter where they come from. And now,
let me jump in on that for a second. So it's actually one of the fears that I had when I first joined NSF and this program was being created, that, okay, what's going to happen to those proposals from SciSce that really don't touch upon any of the engineering things. So my own research is in planning. So I was thinking, okay, what happens to planning proposals in these panels, because they don't talk so much about controls or the other aspects that arise in planning. But I have to say that in 2 years, I am really excited about this program, and I have not seen any issues. And I would encourage all the people that submit to WAFR, the research that you do that gets published in WAFR, make for great proposals in this, and they're going to be treated very fairly in the panels that we have run. The panels, from my experience, we've had a mixture of both engineering and SciSce experts, but the panels have worked out beautifully. And also remember that there's a large number of program directors from both SciSce and engineering that manage these programs, and over the years we have learned how to balance those. I would encourage everyone not to have that fear, but to go ahead and submit your best ideas without thinking, how is this going to be reviewed by an engineer, or how is this going to be reviewed by a SciSce person? If you write the proposals that way, it's going to be problematic. But if you write the proposals the way you'd like to write the proposal, it's going to show up in the panel, and excitement is going to build around that proposal from both SciSce experts and engineering experts. Now, the other thing that is happening is that FRR is in the third year of its iteration now. So those distinctions between SciSce and engineering are disappearing a little bit here and there, especially in the culture of how the panels are run and how the proposals are presented. So this dichotomy that we have had, or looking at past history, in 2 or 3 years is going to become irrelevant, because most of people are going to submit to FRR. So it's hard to tell. Like, look at the proposals that are there. Don't look, try to figure out, are they SciSce or engineering? And it's getting harder and harder these days. Yeah.
And I guess I'll add 2 points. One, I want to, something Jordan kind of mentioned, but all of you should volunteer to be reviewers. So reviewing for a program is the best way to see what happens and impact what happens in the process. So all of you can email robotics@nsf.gov, and a few keywords of your expertise, your CV, and say, I would like to be added to the pool of potential reviewers. So that's definitely something I wanted to bring in. And I think just one more point to drive home the same message with my colleagues. Remember, as I said, the advancement does not happen to occur, to take in both cases, like engineering and intelligence. So if you're claiming you're advancing control strategy for a robotic system, yes, there's going to be a control person evaluating whether you're doing that or not. But if you're saying I'm advancing something else, path planning aspect, nobody's going to be, checking in. Are you also doing that? Because that's not what you're claiming your contribution of your proposal will be.
I wanna argue with Irina just a little bit. And I want to say the whole point of defining intellectual merit to be in terms of the robot itself and the abilities of the robot is to take this argument off the table. So if you are actually arguing that you're making a better control system that's going to help robotics, you should not be submitting to FRR. And if your point is you're making a better machine learning algorithm that will also help robotics, you should not be submitting to FRR. You should be going to those core programs. You should phrase your FRR proposal in terms of what the robot can do that robots couldn't do before. And if you phrase it that way, it doesn't matter how you're doing it. It's evaluated on what new robotics you're bringing into the world. And that's the whole, that was actually intended, that definition of intellectual merit. It was all, we try to bypass all of these arguments in that way. And so far, so good, I think. But,
Jordan is right. And yes, we do have recorders. He was right.
Thanks. So, hi. So thanks so much for coming and obviously for service. I have a bunch of just like programmatic questions, not so much philosophical, right? So 3 questions. One is kind of, maybe I missed it because I got in a little bit late, but what is the overall budget? The second one is, given that it's a kind of a rolling panels, what happens if kind of you've funded a bunch of things? And I mean, is it good to submit at the beginning of the fiscal year? I mean, I know these are kind of silly questions, but I think it's, and the third one is, in terms of the career, I'm not going to apply for a career. I do have, no, but in terms of kind of advising our junior faculty and everything, SAIS has very outspokenly said career is for young faculty, right? So like first, second, third year, or in the recent, that's what the message that I've been getting in the last few years, in the last couple of years. Engineering, as far as I know, does not have that. It's more kind of towards the end of the tenure. So for FRR, what should I tell my colleagues? How should I advise them? So there was three questions.
I'll get the message that career proposals, Margaret, the SAIS AD, she has been mentioning that many times, that you should submit a career proposal when you are ready. There's no benefit in waiting a few more years to see what is going to happen afterwards. It actually may become problematic because you would have published a lot of the ideas that you had at the beginning. And so now how are you going to distinguish your career proposal based on the prior work? You have 20 papers on that idea, so it becomes a little bit harder. So as soon as you are ready, submit. Could be the first year, could be the second year, but don't delay just because you think you are going to get a better advantage by submitting later in life, so to speak. I don't think.
No. Yes, my question is that's the message from SAIS, but that's not the message from engineering.
That's the message for FRR. I'm talking about FRR.
Oh, I see.
Yeah.
Thank you. Sorry.
Yeah, but at least from my understanding of FRR and the advice that I've been giving PIs is that whenever you are ready, you should submit. There's no advantage in FRR in waiting a couple of years or a year. It's not that your proposal is going to get treated better just because you waited a couple of years. Now, if you are not ready, then it's going to show up in your proposal. But if you are ready, you should go ahead and submit. And you can look at the career proposals that FRR has awarded, and you can look at the history of employment of those PIs and see how long they've been employed by their institution to look at the numbers, if that is going to help.
Yeah, and I think it's a spectrum. If you see what we funded, it's really just, it's submit when they think they have a solid idea. So I don't think I've ever heard that engineering was like, oh, make sure you wait. It's just really what it takes.
Okay, no, it's not so much that you wait, but rather make your CV more impressive. So you're considered. So it's a philosophical kind of, is this supposed to support someone who does not have the CV yet, but has the trajectory versus someone who has more of the CV and the trajectory, of course. I mean, granted, if it's not ready, it's not ready. 100%, but the depth of the CV, whether there's a difference between the directorates, that I'm not clear on.
This is not policy. I think maybe it's just what panels, I don't think there's an answer. I think submit when ready and try not to overthink it. I think that's the best answer.
And then I think there were a couple other questions.
I was asking basically on the amount of money you have and how it's spread out around the year, whether kind of.
So let me answer about the year, because that one, so engineering went to no deadline 3 years or 4 years ago. So I've been answering the question a lot. I think in reality, it really does not matter, because if we really like your proposal and we run out of money, we'll just wait 2 more months until, like right now, we already ran out of money because just the fiscal year, like we need to push all our award recommendations in the next couple of weeks. So we'll just hold it until October, So I think if you have a specific, like I must start by September 1st, then you definitely want to submit, I would say maybe by March, just because usually it takes us 6 months to review and that's kind of our target. But in reality, and if you submit really bad proposal and we still have money left over, we're still not going to fund it. We'll put it towards some other proposals. So it's not. I think your question about the budget, it's harder to answer. I don't know if any of my colleagues have it, just because the way it's done is that from the 5 divisions that participate, every division is putting in whatever they want to put into the program. So I think the most solid numbers you can see, because you can see all the awards, you can see how much we spend in our first year. The second year, we're still working through the awards, but it's really hard to say like how much we're going to be next year. Like this year, for example, we requested way more budget than NSF received. Next year, we have no idea. Like the budgets are really kind of coming from Congress, right? And so it's just really hard for us to say like this is, I know in solicitations, you probably used to see that number, but even then, that number says subject to the availability of funds. So it's really not saying much. I think what I would say is that in the 2 years that we ran this program, every proposal that we were excited, that the working group excited, we're going to figure out how to fund it. So I think that's really kind of the focus of, I hope the takeaway for the PIs is just focus on writing the great proposals. Our job is to figure out internally how to make sure we fund everything that we want to fund.
Thank you.
Thanks. So I wanted to kind of invite you to comment on the word foundational that shows up in the title of this program. And I'm asking because I've seen that word now in 3 different contexts within the robotics world, right? Once in the old days where there would be categories of NRI projects that were classified as foundational or integrational. Once now in this title FRR, and in the name of this meeting, we have a sense of what the word foundational means when we talk about foundations of robotics. And I wonder if that word means the same thing in those 3 different places, or if there's a different sense. So how seriously should we take the word foundational in the title of the program, and what does that mean in that context?
So I'm just going to give an answer. We have the 3 questions that determine suitability for FRR. And if you go with those 3 questions, then you have met the criteria for submitting to FRR. And I wouldn't try to decode much more the meaning of foundational in FRR. So if you can answer those 3 questions in a strong manner, then you have answered the connection to FRR, and that's all that matters.
I don't, I'm not going to disagree. I mean, some of the things you point out were influence the naming. And I must say, I don't think FRR was our first choice for the name of the program. I think it was originally robotics core, like, and core, what does core mean? So NRI, the evolution from NRI to FRR, I mean, it was a thing, and definitely the foundational category. I mean, there was a time when FRR became the foundational category from NRI, and NRI was so the NSF funds research. It doesn't fund applications. It doesn't fund development. And so I think perhaps the word persists just to remind everybody that NSF funds new science, and we've defined it in the case of robotics. New science is robots that do new things, and that's pretty much what Arian said. Well, we took a long path historically, and I just recounted it for you, but we end up where Arian, which is just be innovative and stress the new robotic capabilities.
Actually, I had a question, and apologize if I missed this at the start. I was outside. With NRI, we could write a proposal that could be funded by USDA or through NASA. Should I write a proposal, let's say, with an agronomist any differently if I'm submitting to FRR? Should I be submitting proposals like that to FRR?
I'm sure you're going to disagree with me then. So I think, let me maybe try to rephrase the question a bit, or at least to answer. So I think what you're talking about is that part of NRI, we had the collaborations with federal agencies. So, and as Jordan mentioned in presentation, is we are working right now very actively with all of those agencies. We're talking with them to bring them on board to the FRR. So stay tuned for those updates. They will be coming up, and more details will come on that. But if you're thinking about, well, I want to be, so I guess there's a question, kind of depends. Are you planning to submit something very applied, which is what Jordan was talking about just now? If you're using, and if you're not enhancing robotic capability, you're just figuring out how to apply it now to picking tomatoes, but it's already existing robotic system, it's not NSF, right? But if you're saying, I am motivated by a robot now being able to pick tomatoes, and as part of that, I need to enhance and create this new robotic system, absolutely, it's FRR, right? You fundamentally advance in robotics, and it doesn't matter what the motivation, so we make distinction between motivation and application. What's the motivation for the need for this new robotic capability in the new robotic system? So I think maybe that's, hopefully answers your question.
Just to follow up on that, so let's say there is an agronomist on board as part of the team, and we are going to develop new capabilities for robots as part of the project, and then they are going to be used by the agronomist to do ag science. So for a proposal like that, sort of would FRR fund the ag science component?
So, I mean, if it's a validation, right? Like I talked about it that, okay, but so that would be part of it. I don't think I heard very well the second part of your question.
So if the second part was, if we develop this new capability as part of the project, and that's going to then be used by the agronomist to do a specific ag science component, they're going to study something that's agriculture specific using this new sort of tool algorithm that we've developed. Would FRR be a good venue for funding research like that?
Well, I would just say, don't forget that NSF proposals evaluate on intellectual merit and broader impact. If your broader impact is in agriculture, agronomy, then, I mean, those are equal. It's not like it gets hammered into us as program officers that broader impact is not the stepchild. It's not the secondary criteria. They are equal criteria. They're given equal weight. So I would just say, if you're going to write that proposal, make clear that the intellectual merit lies in the new capabilities of the robots. The broader impact lies in the application to the agriculture and show the merits of both cases. And then those are essential elements of a strong proposal.
Maybe Bill, excellent point. And I maybe build on is that, and you can budget for educational outreach activities and broader impact activities, right? So if you want then spend 3 months for graduate students to go and work with the farm and teach, local farming community how to use that, absolutely, that could be part of your budget, just like you would budget educational activities or going to K through 12, right? So I just want to close the loop on that.
Thank you.
Okay, so I have a couple of questions. The first one is again clarification on the point that keeps being brought up, which is that third point, which is if you remove the robot, is it still a valid proposal? And if it is, then it's not an FRR proposal. So that's a little tricky because let's say that I write a proposal where I have a new learning algorithm or a new control algorithm, and I demonstrate the new capability on a robot. If you remove the robot, there is still a new learning algorithm or control algorithm. That could be a CPS or RI proposal. If at the moment I put the robot there, then CPS and RI are going to be like, oh, this is an FRR proposal, new capability on the robot. So it's a little bit difficult knowing which program one should go for such a proposal.
So it depends, essentially. You could go to FRR with that kind of proposal, but if you're going to FRR with that kind of proposal, then you should emphasize the robotics aspects of that novel algorithm that you are proposing. So maybe if you develop a new camera system and robotics was just one of the applications, but you don't really do anything about it, then it may not be suitable for FRR. But if now you are using that camera and you are enhancing and you are making the robot do more things, then it would be suitable for FRR. So that's the idea of robotics being essential to the intellectual merit. Maybe let me give another example. I don't know if it will be good or bad, but from robust intelligence, something to distinguish what would be a good proposal for robust intelligence and something that would be good for FRR, especially in the context of this conference in here. So let's say you are doing path planning and so on. So it comes up in a different spectrum. You can develop a path planning algorithm that can be applied to robotics, but can be applied to other things. Now, if your contribution is about, let's say, path finding and everything there is as points, then that is unlikely to be suitable for foundational research in robotics. It's more suitable for robust intelligence because you are not taking advantage of the notion of the robot. The robot there is this very, very simplified model that is just a point that doesn't have any other capabilities. But now if you model a little bit more and you add more about what the robotic system looks like, maybe you model, let's say, the control aspects of it or some sensing capabilities or other things, so you make it more and more look like a physical system, then you are moving closer and closer towards foundational research in robotics. So the algorithm could stand on points, it could stand on physical robots. That's great. I think that would be suitable for FRR because you are meeting that criteria that you have robotics as an essential component to it. Now, what Irina said there is to remove robotics out of it is mostly in the context of ensuring that you are making a contribution to robotics, essentially, that your proposal does not fall apart if you take, that there is a contribution to robotics. So let's say, if you take robotics out of it and then whatever remains is so great that the robotics was just something like a convenient platform where you showcased your ideas, but those ideas could have been applied elsewhere, then maybe it's not suitable. Like if you're doing research in machine learning per se, then FRR is not your program. FRR is machine learning for robotics.
Can I? So I'm going to enhance it a little bit, and maybe this is like my engineering aspect of it, is to me, if there's something inherent about the robotic system that you're studying, and that is necessary for your algorithm to do well, right? So you are, for lack of a better word, hard coding some aspects of this robotic system into your innovative approach. Then you cannot remove the robot. Because if I remove the robot, the whole thing doesn't work, right? Like we are somehow capturing. But if, there's absolutely nothing, I can just easily swap one or the other, the algorithm will perform just as well. Go ahead.
So if that is the case, so say I can remove the robot, the proposal holds. I should submit it to RI and remove the robot part, because then they're going to complain that this has a robot in it and just talk about AI.
Can I throw in?
RI, so I think you should.
or let's say control algorithm, doesn't matter. Yeah, CBS.
I just want to differ from, I want to say this is not, I would advise you not to be categorical here. It's not, so for me, it's not a matter of either the proposal falls apart without the robot or the proposal stands without the robot. I think it's a matter of degree. It's a matter of the story that you want to tell in your proposal. If the robot is the most compelling application of your innovation by a lot, then I think FRR is still the right choice, even if you could make an argument for another application. You can imagine, so just imagine this in the panel. The panel is reading your proposal and they start arguing about whether it's FRR or not. And this is not hypothetical. This is what panels do. And they start arguing whether it should be in FRR or it should be in DCSD, and they'll start coming up with other applications. And they'll say, well, you could do this, you could do that. And if everything they come up with is clearly contrived and inferior, I mean, sure, we can make something up, but the robotics application is just the most natural, most powerful, most impactful application. FRR is the right place. So it's a matter of degree, and it's a matter of how you choose to tell the story, and it's a matter of the what ifs that a panel full of contrarians can come up with. And I think that's a better way maybe to think about it.
And quickly, you have those 3 questions. You can write those even in your proposal, not just in the email to us. You can have that as part of the text of the proposal so that when your proposal is discussed, they know the answers to those questions and they can argue with those questions, but at least you have provided some answers to those questions.
Okay. Maybe a related question about scope here is about the ongoing debate we have on RAS between robotics and automation. And I'm curious here how you're thinking about that. So would automation, how would that be thought of? So for example, if I'm looking at something that's controlling a system of conveyor belts that are smart conveyor belts, and they have sensing and they have actuation in the sense that the conveyor belts can tilt or something, but it's not a robot in the classic sense of a 3 or more joints. So this comes back to its intelligence embodied in an engineering construct. So that would be automation would fit that, you're saying?
I wouldn't say the conveyor belts are intelligent.
No, this would be where they would be intelligent. They'd be sensing and making decisions about how they move.
So then I would ask whether it's an engineering construct and how much of it is able to kind of what level of physical complexity it has to move within substantial alter in its working environment. Because if all it's doing is, I mean, it's something for you to argue within the proposal.
Okay.
I'd say there's no place else at NSF for you to send that proposal. And if the engineered aspects, essentially this is a question that a panel's going to debate. And if your proposal makes it easy for them to conclude that, yes, this system of conveyor belts senses and substantially alters its working environment, which I think is a makeable argument, and there's innovation in either the engineering or the algorithmic side or both, then I think FRR is fine.
Okay, thanks.
There are no automation. There's no foundational research and automation programs, so it's got to handle a very broad category of systems.
I have a more general question, I guess. I didn't want to ask it at the beginning because I wanted to allow the faculty to ask more relevant questions to FRR. I'm a postdoc, and a reason that I'm doing the postdoc is to get some experience in proposal writing, right? So I'm not so experienced in writing proposals, and sometimes those things take a lot of time, maybe 6 months, 8 months, 1 year, whatever, with my postdoc advisor. But at some point, I'm going to get a position in academia somewhere as a faculty member. And usually that happens if you think of the review process, usually that happens right at the time you get the position, you know, the NSF proposal may get accepted, but the funding doesn't come to you, it goes to your advisor. And we have discussed that with my advisor, Michael, there. It's a concern. And I was wondering if you can share your experience on that, if you can somehow transfer money, if you go to another university and so on.
I will say a few things. First of all, postdoc can be co-PI, just to start with. It's up to the institution. From NSF perspective, postdoc can be co-PI. So it's really up to the institution whether they want to take on the responsibilities. We've absolutely had the cases where part of their projects can be transferred after the fact to, I mean, we have it when two faculty submit a proposal together and it goes to one, you know, from one institution, and then one of the faculty moves to different institutions and part of the money will travel to them. So there's definitely mechanisms for doing that. So I wouldn't use that as a concern or hesitation to submit a proposal. They're different, and it's pretty standard procedures within NSF to either give a sub-award to a new institution, or actually probably that's what would happen to that, or the whole proposal would have to be transferred or something like that.
And that's true even if you're not a co-PI. So I know there are some institutions that don't allow, you know, they don't allow even research scientists to be co-PIs. It doesn't matter but you know, the PI has to agree. Like you're going to need the PI's help. As long as that's okay, then the NSF will be happy. We'll be fine.
And what part of the budget can we move to the new university, like the postdoc salary?
You could move the entire proposal if you wanted to.
Really?
You could just transfer the proposal. I mean, if that's what you want to do. I mean, NSF doesn't care. You could go, or you could just sub-award everything except you know, one summer month of vacation for the PI. And I mean, everything. Whatever, basically NSF will allow you to do anything from all to none.
Yeah, the institution has to agree because the award goes to the institution. So when we make the original award, we'll go to your advisor's institution and they need to be okay with transferring how they want to do it. But for NSF, we do them on a regular basis. It's really not a big deal.
All right, good to know. Thank you.
And I will just follow that up to say, all of that is correct. And I'm glad that they're telling you the same thing that I told you. So you see that I'm not trying to pull a fast one.
So you want us lunch afterwards, right? Is that what I'm hearing? We're on same page.
Right. Well, on the conference outside.
So I got a quick question about sort of, let's say you had a proposal that was not funded for NRI. How would you advise a PI to sort of move that NRI proposal after you made some edits to FR, given that NRI was more focused on the integration, right? Whereas then FRR, you really got to focus on sort of the foundations to the robotics. How would you sort of move that over?
So integration can also be supported by FRR. We also mentioned that in the slides that as long as you answer those three questions, then it would be appropriate for FRR. But for specific proposal, my suggestion would be that you send an email to robotics@nsf.gov. And if you had an NRI proposal that was submitted before, mention the proposal number and ask for some feedback from robotics@nsf.gov. And most of the time, what ends up being is that we schedule a Zoom conversation and we talk to the PIs and we can give you more specific feedback about FRR, what the criteria is and what kind of specific questions you have, and see how much we can help you to understand the scope of FRR and how you can better tailor your NRI proposal and revise it to make it more appropriate for FRR.
Yeah, and maybe just short answer is fundamental advancements in integration in robotics is foundational research in robotics, right? So that's
what I was looking for. Right. Thank you.
Any last minute question? I think Michael can check.
Any plans on funding large amounts of compute? Large amounts? Compute. So like now, if one needs to run large models, pre-training models, it's really difficult to.
So for that, I don't think FRR would be your best program for that one, but within NSF and especially within SAIS, there are some other programs that support computational needs and some cloud computing resources that you can apply. You can get credit either through the support that NSF provides or through some other places. So I would suggest that you look outside FRR for those kind of computing needs, because FRR is not going to be the program to support those.
So actually, just reminded me. There's we've been hearing about the America Competes Act that's winding its way through Congress. Have you been tracking that? Because apparently it's got a huge allocation for research and supporting closing the gap for artificial intelligence in with other countries like China. So are you looking at like you don't know about this? Do you know about this major initiative? It's billions of dollars.
So, I mean, I guess we're the very bottom of the food chain, right? We're program officers, and we'll be aware of this when. What's that?
You're above us.
No, that's not true. That isn't true. We feed you. I don't know. You eat us. I think you're above us. Anyway. When someone gives us our budget, we spend it. And if someone gives us an opportunity to argue why we deserve this money, we would make that argument. But honestly, that would happen when maybe the AD of engineering would ask. I mean, that's just not something, maybe Irina will do this in her new job, but mostly that's not what a program officer does.
But I guess I will say that NSF has Office for Public and Legislative Affairs. They are very well in tune with Congress and the Hill, and they work closely in a lot of those things. So I guess the reason I was making a face is like, where are you going with this? Like, what is the question is going to be, right? And so I think it's too early to say, oh yeah, that specific thing will allocate this much funds to this program, but they're absolutely very well aware what NSF is doing in this space. And I don't know specifics, but I'm pretty sure that there's a conversation going on. The conversation is just above our pay grade, but at some point, like, trust me, people within NSF are, on the lookout and really looking out for the research community and trying to figure out how to make sure that we're well represented there, but nothing specific yet.
So on that optimistic note, thank you for being here, for sharing your thoughts about the FRR program. We have. It's time for lunch. So lunch is ready outside. We'll be back in this room at 2 p.m.
Yeah, sure.
Okay, hello everyone. Welcome back from the lunch. This is session 8, so we have 3 more great papers on the algorithmic foundations of robotics. The first one by Hava Vigal, Jeffrey Ichnowski, Max Kao, and Ken Goldberg from Berkeley. It's titled CompST, Grasp Optimized Motion Planning for Suction Transport.
All right, can you hear me all right? All right, so it's my pleasure to present to you CompST, Grasp Optimized Motion Planning for Suction Transport. This is joint work with my co-lead Yahav Avigal, Max Kao, and Ken Goldberg. So we were really interested in tackling this problem of what's going on with the logistics industry. How do we get stuff moving faster? Obviously, we have a lot of problems with that right now. And so we started looking closely at what is the pipeline in these logistics facilities. And it usually starts off with saying, on the motion side, let's take an image, let's do some segmentation, let's computer grasp, and then let's do our pick and place motion. But in reality, all the front end of this is really fast now using deep learning methods. And we're dominating, the thing that dominates everything is the pick and place motions. So this is actually sort of the 4th in a series of grasp optimized motion planning work. And so I'm going to give a background on it because it builds into what we're presenting here. And a lot of this work builds off of really exceptional work in optimizing motion planning. We already saw some great work from Russ here. And we also extend a lot of dynamic manipulation, which we'll get into in a little bit. And so going forward, I'm just going to start sequentially going through the history of these grasp optimized motion planning backgrounds, starting off with the original grasp optimized motion planner. So when we start thinking about how do you pick and place something quickly, the first thing we usually start off with is a grasp plan that says, here are the 2 points at which you can close your parallel jaw grippers in order to robustly grasp and transport that object. And usually what happens is you get a motion plan for a top-down grasp that will transport that to somewhere else. What we realized was that that implies a degree of freedom that we could exploit to find faster motions. So we wanted to use this in order to speed up our pick and place transport by integrating it into a time optimizing motion planner. And so the end result is we get these fast motions, and I'll show you a little bit about how we get to that. So going back to the more like high level problem, we want to go from pick bin to place bin, or this could more be generally thought about as like any pick point to any place point, whether it's bin to bin, shelf to shelf, bin to shelf, or some combination. And we want these motions to be fast and smooth trajectories, subject to those grasp analysis constraints I just showed you, the obstacle avoidance, and joint limits. And high level, we want this to essentially be find a minimum time trajectory that satisfies all these constraints. And so putting it together in going a little bit deeper, we have these grasp analysis obstacle avoidance constraints, which are not convex, and other constraints that are convex. So to solve this problem, we discretize the trajectory, including velocities at the waypoints, and we create dynamic constraints as well. And sort of as typical, and as Russ talked about earlier, you have these application-specific objective of minimizing the sum of squared accelerations or velocities, or whatever you choose. We chose accelerations here, but I'm going to say, okay, how do we solve this first, and then how do we minimize the time on it? So going through in a little more detail again, we say, here are the joint constraints. These are all convex. The configurations have to be in their limits. The velocities have to be in their limits. The accelerations have to be in their limits. And we want these boundary constraints, which are also convex, that it must start and end at 0 velocity. And then between all the waypoints, we set up an MPC style constraint so that every single point moves along the trajectory explained by the dynamics of the system. And then to get to the non-convex constraints, I'm just going to give a high-level overview of how we do that. It definitely plays out through the rest of it. But the high-level idea here is that if you've got say an obstacle wall, a bend wall, a shelf wall that you want to avoid, you need to define a linearization of that obstacle into the convex optimization. So the way we do that is we say, here's a Jacobian, which is essentially saying with an infinitesimal change in the joint configuration, this is going to result in an infinitesimal change in the length that we're trying to keep out of that obstacle. And from that, we define our linearization of our constraint, put it into our optimization. We add all of our other non-convex optimizations similarly, and then we solve it using a sequential quadratic program solver, in this case, something based off of trajopt. So once we get that all solved, we get a trajectory that looks something like this, where on the top you see the configurations over time, the velocities over time, and the accelerations over time. And then to minimize for time, to find the minimum time trajectory or a minimum time trajectory, we just repeat the process solving for shrinking horizon until the SQP solver says we can't find a shorter solution, and we take the shortest solution it could find. And then we get these fast motions that can transport objects from pick to place points. Now we got some sound too. So the next part of the series is that we found from talking with people in industry and our own experiments that we really needed to include jerk into our optimization. We need to minimize it and limit it. And so we added that, and we thought, okay, the formulation is simple. We'll just add it and we'll be done with it. And then what we found happened was our compute time blew up to 28 seconds median compute time, which is hardly useful for fast pick and place motions in practice. And skipping through a whole bunch of details, what we came up with was that we could learn an efficient warm start for the SQP by learning in an offline process with this neural network and then running our problem through it to get a warm start that we could then solve with that same SQP that I showed you earlier. And that brought our compute time down to 80 milliseconds, a 300x improvement, making it practical for actual use. And this was the science robotics piece. So now getting to GOMP FIT, fast inertial transport, which we just presented earlier at ICRA. And here we wanted to solve the problem, well, is it possible that you could transport some objects too fast, like that wine glass? And this is related to the waiters problem and liquid transport. And just running our trajectories, we get things like this, where we're getting these really fast trajectories that ignore everything else that's going on and things fly everywhere. And so what we wanted to do is say, let's not have everything fly everywhere. And we introduced these inertial constraints that essentially try to keep the inertial vector, inertial forces aligned with what will keep the contents in the container. Now, the great thing here is that we already have the dynamic state at any point in time of our joints. So we could just compute through the recursive Newton-Euler formulation what is the acceleration at that end effector and formulate constraints around that. So we just said, let's figure out that acceleration and let's integrate that as a constraint on the tilt angle. And we end up with transports that now are fast, but don't spill anything. And we even applied that to transporting wine. And here it is in slow motion, where we don't spill a single drop. We did not replace that white sheet. And we got the challenge to do a German party trick of transporting upside down, and we tackled it. So that gets us to where we are here. So I showed this picture before, that this is the timeline that we're seeing in pick and place operations. But I don't know if you paid attention closely to the video, but actually what's dominating time right now is that gripper closing. It actually takes about a second for that gripper close, then does a sub-second transport, and then another second to open the gripper. So our time is now dominated by that gripper action. And so we started following what industry has moved towards, a lot towards, is really favoring suction grasping. But if we start moving suction grasp too fast, what happens is that suction breaks. And so we wanted to tackle this problem. And there's been actually some really good work on how do you get robust suction transports or suction grasps, and we leverage a lot of that, and we build on that. And high level, we wanted to say, let's add a constraint or a series of constraints that will keep the suction held. And so we thought about all the analytic models that people have developed, and we could say there's a friction, a suction, a moment, a component that we want to all keep below some threshold to keep it in grasp. But then there's lots of assumptions we can start to incorporate. And we had this other problem that we've realize when we look at the video in slow motion of what happens when suction breaks is that there's a deformation that happens between the before, when it's got a good suction graph, and when it starts lifting, and before it breaks. And while it's deforming, the suction grasp is still there. It's just if it keeps pulling, the suction grasp will break. And so we said, okay, we'll add the deformation constraint to this. And as I show, it's got to be a function of some history to capture that deformation over time. And we could model this, but of course, then once you start having deformation in your suction cup, you also have these issues where the suction cup is going to change its contact area or change its pressure, which would then feed back into all these other things and make a really complex model, which we might not be able to run efficiently online. So we said instead, could we learn a constraint? Can we come up with some function G that we say, we want this to be parameterized by a neural network, and just say, could it be below a threshold? Or keep it below a threshold. And I say probability of dropping here in quotes because we're just looking for a thresholdable value. We're not trying to model the actual probability. And so the question is, how do we get the training data for this? And one of the things that we realized is that maybe there's going to be arguments about this later, but we couldn't use video. Video would not work for us. Instead, we went with a cheaper alternative, which was actually really, really effective, of attaching a pressure sensor right into a custom-built suction gripper. And this gave us a really fast, really high quality signal of when suction breaks. So with that in place, we built our suction constraint self-supervised learning pipeline, where we do data collection, data augmentation, we train that function, and then we will use it online. So I'll show you how we trained it. So we had the robot lift up vertically a plate in suction grip over and over again with different motion profiles, but always vertically and just varying the angle at which it's holding the gripper to control for the direction of gravity, and also not to have it flying off everywhere. So we set up a motion profile, and we understood that if suction breaks at one point and you go faster than that, it's going to break at any point faster. And if suction is held with a certain profile, you can go slower than that and it will still be held. So we could use that to do a boundary search on these motion profiles, and then as a form of data augmentation, fill in the rest of that grid. So once we had that all together, we trained our neural network. We gave it a history of states from our accelerations at the endpoint. And that history of states, we determined it just by looking at the video and seeing how many frames of video required before, from the deforming of that suction cup starting to when the suction broke. And that's how we determined our history. So there could be other ways to do it. And then we just trained the neural network with the simple 1-0 success failure or failure success metric so we could threshold it. So to integrate that back into that whole GOMP optimization pipeline, we need to linearize this constraint so that we can have the SQP solver solve it or use it in its solving. So the great thing here is we just need a Jacobian, and the way we could get that Jacobian is just through the autograd of the neural network. Just the machinery that we used to train it was just available for us to get that Jacobian. So now we can linearize our constraint and put it back into our optimization pipeline. So with our optimization pipeline together, we have that part on the bottom where, as it's linearizing constraints and resolving these QPs over and over again, it's just querying the neural network for those constraints and Jacobians, and we get our solution, and we're able to transport these objects without dropping them out of suction. And so when we compared, we decided to compare it to sort of what I'm calling here a pessimistic and an optimistic analytic pipeline for that constraint. The pessimistic one always succeeds. The optimistic one almost always fails. And we compared it to our learned model. And the learned model comparison, we also say, here's what the history of one does. We need that history. If we don't have the history, it's going to drop all the time. And we also, importantly, compared motion time. And with even the high success rate that we're getting, we're still able to outperform by 16 to 58% over the baseline with the analytic models, even on unseen masses. So dirty laundry. So we assume that we know the object mass. We assume that comes in from somewhere else, a vision pipeline, perhaps. We assume local planar object surface. We assume multiple suction cups, but as I suggested, I believe that's pretty common in practice. And as a result, we get to ignore pendulum effects. So if you grabbed an object with a single suction cup and moved it quickly, it would sort of swing in place and you get these additional effects you need to control for. And so we also don't know how to generalize this to different suction cups. So you can see a whole bunch of different suction cups up there. Those we don't know how to generalize to yet, but it would be really nice if we could figure out a way to not have to retrain for every single suction cup. And with that, I'll say thank you and look forward to your questions.
Great, thanks. I suggested to Jeff that he could write a paper on wine manipulation. Definitely read that. So now we're switching to the second paper. The speaker is Ken Elimelech, the first author of the paper, together with Lydia Kavraki and Moshe Vardi. The title of the paper is Automatic Cross-Domain Task Plan Transfer by Caching Abstract Skills.
Thank you.
All right. Can you hear me? All right. Hello, everyone. My name is Ken Elimelech. I'm a postdoc, as Kostas has said, with Lydia Kavraki and Moshe Vardi at Rice University. I'm very happy to be here. Today, I'm going to present our paper about automatic plan transfer by caching abstract skills. And this is quite a theoretical work. So my goal here is just convince you that it all makes sense and it is potentially useful. So bear with me. So I'll start with a motivating example. So we can think of this robot arm that is able to manipulate objects in the environment. And first it is tasked with stacking 3 boxes in this pyramid configuration on the left. And after some calculation, it is managed to find a plan to perform this stacking. And afterwards, the same robot is tasked with now stacking the 3 cans on the other side of the table. So intuitively, for us humans, we can say that these 2 problems are similar, and therefore we expect the 2 solutions, the 2 plans, to also be similar. But unfortunately, we cannot just take the plan that we had before and simply reapply it, because we need to address the fact that it's different objects. We need to change the location to the other side of the table. So there are adaptations that needs to be made. Is this any better? All right. Okay. Should I repeat what I said, or is it good? All right. So what I was saying is that the 2 problems are similar, but we cannot take the plan and reapply it as it is. So the question that we're concerned with is how we can take knowledge from past successful solutions of tasks and somehow automatically adapt it so we can solve efficiently new tasks. So I will just suggest a few very simple definitions just to make sure that we're all synchronized about the terminology that we use here. So a planning domain is comprised of a state space, an action space, and deterministic discrete transitions that specify how to move between states. The state space and the action space can be continuous, but the transitions are discrete. A plan in this case would be just a sequence of actions. A task would be some objective that we want to satisfy by executing this plan of actions. And for this work, we can just assume that every task is specified in a different domain. And the task planning problem in this case would be given a planning domain, we have an initial state and a task. We want to find a plan to satisfy this task, of course. So given these definitions, we can maybe formulate the goal that we set beforehand. So given a plan that is a sequence of actions that solve a certain task that we know, a task for planning problem P in domain D, how we can use it to find a new plan that solves a similar task P prime in domain D prime. So maybe a standard approach to that would be to try to find or learn some transfer between the sequence of actions to the new sequence of actions that solve the second problem. But this actually has many drawbacks. that I will mention a few. First of all, mapping between different action sets is not trivial. So we can think of a robot that can pick and place objects and a robot that can push objects. How am I supposed to transfer between these two action spaces? So this implies that I can only transfer between robots that have very similar capabilities. It's also quite fragile. So if I transfer a plan and then one of the actions turn out to be infeasible, then the entire plan is invalidated and I need to find a new solution. And also it's unclear how to automate it because I need to perform infer this transfer for every new domain. So instead of doing that, instead of just looking at the plan, we suggest to examine the entire execution of the plan in the original domain. So in this case, the execution is the sequence of states. So we have the initial state and then an action and then the new state and then an action and so on. So this is visualized here in this figure. So the circles are the states. And we say that instead of trying to transfer the actions, we can try to transfer the state. So we take this sequence of state, we call it a roadmap, and then we transfer this sequence of state to the destination domain. And after transferring it, we can, in the destination domain, find the sequence of actions to follow this roadmap. So therefore, we can perform transfer even between robots that have different actions because the actions are recovered after the transfer. And this is also more flexible. So let's say that we transfer the roadmap and one of the states is invalid for some reason, we can just skip it and we still have a roadmap that we can follow, right? And we can also very intuitively decompose or compose roadmap to build skills or break them down. So now that we establish what is this knowledge that we want to transfer between domains, this roadmaps, we want to explain how to do this transfer automatically. So we introduced the notion of abstraction keys. And abstraction keys, we have public keys and private keys. Public keys are just pairs of functions, inverse function. One of them is a projection function, takes a state and returns an abstract state. And the reconstruction is just the inverse, takes the abstract state and returns the original state. So these two functions are parametric, and this parameter is chosen for the specific plan. And we said that this is a private key of the plan or of the state. And maybe some intuition why we use public and private. We can think of encryption keys. So if we encrypt data and we want to retrieve it, we need both the public and private key. So here it's the same thing. If I abstracted the state and I want to retrieve it, I need both the public and private key. So maybe we can see a little demonstration here. So this is a certain abstraction key that we provide in the paper. We call it symbol stripping. So what it does, it takes a state, it has a symbol. This can be a color symbol. So the projection will just remove the color. We'll have a colorless state. And then with the reconstruction, we can just put the color back. So why we care for abstraction keys? Because they provide a very systematic and automatable way to perform state transformation. So what we would do, okay, okay, now I hear myself very loudly.
If you don't like that one, we have another.
Okay, I'll just hold it afar. Okay, technical issues. At least everyone is awake, I hope, because the entertainment. So rolling back, we want to transfer between a state that has the color blue to a state that has the color red. So what we do is we project it, remove the color, and then put in another color. So this way we can use the abstraction keys to automatically change. And if we think of the example that we had in the beginning, we had boxes and cans, so I can remove the reference to box and replace it with a reference to can. And this is how I can transfer the plan. And different abstraction keys allow us to perform different transformations. So this is just one transformation, a transformation of symbols, but we can have different abstraction keys. Once we have this abstraction key, we can just apply this idea on the entire roadmap. So we have a roadmap of a plan. We project all the states. We have this abstract roadmap, and then we reconstruct it in the destination domain. This is how we can take a plan and transfer it to a new domain. And maybe we can see another example here of another abstraction key. This is what we call a tangent. So we have a sequence of states, and we see that the first variable x repeats in all the states, so we can simply remove it. We have a substate, and then this is an abstraction, and then we can replace it with another information. So as we just explained, the transfer is performed in two stages. So we say that we can and should perform this transfer in two separate stages. So the first stage happens once I solve a task. I immediately take the solution and I project it to the abstract domain, and I cache this abstract roadmap as an abstract skill. And this way I can form a library of this abstract skills. And later on, when I have a new task, I can just take one of the skills and reconstruct it, and then I can use it to solve the task, the new task. But there is a missing link, because we need to, not every skill is obviously applicable to every new task. So we also need to determine if the skill is applicable. So what we actually ask here is, can I find some private key for reconstruction that if I reconstruct the abstract roadmap, it will match the new task. So here we can think of a simple task that is just navigating from a start to a goal state. So on the bottom, we see the start and goal state, and on the top, we see the two ends of the roadmap. And we ask, can we take the two ends of the roadmap and somehow reconstruct both of them to match the two ends of the start and goal? So in this case, we can see that it is applicable, the skill, because we can just add pink, and pink will just add, will make both of these abstract states match the start and goal state. Here we can see a case where it's inapplicable, because no matter what color we add, we will not be able to get this yellow, right? So this is inapplicable. And another case that is inapplicable is if we have, we see each of these two states independently can be reconstructed into the start and goal state, but not using the same key. So in this case, we cannot choose a key that will reconstruct the entire roadmap into this task. So it's inapplicable. But even if we don't quite understand it, we don't need to reason about this explicitly, because we can just formulate it as a constraint satisfaction problem using the abstraction key, and we can easily solve it. So we can easily and automatically determine if a skill is applicable. We don't need any human to intervene and choose the skill. And it means that the idea of abstraction key allows us to automate both how to perform the transfer and also to which task we can perform this transfer. So we can automate the entire pipeline. And maybe a higher level of what we're actually doing here. So instead of doing this naive transfer between domains, so every square here is a domain, we don't need explicit coupling between domains. All the skills go through a centralized central domain, and then we can transfer also to new unseen domains, because we don't need to have explicit transfer functions. And we can have maintain the unified skill library and increase the entire scalability of the transfer problem. So just a recap of all the contributions that we suggested in this work. So first novelty contribution is that the skills are represented as roadmaps and not as actions, not as a sequence of actions. That skills can be transferred through an abstract domain, and we can also cache them there. That the transfer can be done automatically using the abstraction keys. And overall, what we achieve is that we can learn generalizable skills using a single demonstration. So we don't need multiple demonstration to achieve generalization. And this is the dirty laundry. So these are the challenges with this work and how we plan to address them in future work. So first of all, this is quite theoretical idea. So we want to have more validation and experiments of this concept. We, of course, cannot use this approach to transfer plans between just arbitrary domains. We need some type of symmetry, but we can somehow mitigate it by allowing skill composition and decomposition, so we don't need to have very harsh symmetry. Developing abstraction keys is also not quite trivial. Like the ones that we presented here are the ones that are handcrafted, but we can potentially learn such abstraction keys. So if we have a complex state that is an image, we can try to use maybe a neural network to learn a projection of this image to an abstract domain, and this will be an abstraction key. So we can also automate this Abstraction process, choosing the best abstraction key is also not trivial. So we have some ideas of how to address that. And maybe the most prominent future work that we want to do here is to extend this idea to motion planning, and by such to task and motion planning. And because we just talk about states and not actions, then this would be very trivial to do. And I added the final bullet just because I had some discussions here with people that this skill-based representation can allow us to have dynamic abstractions based on the capabilities of the robot. So this would be interesting. And with that, I will conclude. Thank you very much.
Thank you. Great, thank you, Ken. And the next talk, I think we got a little bit of a preview during the first plenary. It's by Alexander Hamis, Honkai Tai, Peter Werner, Anand Zhang, and Ras Tedrick from MIT and the Toyota Research Institute, finding and optimizing certified collision-free regions in configuration space for robot manipulators.
Great. Can everyone hear me? All right, so today I'm going to be following up a little bit on Russ's plenary. A lot of people asked the question during that, how do you even find these regions for the graphic convex test approach? And while this was the original motivating work for this, I want to point out that this work is going to be slightly more applicable to even people who like to still use randomized motion planning. So there we go. I don't think I need to motivate anyone about the problem with planning configuration space. It's really natural for specifying almost all the constraints we like. The really challenging one is don't run into things. And so here what I'm showing you is a 2 degree of freedom robot on the right, and the configuration space is just the angle of the joints. And here what we have is, even though the constraint of not running into anything is actually really nasty in the configuration space where we do all of our planning. It's not convex, and in fact, it's APX hard to even get these shapes. So getting a general mathematical description of these shapes is not really feasible. What we're going to argue for is we don't need to describe these shapes. We just need some representation of the free space that we can actually plan with. So how do we do that right now? So I'd say the easiest way to get a good description of free space is based off randomized motion planning. So these are your PRMs, your RRTs. And the idea here is, one of the reasons that these are so attractive is they work in any space that you want, any mathematical space whatsoever, and in any dimension. As long as you can sample, you can run these. And they provide these probabilistic certificates of non-collision based on how finely you can discretize the space. And that's really attractive because you can more or less be sure that you're not going to collide, probably. The problem is that scaling to high dimensions or in really safety critical applications, this might not be enough. So what kind of deterministic or rigorous certificates can we do? So Russ brought up this algorithm that came out of our lab a few years ago called IRIS, which essentially is able to find these rigorous certificates. And it does this by solving a series of convex optimization programs. And so it's able to generate these rigorous certificates and these regions where you're not colliding with anything in a very scalable, tractable manner. And the nice thing about these also is that they also work in arbitrary mathematical spaces and in arbitrary dimensions. On the other hand, it requires all the obstacles to be convex. Very realistic for task space when you're operating in 3D and you're trying not to run into stuff. But as you saw on the first slide, very unrealistic for configuration space. And so this algorithm isn't quite enough. So where are we going with this? What we're going to do is we're going to provide rigorous certificates of non-collisions for entire regions, these polytopic regions in this configuration space. We're going to tell you how to fill that space as well. Our technique is also going to apply in arbitrary dimensions because that's not a property we want to do away with. And importantly, we are never going to explicitly require the construction of C-space obstacles because that is way too hard. So let's take a look at the intuition here. How do I check whether in task space that body A and body B are not colliding? Well, what I need to do is, it's safe to assume that both of these bodies are convex, and I can check this I can check that they're not colliding by finding the separating hyperplane between them. This I can write down as a convex optimization program. Find the parameters of my hyperplane, subject to everything, all of the points in body A being a positive margin from my plane, and all of the points in body B being a negative distance from my plane. And notice here that this is configuration specific. So if you give me a configuration Q0 of my robot, this can check whether I'm in collision or not. I'm going to write these as positivity constraints because it's going to be very suggestive if you're familiar with the technique that we use in this paper. On the other hand, notice that this hyperplane is great for this current configuration. It's not so good for this one. So I'm going to have to rerun this program. And so I need to be able to actually look for a parametric hyperplane. I need to find a function A and a function B such that for all of the points in this region P, I can certify these two positivity conditions. So these types of problems are known as functional implication problems. They're extremely difficult in general. On the other hand, if we restrict our hyperplanes A and B to be polynomial functions of Q, and I can write down the two functions, I don't think my pointer's working, these two functions as polynomials as well, we can actually solve and search for these functions using convex optimization, using a technique known as sums of squares programming. Now, if I have a serial manipulator like my KUKA in this example, my position of for example, the body A is actually going to be a trigonometric function. And so I actually have to write my program like this, where I'm going to introduce this one-to-one change of variables, where I'm going to work with this in this new space S, where S is just equal to tangent of Q divided by 2. This is just so that I can write everything as polynomials and actually apply the technique that I like to do. But once you have transcribed your problem like this, you can actually just solve this as one big optimization problem. I'm going to find one hyperplane between every single pair of bodies in the scene on the right. And then I'm going to run this certification program that's going to prove that those hyperplanes are positive for every configuration in this yellow region on the left. I want to point out here, I'm only highlighting or showing you the hyperplane that is separating the two end effectors, because it'd get very cluttered if I showed you all, I think, 90 hyperplanes in this one scene. But there is, in fact, a proof that every single body on the right is not colliding for every region here. So that's great if you can propose me a region in C-space, but it's not so good. But I haven't told you how to actually find those regions, because that's hard. If I can't even visualize this, how do I even get that region? Well, what you can do is you can start by proposing a very, very small region and then think about trying to grow that region. So how do we do that? What we're going to do is we're going to borrow a key idea from the original IRIS paper. And so we're going to measure how big our polytopes is by drawing an inscribed ellipse on the inside. And what we're going to do is try to push away from that inscribed ellipse so that I can actually grow. So the algorithm roughly goes like this. You give me a polytope, I check whether I can certify that as collision free. If no, shrink the polytope. If yes, then find me the maximum inscribed ellipse of that polytope. Our certificates typically have a little bit of wiggle room, and that allows us to write a small convex optimization program where I'm essentially going to try to push the faces of my polytope away from this current inscribed ellipse without violating the certificate computed on the previous step. With this new polytope, I just recertify, grow the next inscribed ellipse, and keep going until I grow to something that's satisfying. And I want to point out, every single step here is a convex optimization program. This step of growing is also convex, and it's much, much smaller and much, much faster. And so over time, just by running this algorithm, I start with something very, very small, and I can grow to cover my entire region. These alternations are, like I said, convex, and eventually they converge to something that you may or may not find satisfactory, and you just keep going until you cover your space. And so as a final result, once you've run this long enough, you can plan using more or less any technique you want. Here, I'm showing you a graph of convex sets approach, the trajectory that we found, but you could also grow an RRT and check that the entire RRT is collision-free by just checking that every pair of nodes is contained within one polytope. I'd also like to point out that there's one certificate per region. So sometimes on the right, you're going to see two hyperplanes show up at the same time. That's because my configuration is traversing two regions at the same time, so I'm doubly sure that I'm not in collision here. So let's talk about some of the practical considerations. These are optimization programs, and they can get pretty big pretty quickly. And so where are the complexities? First, if you want to describe really complicated regions of configuration space, you're going to need to describe very complicated convex bodies. And so you're going to need a lot of linear inequalities in your polytope. And your program is going to scale roughly linearly as in the description of the polytope you give me. If you want to run this on higher degrees of freedom, you're going to pay that cost quadratically. So the more joints you have in your robot, you're going to pay a quadratic price for that. And the more things that can run into it, since you need one hyperplane certifying that things aren't going to hit each other, then you're also going to pay a quadratic. You're also going to pay quadratically for that, but the quadratic scaling is a little better for that one. So can we run this on realistic examples? A lot of people, they hear sums of squares optimization and they're like, that's going to take a while. So actually, this scales extremely well. In this scene, we've got a 7 degree of freedom robot reaching into a shelf. There are about 99 things in this scene that can run together. And it's a 7 degree of freedom robot, like I said. It only takes 1 minute to certify that a polytope in this space contains no collision. So if you have a good initial guess about where you aren't running into each other, into yourself, then you can check that very quickly. If you want to run the alternations, well, 1 minute to check the growth, 8 seconds to grow the region, and so every minute you can be getting filling more and more space for around a given configuration. We're even able to scale this up to 12 degrees of freedom in extremely reasonable times. So here again, you have about 100 collision pairs. And let's see what it would take to certify a half radian box in all of the joints here. And I wanted a resolution of 7.3 millimeters. So in this, what I'm showing you is the two red bodies here are 7.3 millimeters apart. And this black line here is actually a hyperplane proving that they're not touching. And so this was the closest configuration we could find within this region that we're certifying where they're not running into each other. If you want to do this with sampling and take kind of uniformly grid your space, it'd take you 10 to the 20 samples to be able to certify something with this kind of resolution. And so if you did one sample per microsecond, it's 10 to the 9 days. And then you still wouldn't have a concrete, hard mathematical proof that they're not running into each other. On the other hand, our approach, 1 hour and 45 minutes. So if you have a good idea that these aren't going to run into each other, 1 hour and 45 minutes, you can have a proof that you can check at runtime that you're not going to collide. And if you want to run the alternations, it's going to take 4 minutes to grow the polytopes. And so that's, I'd say, not so bad for this high degree of freedom. And once you have run this admittedly expensive pre-computation, you can actually store these certificates extremely efficiently. It's just a few numbers of what the hyperplanes are. And so in kilobyte-sized files, you can have these. So challenges and limitations. I admit the alternations can be slow in high degree of freedom plants. And so seeding the alternations with large initial polytopes is very important. We give a couple of heuristics on how you could do this in the paper, and we're interested in exploring other ones. Also, admittedly, it does require very good knowledge of your environment. And so it's most applicable to fixed manipulators in relatively static environments, which is where we're kind of the problems that we're very interested in solving right now. Also, we generate our regions in this one-to-one transformation of the original configuration space, not the original configuration space. But we don't think this is too big of a deal. And it's also a gap we're trying to close. And finally, choosing where to kind of start the alternations in order to make sure that you get good, important regions is not trivial. And we're thinking about heuristics that might be able to help us do a better job of doing this automatically. So in conclusion, describing the free C space as a union polyhedra, that's extremely useful for any type of motion planning you want to do. And we demonstrate in our paper how you can do this, how you can obtain these kinds of decompositions using only convex optimization. Our method works in arbitrary dimensions and it scales very well. It makes the very realistic assumption, it relies only on the assumption that your obstacles are convex in task space. It never requires the explicit construction of the C-space obstacles, and it'll provide a rigorous certificate in both task and C-space, which can be checked at runtime. And finally, if you want to actually run this on your own systems, we have all this is available already and and we're happy to help you set it up. These, unlike the graphic convex set stuff, this is still only an experimental fork of Drake. We're trying to get through code review. And one last thing from, just to show that we really do believe and trust in this method. These are results from last night that Russ forwarded to me, where we're running the graphic convex sets machinery to do this very coordinated transfer motion between these two arms. And so the regions through which this task was actually done aren't certified yet using this machinery, but we really believe in this method, and we think that as like a whole pipeline, this is something that can be used for real tasks, and we trust it. Thank you.
So let's get all three speakers, and then now it's time for a Q&A session. So we have one question here, one question there. So we have microphones. How many microphones do we have?
Yeah.
Okay, let's start the first question.
This question for Alex. Great talk, Alex. I really like your work. So just a quick confirmation question. So for the facets of the polytopes, is that tuning parameter, or does your optimization figures that out? And yeah, that's my first question. Yeah.
So you do have to set the number of inequalities that you use in your polytope. And so that's why I brought up the description of the polytope, because sure, you could in theory describe more complicated shapes with 100 inequalities, but the certification program is going to make you pay for that in the long run. So it's better to use slightly less descriptive if you can get away with it.
Do you think of it as a challenge of like pre-specifying, for example, the number of versus number of hyperplanes and their orientation in high dimensional spaces, like 12D?
So our experience was that if you give like fairly regular polytopes and you just kind of perturb them from their regular orientation. So if you give like an actual box, then the alternation doesn't do a great job of finding like, it kind of terminates somewhat early. If you start with a box, but you perturb the angle a little bit, for some reason that helps it grow longer and faster.
Okay, thanks. I will check out your paper for more details.
Hi, so this is regarding the cross-domain task plan. So thanks for the talk. Yeah, yours was mainly on forming abstraction keys, right? So how do you think that it can scale for high dimensional state space? Because for high dimensional state space, finding abstraction keys won't be trivial, right? And the second thing is, are you familiar with bisimulation distance? That is one guaranteed abstraction way to find abstraction in sequential decision making.
Okay, so to answer the first question, actually the abstraction keys that we presented here, they are not dependent on the dimension of the state, right? Because what they do, for example, is either focusing on a subset of the state, or they can just change certain properties of the state. They can change certain symbols. There are other keys that I haven't shown here that can, for example, if I have a geometric state, then I can change the scaling, change the locations, and so on. So I don't see it as a challenge.
So if the number of states increase also, so then also the number of abstraction keys will be tractable, is what you're saying, is it?
So every abstraction key allows you to perform a certain transformation. So we see symbol change is certain transformation. In that case, it doesn't depend on the state, the dimension of the state. We can have different transformations that we want to perform, change, as I said, in geometric domains, change properties, change locations. You just take a state and you project it it shouldn't be dependent. It shouldn't be a challenge, the dimension of the state. And as I said, if we have a very high dimensional state like an image or a complex, we can potentially learn these projections from experience.
Thank you. Perhaps jump here. No?
Question to Alex. Obviously, you're concerned with covering the free space, but I think it will also be advantageous that there's minimum overlap between your polytopes for application purposes, for being economical. Have you thought how to do that?
So the more overlap the polytopes have, at least for the graph of convex test machinery, the more kind of flexibility the solver has. But that also kind of makes the problem harder for the graph of convex set solver itself. And so there is kind of a trade-off on how much they should overlap. Since this is a convex optimization procedure, you can add all sorts of constraints. So for example, in the alternations, you don't want the polytope to wander away from it originally started. And so we basically peg the polytope to some initial seed point. If you wanted the polytope to not penetrate one of your old ones, you could put in an artificially hard constraint that says, okay, you can grow, but no farther than this. And so it's going to force the polytope to grow in the other direction. And so there are a lot of tricks you can do with more and more constraints that would cost almost nothing to encourage growth in other directions.
The last trick that you propose is a bit maybe problematic because it will make it more difficult to cover space if you put those specs.
Yes. Minimal covering of even a space with polygonal holes in it, that's APX hard to approximate. So any sort of heuristic that you come up with, that there's always going to be some environment where it's going to be difficult to do. And we're not going to break that. But this is a pretty good heuristic for generating good covers, we think.
Hi, question to Alex. Thank you for the great talk. It is just a clarification related questions and apology if it is not relevant, but the region in which you're designing the polytops, or I think when the constraints weren't satisfied, it doesn't require it to be compact or bounded, but when you run this algorithm, maybe it requires it to be like bounded or compact. Is it related?
So the way we wrote the paper, we assumed that we had serial manipulators. And so typically those have joint limits. And so there is also the joint limit polytope that's constraining everything else. So at the very least, you'd have the joint limit keeping your domain compact.
Thank you so much.
Hey everyone, nice presentations. I enjoyed all of them. I actually have one question for each of the presenters. So for the first presenter, I want to know, how does your work apply or transfer to containers that have different weights and so forth in them, right? So if we think about suction, or even if we think about grasping in a sense, right? If this bottle was empty, it'll be fairly easy for me to grab the bottle and move at a very high acceleration without it slipping out of my hand. But if it was full, I can't apply that same acceleration, right? And so I think the profiles that you end up developing somewhere in your slides, won't they become invalid for different weights and of your containers?
So let me make sure I understand your question. I think it's a great question if I understand it right. Maybe it's a great question if I don't understand it right. But you're saying that the rate at which, or the torques that the robot can actually apply are going to be, slowing it down if it's got a heavier mass and payload, right?
Yeah, because at a heavier weight, you can't apply a very fast acceleration and still expect suction to work.
Right. Okay. So I guess there's kind of two answers for that. The first one is the actual suction part. We trained mass into the neural network. So mass is one of the parameters that you put in. You have to know a priori. And that becomes one of the constraints as to whether or not it's going to hold suction. And we also found that it did generalize to unseen masses. So we trained it on a series of masses, and then we tested it on mass in between those, and it seemed to generalize. The other question about, I think, is slowing it down based upon what torques can actually be applied. For those, we sort of simplify the problem by just saying these are the maximum accelerations that you can apply and making it a convex constraint, mostly in the interest of running it faster, or computing the solution faster. But we could, with the machinery that we've developed, make it much more complex, probably slow down the optimization and actually incorporate the recursive Newton-Euler all the way through the optimization.
My question for the second presenter is, can you provide any comments on how you can safeguard from information loss during the abstraction process, right? Because at some point when you abstract to a lower and lower dimensional state, you end up losing a lot of information. And so how does that play into transfer into another task?
So actually, because the abstraction key, the two functions, the projection and reconstruction, are inverse functions, it actually means that we have no loss of information. Because if I have a sequence, a roadmap that I use and I project it, if I use the same private key, I will reconstruct exactly the same roadmap that I have. Right, so I have no loss of information. What I do with this abstraction is I take information that I think is now relevant or can change and put it in this private key. And this I can change afterwards. So there's actually no loss of information. And this is one of the advantages of this symbolic approach to abstraction.
Let me give an opportunity to someone else and perhaps can come back.
Hi, I have a question for Alex. So the polytope growth process is that you start from a seed and then you start to grow it. Is there a resolution to it, or is it, so how close does it get to the obstacle region boundaries? Or is it like as more time you give it, it gets infinitely close to the boundary?
So if I understand correctly, you're asking how close could the region in principle get to the boundary? So that's it. Theoretically, it's up to the floating point precision of your computer. In practice, you might run into numerical issues in the alternations itself, the closer and closer you get to the boundary itself. So in practice, if you roughly know a good initial polytope, or you can say like this hyperplane is as close as I want to get, just leave it fixed and grow the other faces, that is probably what you want to do.
Let's check if there are more questions. So the mic. And your third question.
The third question is for the third presenter. For your experiments, are you assuming static or dynamic scenes?
We're assuming static scenes. So we're extensions to kind of new obstacles and things like that. As you can see, in 12 degrees of freedom, that's going to be hard to tackle in real time. But we're optimistic that as when you introduce a new obstacle into the scene, you can rapidly compute only on that obstacle and its intersection with the polytope representation you currently have, rather than starting from scratch.
Okay, and I guess a follow-up to that is, let's say you pick and place something, right? Your C-space ends up changing. So do you have to verify every new scene that you encounter?
I actually asked Russ this originally when I started working on this, and his claim was that a lot of times people have kind of two representations for the robot, one without it gripping an object, one with gripping an object. Otherwise, you could always, since it's per collision body, you could run the same optimization program, but only on the change of the end effector, which would speed things up a lot. You wouldn't have to resolve for all of the other planes. And if you wanted to modify, you could shrink the polytope. The old certificates are still valid on all the other things, and you just have to shrink the polytope the little bit you need for the new object you've picked up.
And one of the papers of Jean-Paul Lamont is about building one roadmap across transfer and transit paths with Nick Simeon, and it helps with this case.
Can you hear me now? Yeah. So I have a question for Jeff. I really like learning the constraint. I thought that was very cool. And my question was really on the dirty laundry. Like how generalizable is that learning with other suction
Sorry,
cups?
it's so hard to hear.
Yeah. So my question was really on your dirty laundry slide with how generalizable is your suction cups. But since you had that there, I have another question to ask. Like how robust is this learning constraint when you use a similar suction cup, but from another company, say, which may have slightly different characteristics of the elastomer material? And how does it work like with, you mentioned that it does really good job with the mass, but it's not only the mass, you may have some dirt in the objects that you're picking. And I was, some comments on how robust is this learning constraint thing that you applied there?
So great questions. The first one I don't know the answer to, so that's why I like it, because we want to figure that out. How to generalize to different suction cups, like what are the parameters of that? How deformable is it? How, you can measure some things like the surface area, and maybe we can incorporate that into the optimization. But if the manufacturer is using a different material, then how do we incorporate the constraints from that into our learning process? So I think these are really open, interesting questions. And then your next question, sorry,
it was about like
dust.
Yes.
Oh, so the thought that we've had on that was that we would train it into the model. That's something if we had right now we've trained mass into the system, but we could also train and maybe extend the training process longer to handle more surface contacts or handle just sort of the worst case scenario. Those are things that we could potentially incorporate in.
All right, thank you.
So I had a question about the polytopes. So you create this union of the polytopes, right? So the question I have is, what properties or what criteria do you have to determine this union? And then are there any properties about the C space you need to preserve when you're creating this union?
So in terms of properties of the C space, we don't really, we assume almost nothing about the C space, just that it's coming from a multi-body plant that has only algebraic joints. So basically you can't have screw joints in your system, but anything else we can probably handle in the machinery. I'm not sure I understand the question about the union of the polytopes.
Basically, based on what I'm reading, you do a union of the polytopes, right? So you create your polytopes and then you create a union of it for the randomized motion planning. So
You treat every single polytope independently. If you're going to use the graph of convex sets approach, you would your nodes would be the polytopes themselves, and the edges would be where the polytopes overlap. If you're going to run a randomized motion plan or grow a PRM in it, what you could do is whenever you want to connect two nodes, because they're convex, if you want to check that the entire edge between those nodes is also collision free, as long as the two nodes are in the same polytope, that check's done already.
Okay, thank you.
Let's thank the speakers.
All right, we have coffee outside and we are back in the room for the last session at 3:30.
Oh.
I will find out. So I can't. No, I'm working. The moment I decided to write down is when he said, I would do that. But very funny. How do you say
Okay.
Yeah, very hard. And they say this says it's science. I'm excited to surprise you.
Yeah, just share the screen. Just testing the audio. Okay.
He was online a minute ago.
Hello, my name is Tristan Schäfer, and this talk is about a design space exploration procedure that uses combinatory logic synthesis, which we applied to sampling-based motion planning problems. So first of all, let's start off with the motivation. There are spaces of high variability. That means we have data products, maybe algorithms or models, whatever, that expose high variability. And these spaces usually require means for automatic configuration of these variants. Design space exploration is a technique to systematically search these spaces, these design spaces. And in our case, the space represents algorithmic families. Our contribution is as follows. We use combinatory logic synthesis to represent these spaces and build programs for algorithmic variants. That means we can build one particular variant that is part of the space using a certain configuration. We incorporate an optimization tool to implement an automated design space exploration procedure. And we apply this to the sampling-based motion planning domain to demonstrate the benefits of this methodology. So first of all, we consider a motion planning problem as a multi-objective optimization problem. We have a domain of interest, the design space, which consists of different dimensions that we can change, which usually are variability points. And the optimization criterion is manifold. Therefore, we have multiple optimization functions, and the result of this function that we need to optimize is not a single value, but rather a tuple consisting of many different values. Therefore, we usually don't have one particular optimum, but rather a Pareto front and a set of different configurations that make up the Pareto set. So in our case, we selected the planning dimensions and also the solution vector, which you can see here. Our planning or design space consists of a planner, a sampler, a motion validator, and a maximal allowed planning time. So these values, the first three values are categorical values, while the last one is a numerical value. Our solution vector consists of the path length, the computation time, which are resulting path length of the resulting path. The computation time is the time that was required to perform to solve the problem. And also the number of values, as it is not guaranteed that the configuration of an algorithm finds a result. So this is an overview of our procedure. On the left side, we have an active learning loop, which is guided by the hypermap optimization framework. This optimization framework chooses a configuration inside of the design space. We perform a synthesis. We synthesize a Python program that runs OMPL code. And after running multiple instances of this planning program, we can return a result vector, which consists of the optimization criteria we have shown on the slide before, which is then fed back to the optimization framework. Inside of the active learning loop, the optimization tool builds a model to represent the design space, or rather to represent the outcome for different configurations, and therefore aims to find new samples that are hopefully somewhere near the Pareto front. Few notes on CLS. CLS, combinatorial logic synthesis, uses a repository of components to build data and programs. CLS uses intersection type as a logical foundation, and as such, users can define semantic types to describe properties of components. Users can also use logical expressions to specify rules of composition on a component level, and therefore CLS can be considered as some kind of logic programming. Another important part is that the semantic types and the rules of composition can be used to encode domain knowledge in the repository. In this study, we demonstrated this by allowing only viable planar sampler combinations. Synthesized programs are not planning programs, but rather generators for Python planning programs. And the generators take care of parsing problem definition files, referencing 3D models, generating code for OMPL, and also the generators execute the generated Python programs and analyze the output. So this is a plot of one optimization run that was performed for a 3D rigid body planning problem instance. And we have the solution path length on the x-axis and the computation time plotted. And in this case, we have observed that there are three particular planners that show strong results. EST, SPL, and Stride. And also we can see that the sampling strategy seems to have some kind of impact regarding the computation time and the solution path. More results on the paper. Due to the time restriction, I cannot go too much into detail here, but let's take another line of experiments that we conducted. We synthesized motion planning for configurable robotic arms, and we used synthesized models of robotic systems in this case. So these robotic arms were also a result from a previous synthesis run, and we integrated this new kind of planning problem instance, that means planning for configurable robotic arms, into the existing repository. So we extended the 3D rigid body planning repository, and this is notable that it required very little effort. We had to initiate a new state validator that uses the robot model and perform simple forward kinematics to check if a certain configuration state causes a collision or not. Well, we performed multiple experiments with different degrees of freedom, and some of the plots are also contained in the paper. And overall, this particular problem instance showed to be somewhat favorable for the algorithmic family of RRT planners. This is one particular result that we found. Well, this is our dirty laundry slide. challenges and limitations. First of all, CLS in general comes with some challenges. First of all, the specification and implementation of components and therefore the setup of the repository always comes with an initial cost. And also working with CLS put some requirements on the domain which are regarding the variability and maturity of the domain and also the applicability to real-life problems. Last point is because CLS can produce runnable code and can produce large code and even software products, which is one of the which is something that other synthesis techniques have problems with. And well, one particular drawback is that a logical framework is sometimes perceived as heavy machinery. Although we have several student projects that were very successful, and they imply that starting with CLS can be done with moderate effort. Well, our experiments that we have shown in the paper, first of all, our methodology delivers data without explanation. And in our paper, we provided the methodology, the tools to conduct a study of a certain domain. However, our tool does not explain how these results have to be interpreted. We do not intend to provide an in-depth analysis of the motion planning domain, but rather just present the tools to perform this work. Well, also from a machine learning perspective, it might be interesting to analyze how the incorporation of different optimization or learning techniques impact the results. So let me conclude this talk with this slide. The design space representation using CLS brings several benefits. You have a reusable, extensible, and modular approach or setup that can express variability on a component layer. This brings several benefits for the adaptation, for instance, of problem instances. And also CLS enables the construction of industrial scale software products and data, which is something that other synthesis techniques apparently have problems with. Also, our methodology allows the evaluation of particular variability points, such as planners, samplers, or collision detection techniques. Our future work could target hybrid optimization approach that performs search in a feature space, but also considers planar parameters. And this could be implemented by supporting component-specific parameters. That means we have different combinators or different software components that represent planners with predefined parameter sets. Also, we would like to further study the integration of other optimization techniques. Thank you very much for listening.
Thank you. I wonder if any of the authors is online to answer a question later. Oh, they are online? Very good. So you'll be able to put them. Very good. So we move on to the second talk by Khalid Jafar and Michael Otte. PPIX, funnel-based online feedback motion planning, replanning in dynamic environments, and Khalid will give the talk.
you. Hi, I'm Khaled, a PhD candidate from the Motion and Teaming Lab at the University of Maryland College Park, the host university. So today I'll be talking about our work, PipeX, which uses funnels for feedback, motion planning, and replanning. So consider this particular illustration in which we have three funnels stacked one over the other. And imagine if you drop a marble at the inlet of the funnel 1. So it remains within the walls of the funnel 1 and drops into funnel 2 and then drops into funnel 3 and then drops to the ground. So this was our primary motivation to use funnels for feedback motion replanning. So I'll go through the three terms in the title of the slide. So feedback motion planning considers the two-way interaction between the planner and the controller. So usually when you say robot autonomy stack, you have say a high-level planner and a low-level controller. And but what if the controller wants to talk back to the planner? What if it says that this is my stability guarantees, this is my performance, like this is where I'm stable, like especially for nonlinear systems. The same controller can be stable in a particular region of state space, but in a different state space, it can be destabilizing. So feedback motion planning enables that two-way interaction. And funnel is mathematically defined as a finite time invariant set, or in English, it's like if you start within the set, you remain within the set for that finite time interval. And replan is short for plan and replan in case of changes in the environment. So the algorithm, the framework that we present is called as PipeX, which stands for planning, replanning, and pipes in dynamic workspaces. So X signifies the dynamicity of the workspace, and pipes is analogous to funnels. So given a workspace in which we have a goal region, a start, and obstacles, we grow a graph of funnels from the backward, from the goal region, like so. So it's composed of the funnel edges. And once the start is in the inlet of a funnel, we complete the graph building phase, and then we plan a path in that. And we use incremental search, graph search to plan the path in this. So, and in case of new obstacles, the three funnels on the left become invalid and it replans accordingly. So there'll be two terms which I'll be using throughout the talk. One is funnel graph, which is the network of the volumetric funnels itself, and funnel path, which is a finite sequence of composable funnels. So what do I mean by composable? In this case, consider three funnels, 1, 2, and 3. The outlet of funnel 2 is completely within the inlet of funnel 1, and that is defined as composable. So 2, 3, 2, 1 can be a funnel path, but 3, 1 cannot be a funnel path. So a brief background, we combine concepts from three different fields. We use invariant set theory to compute the funnel. We use sampling-based motion planning to construct an RRG. And then we use an incremental graph search like D-star light or LPS star to keep computing the shortest path as well as updating the shortest path in this graph. So our contributions are that we provide a global online planning and a replanning algorithm with funnels. And we propose a graph data structure to store this particular funnel network. So we have an offline phase and an online phase. In the offline phase, we pre-compute a library of funnels for different initial and final states. And in the online phase, from this library, we compute the optimal sequence of funnels that will take from the start to the goal region and update it on the fly. So to compute the funnels, we consider the robot's closed loop dynamics. And the level sets are the bounded level sets of a quadratic Lyapunov function. Bounded between 0 and 1, it's a positive definite function. And then time derivative is a negative semi-definite function. And we use convex optimization tools like sums of squares to maximize the volume of the funnel. So this is an example of a funnel library. So the funnels exist in the time cross state space, but we have projected down to time cross XY space for visualization. So for 2D planning, we need XY, and it's the initial conditions are in a circle, the green dots are at a circle of epsilon radius, and the final state is the origin. And the finite time horizon is 0 to 5 seconds. So once we have the library in the online phase, we construct the funnel graph using sampling-based methods. And we use a heuristic-based incremental graph search like D-star light or LPS star to keep rewiring the shortest funnel path. So this is an example in a 2D forest environment. So with 100 iterations, this is the funnel graph that it grew, and this is the funnel path that it determined. So shortest funnel path with respect to the underlying graph. So after 300 iterations, it's like after it samples some points, some configurations at the center, it's able to rewire the path through the center. And we use a graph data structure to represent this funnel network. And in the next slide, I'll be talking about that. So the directed graph data structure should encode two information. One is the network of the funnels itself, and one is the intercomposability information. So consider this particular illustration wherein we have three funnels. We have 1, 2, and 3 funnels. We in this funnel 1 and funnel 3 pair are composable, but funnel 1 and funnel 2 pair are not composable. So the graph data structure should encode that information. There are 3 funnels and the composability information. So first we start off by representing the inlet and outlet regions as the graph vertices. So we have 3 inlets, 3 outlets. We have 6 vertices in the graph right now. And they are either inlet nodes or outlet nodes. And the next obvious choice is to just connect the inlet and outlet with the edges representing the funnel itself. So we term that as motion edges. So we have 3 motion edges for the 3 funnels. So additionally, we introduce a continuity edge saying that B1 to B3 is possible because it's composable, but B1 to B2 is not possible. So once we have a graph data structure, all the graph search algorithms are happy. We can easily plan paths. We can compute optimal paths. And that's how we go about our replanning, online replanning strategy. So to quickly recap, we have augmented nodes that represent inlets and outlets. We have a motion edge that denotes a funnel. We have continuity edges that represent composability. And those continuity edges are 0 cost, so they don't have any effect on the optimality given by the path, the search algorithms, but they are just there to represent the feasibility of the path itself. So we validate our approach, our algorithm in 2 different environments across various scenarios. I'll be presenting one, in the previous slide you saw a forest environment. Now in the next slide, I'll be showing a maze environment. So the quad rotors so these are time splices of the quad rotor running pipex in a maze environment, 2D maze environment. So the shaded regions are the sensor radius. And the quad rotor starts in the lower right corner and goes to the lower left corner. And the black walls are the perceived walls as of that time instance. So when it starts moving, it needs to perceive the walls and then quickly rewire its motion plan. So I have this particular thing in action video. So this is the initial pre-planning phase wherein it's growing a graph. So it's trying to converge to the optimal funnel path in this, and then it starts moving. So I'll quickly play it one more time. And I'll be presenting one particular interesting result from our experiments in which we analyze the Lyapunov function value of the trajectories of the state itself. So it's like, so we say, why do we make a big fuss about the composability? Why should the inlet, but the outlet should be in the inlet? So it's because we want the entire funnel path to be invariant. We know that each funnel is invariant, but not the entire path. So that's why we need the composability information. So what we do is that we slightly perturb we slightly alter the robot dynamics, we slightly perturb the start pose and simulate and then see whether the actual trajectory lies within the funnel path. And the Lyapunov function value, so each color represents a different trial, and you can see it always remains within 1, which is the level set boundary value. And the peaks that you see in the Lyapunov function value are when it hands over from one funnel to the other, that is the outlet inlet region. But it still remains 1 throughout because we checked for the composability. So 2 inferences from this particular result is that we have the funnel path itself is invariant, and then our algorithm is robust to perturbations and modeling errors. So going on to the dirty laundry, our approach is not entirely online. We still need a offline phase in which we pre-compute a library of funnels. We feel it's essential because it's very computation intensive to compute them online. And having a funnel library or any library of motion parameters comes with its own drawbacks. It's like we can have only finite motion parameters or finite funnels. So we need to discretize the velocity space, and that leads to only resolution completeness and optimality. And one more big assumption that I didn't state in previously is that we assume that a closed loop controller exists. And given a closed loop controller, we know the closed loop dynamics. And that is when we start computing the funnels and the other stuff, the other planning stuff. So whatever the controller characteristics are, the funnel inherits that, and our planning algorithm inherits that. So if the controller is robust, or if the controller is adaptive, our approach is also adaptive and robust to errors and modeling uncertainties. And one more thing that we kept pondering upon, or also currently pondering upon, is how do we give formal optimality guarantees? We know that the graph search is optimal. It gives the optimal optimal path, but is it really optimal with respect to what is currently happening? So we know that the trajectory lies within the funnel path, but we don't know what is the actual length of the trajectory. It can take a roundabout route, or it can go directly from final to the end state. So the funnel volume also affects the trajectory length. So how do we give formal optimality guarantees? That's one scope of our future work. So quickly to summarize, we present PyPEX, a global online replanning algorithm using funnels. We present a directed graph data structure to use graph search algorithms and also to represent the funnel network. And looking at the bigger picture, it's like we are recasting the challenging problem of online feedback motion planning into a graph search, which we can easily solve using efficient algorithms. And funnel edges are like a relaxed alternative to the 2-point boundary value problem. So whichever graph rewiring methods uses precisely going from one configuration to the other configuration, we relax that because we don't need to go exactly from point to point, but just in the vicinity of that point. So yeah, for the pseudocode and the algorithms, you can check our preprint. And we also have a journal version in which we go into the finer nuances of our approach, and then we give the necessary rigorous formulation. Yeah, thank you.
Thank you, Jafar. We move on to the second online talk by Marcus Herger, Hannah Kurniawati, Dirk Kruse, and Nanye, adaptive discretization using Voronoi tree maps for continuous action POM-DPs. And
hi, my name is Marcus.
Is giving the talk.
Herger, and I'm currently a postdoc at the University of Queensland, Australia. And today I'm going to talk about our work on a new online POM-DP solver for continuous action spaces. So it is well known that every autonomous robot that operates in the real world is inherently subject to various uncertainties, such as control and sensing errors, or limited understanding regarding the operating environment. Now, in order for a robot to plan a robust strategy to achieve its task, it has to take these uncertainties into account during planning. And a principled way to deal with such problems is the partially observable Markov decision process, a framework which enables robots to make good decisions in the presence of uncertainties. Where the main components of a POM-DP are the state, action, and observation spaces of the robot. Then we have a transition and observation function, which model the uncertainty in the effect of executing actions and receiving observations as conditional probability functions. And last but not least, we have a reward function, which basically models the objective of the robot's task. Now, due to all the aforementioned uncertainties, the true state of the robot is only partially observable. So instead of planning in the robot state space, we lift planning to the belief space, which is the set of all probability distributions over the state space. And the goal is then to compute an optimal policy, so a mapping from beliefs to actions, which maximizes the expected total discounted future reward the robot receives when following this policy. Now, unfortunately, it has been shown that computing the optimal policy is computationally intractable in general. And in particular, it is actually exponential in the number of states and the number of observations, and doubly exponential in the planning horizon. So in other words, in all but the simplest problems, we have no chance to actually compute this optimal policy. But there's been a lot of progress in the last 20 years. So nowadays we have some very efficient approximate optimal online solvers where the idea is to balance optimality with computational tractability. And instead of computing a policy for the entire belief space, online solvers compute a policy with respect to the current belief only, typically by performing forward search in a belief tree to evaluate sequences of actions, where the nodes here represent beliefs and the edges represent pairs of actions and observations. So there are various search methods that have been proposed whose aim is to estimate the best action to perform from the current belief. So the action that maximizes the expected total discounted reward that can be achieved from the current belief. Now, these online methods can be quite efficient for POMDP problems with small discrete action spaces. However, one of the fundamental challenges in POMDP planning in general are continuous action spaces. Now, the difficulty is that for POMDPs with continuous actions, we have to do optimization in potentially high dimensional spaces while having limited amount of information regarding the exact action values. And additionally, for tree search-based solvers, we would have to encode every possible action via an action edge, which is obviously no longer feasible for continuous spaces. Now, to deal with these issues, state-of-the-art methods typically aim to select a small sampled subset of the action space and focus on evaluating the action values for this subset only. For instance, one of the earlier methods called GPS-ABT interleaves general pattern search, which is one of the simplest gradient-free optimization methods, with Monte Carlo tree search to evaluate the action subset. Now, more recently, two Monte Carlo tree search-based methods called POMCPOW and WOMCPOW have been proposed, where the idea is to use progressive widening to grow the set of sampled candidate actions as planning progresses. For instance, WOMCPOW partitions the action space into Voronoi cells and then biases the action sampling towards cells which likely contain good actions. However, sampling from Voronoi cells can be quite challenging, particularly for high-dimensional action spaces. And additionally, the rate at which those cells are refined by sampling new actions is independent of local information in the action space, such as the cell sizes, which can result in insufficient exploration of the action space. So to resolve these issues, we've developed a new online POMDP solver called Adaptive Discretization Using Voronoi Trees, or ADVT in short. Now, in a nutshell, ADVT performs three main operations during planning, similarly to state-of-the-art methods, which is incrementally constructing a set of candidate actions for each sampled belief. Then we use the set to sample episodes using an action selection strategy, where an episode is a sequence of state, action, observation, and reward quadruples. And finally, we use these sampled episodes to improve the action value estimates. Now, for all three components here, we decided ADVT to better utilize local information in the action space, which then helps our method to find good actions more effectively compared to state-of-the-art methods, especially for problems with higher dimensional action spaces. So in particular, for the first component, we are proposing a hierarchical partitioning of the action space called Voronoi tree. So at each belief node, we are constructing a tree, shown here in the middle, where a node in this tree corresponds to a Voronoi cell of the action space, induced by a sampled action. And this cell is then further refined into two child cells by uniformly sampling an additional action from the cell. So here we then take the set of sampled actions corresponding to the leaf nodes of the Voronoi tree as our set of candidate actions. Now, the benefit of those Voronoi trees is it allows us to derive efficient sampling-based approaches to estimate the diameters of the Voronoi cells, which I'm going to discuss shortly. And then we can use the cell diameter information to decide when to refine a cell. So during search, after we've selected a candidate action A from belief B, we refine the cell corresponding to the action if this refinement condition is satisfied, where this condition here essentially prevents over-exploration of areas of the action space that already contain a large number of action samples. Now, two questions here need to be further elaborated. The first one is, how do we actually estimate the diameter of a Voronoi cell? And the second is, how do we sample a new action from a cell when ADVT decides to refine it? Now, for the diameter estimation, suppose we have a Voronoi cell with inducing action A, and we want to estimate its diameter. Now, to do this, we first sample a set of points that approximately lie on the boundary of the cell. And this is being done by first sampling a point A prime that lies in the exterior of the cell. And then we use a binary search method with A and A prime as the initial endpoints to find the point AP, which approximately lies on the boundary of the cell. Now, once we have sampled a set of boundary points using this method, we compute the smallest enclosing sphere, which contains all the sampled boundary points. And finally, the diameter of this sphere serves as an approximation of the Voronoi cell's diameter. Now, when ADVT decides to refine a cell, we sample a new point from it. And to do this, we're using a hit and run method by performing a random walk within the cell. So starting from the inducing point of the cell, we sample a boundary point, similarly as I've discussed before. And then we pick a random point between the inducing point and the boundary point, which serves as the starting point for the next iteration. So by repeating this process for a number of steps, we obtain an action that is approximately uniformly distributed within the Voronoi cell. Okay, so for the second component here, when sampling the episodes, we additionally use the diameter information in the action selection strategy in order to facilitate exploration of large areas in the action space that only contain a few action samples. Now for the third component here, once we've sampled an episode, we are updating the action values along the sequence of selected actions. And in contrast to most MCTS-based solvers that use Monte Carlo backups, ADVT uses a stochastic version of the Bellman backup to do this. So suppose an episode selects action A at belief B, then the action value is updated with the immediate reward plus the discounted estimated value of the next belief reached by the episode. Now, this strategy is very similar to the one used by the Q-learning algorithm in reinforcement learning, and it helps ADVT to focus its search on more promising parts of the belief tree, which is particularly useful for problems where good rewards are sparse. Okay, so to test and evaluate our method, we tried it on a number of problem scenarios with continuous action spaces, where in the first problem here, an agent, which is represented as a blue disk, has to push an opponent into that green goal area without pushing it into the black region, all while having imperfect information about the position of the opponent and the effects of a push. Now, in the second problem, we have an autonomous vehicle, which has to park inside that gap between the black obstacles. But initially, the vehicle is uncertain regarding its starting location, and it has to traverse across those differently colored terrains to localize itself. And finally, for the third problem, we have an opponent whose motion is described by the van der Pol differential equation. And the goal of the agent is to catch the opponent while having imperfect information regarding its location. So this table here shows the average total discounted reward achieved by ADVT, as well as the baseline solvers POMSI-POW and WOMSI-POW. And we can see that ADVT generally outperforms the other solvers, except for the last problem. Now this is because in this problem, we also have a continuous observation space, and the other methods are actually designed to handle continuous observations, whereas our method is not, which we are hoping to resolve soon. Now, these results are also reflected by the success rate of the solvers. So this table here shows the percentage of successful runs of all solvers in the problem scenarios, Well, for the first two problems, ADVT has a much higher success rate than the baselines. Now, in all those problems here, we actually only have a two-dimensional action space. So to figure out how our method performs in higher dimensional action spaces, we additionally tested it on a scalable POMDP problem in which we have an autonomous manipulator with varying degrees of freedom and therefore varying dimensionality of the action space. Where here the manipulator is uncertain regarding its configuration and it has to localize itself by carefully touching those differently colored walls in order to mount a sensor in the environment. So here we are looking at 4 variants of the problem with increasing dimensionality of the action space up to a 12-dimensional space. And the results for the average total discounted rewards in this plot indicate that our method tends to scale better to higher dimensional action spaces compared to the other two solvers, which is also reflected in the success rate of ADVT for these problems compared to the baselines. Now, these results here are actually only a small subset of the results we have in the paper, where we also test our solver on variants of the first 2 problem scenarios, as well as an ablation study to look at the effects of the different components of ADVT. Now, despite these results, there are currently 2 main limitations of our method. First of all, at the moment, we don't have any guarantees that ADVT converges towards the optimal policy. And second, right now, ADVT doesn't focus on problems with continuous observation spaces, which can adversely affect its performance in these type of problems, as we've seen before in the VDP tag problem. Now we're hoping that we can resolve both points here in future works. Okay, so this already brings me to the end of my talk. Now we are also providing a C++ implementation of ADVT in this GitHub repository here. So if you're interested, feel free to have a look and give it a try. Thank you very much.
Thank you, Marcus. And we move on to the last talk of this session and of WAFR. And this talk is by Richard Wren, Sivakumar Rathinam, and Howie Choset, a lower bounding framework for motion planning amid dynamic obstacles in 2D. And Richard will give the talk, please.
Okay, thank you, Dan. Thanks for the introduction. And thanks everybody for staying here till the last talk. I know you must be tiring, and I will make it easy to follow. Okay, I'm Richard Wren, a PhD student at Carnegie Mellon, and very happy to present our work, a lower bounding framework for motion planning amid dynamic obstacles in 2D. Okay, so in this work, we consider a trajectory planning problem in continuous 2D workspace with continuous time. And we have a point robot that can move in any directions with the maximum speed Vmax. And obstacles can have arbitrary shapes moving along arbitrary trajectories, but those trajectories are known in advance. And the goal is to find a collision-free trajectory P star from a given start to a given goal with the earliest arrival time C star. Okay, in the literature, this problem is shown to be NP hard. And currently there is no algorithm to solve this problem, or say C star in general. If we make additional assumptions on the obstacle shapes or the obstacle trajectories, then in theory, there are approaches to compute the true optimum C star. On the other hand, there are tons of approaches that can compute a feasible solution, for example, search-based, sampling-based, optimization-based, or learning-based. But in this work, we are interested in finding lower bounding solutions. In other words, compute a solution whose cost is a lower bound of C star. So trivial lower bound are always possible. For example, Euclidean distance between the start and the goal that ignores all the obstacles. But we want to find tight lower bound. Okay, and why do we want to find tight lower bound? So as I have mentioned, there are many approaches to compute feasible solutions. However, one fundamental question with regard to all these feasible solutions is how far away are they from the true optimum C star? In other words, what's the suboptimality bound? So since C star is hard to obtain in general, if we can compute tight lower bound, then these lower bound can be used as proxies to estimate those suboptimality bound. So the goal of this work is to develop a framework that can systematically estimate tight lower bound of C star. So if we visualize this motivation with the figure, it looks like this. The blue line is the true optimum, which is hard to obtain. The black dotted line are the existing approach that can compute a feasible solution whose cost is an upper bound. And in this work, our goal is the red dashed line. Basically, by put more computational resources, hopefully we can compute tighter lower bound. Okay, and here's a video that illustrates the difference between upper bound solution and lower bound solution. As you can see, the red line is an upper bound solution computed by search-based planner, and the green line is the lower bound solution. And as you can see, it's infeasible since it collides with the obstacle. And just want to point out that lower bounding solutions must be infeasible because by definition, C star is the minimum cost feasible solution. So we cannot have a feasible solution whose cost is even less than C star. Okay, how can we actually achieve this goal? So our approach consists of two parts. So first, we propose a problem formulation that can relax a continuous problem to a relaxed graph search lower bounding problem, which is the main contribution of this work. And then since we have a graph, we can adapt existing graph search techniques to solve the problem. And in this work, we use A-star search. Okay, to formulate the lower bounding problem, to begin with, we discretize the workspace uniformly into cells. And then for each cell, we call its border a line segment. And then for each line segment, we will divide it uniformly into subsegment. And then, as shown in figure 2, for each subsegment, we define a graph vertex for that subsegment. And then we will define the graph edges. So within the same cell, for two subsegments that are not within the same line segment, we will connect an edge between them. And the edge cost is assigned to be a lower bounding distance, which is basically the shortest distance between a pair of points belonging to the respective line segment, as shown in figure 3. So this is basically the smallest possible distance between two subsegments. Okay, now we have a graph. The next thing we need to do is to relax the collision avoidance constraints. So given a node, let's say V2, so it's reachable if the entire line segment is not occupied by some obstacle. Otherwise, it's non-reachable. Or say like the entire line segment is enclosed by some obstacle. As shown in this example, we have an obstacle moving from the right to the left, and the vertex V2 is non-reachable between t equals 2 and t equals 3. So that's the first relaxation. And in addition to that, we also allow a robot to stay at a vertex once it reaches that vertex. That's another relaxation. So in this example, if let's say a robot reach vertex V2 at t equals 1, then it is allowed to stay there through time interval t equals 2 and 3. And also know that static obstacles can be treated as a special type of dynamic obstacles. So in this example, vertex V2 can be reached at any time. Okay, and if you are familiar with safe interval path planning in the literature, you may notice the similarity between the reachable and non-reachable interval with a safe interval in the literature. However, since we are finding lower bounding solution, so in other words, even we have a reachable interval, it may still collide with the obstacle. So we use a different name to highlight this difference. Okay, a short summary so far. We have introduced a discretization and a relaxed collision model. So now we have a relaxed graph search problem. The remaining question is how to solve this graph search problem and whether the obtained solution is guaranteed to be a lower bound. So to solve the formulated graph search problem, we're going to use just A star. And other graph search techniques can also be applied. So specifically in A star search here, the G value is used to represent the earliest reachable time at each node. And then to expand the node, we will find the earliest reachable time at each of those adjacent nodes. So that's the step where dynamic obstacles are considered. So remember the reachable and non-reachable interval we have just defined. And then the edge cost is simply defined as the traversal time of the edge, which is the lower bounding distance divided by Vmax. And also know that since we allow a robot to stay at a vertex once it's reached there, therefore we only need to store one G value for each node. Okay, and is the computed solution guaranteed to be a lower bounding solution? So the key idea is that for the original continuous problem, let's say this black line is the true optimum P star, we can always construct a corresponding solution in the graph, which is P. And the cost of this constructed solution must be no larger than the original cost of P star. And then since we run A star in the graph search, so we are guaranteed to obtain the true optimum solution in the graph, which is guaranteed to be less than, like have a smaller cost than the constructed solution. Therefore, the solution computed by A star is guaranteed to be a lower bound of the true optimum C star. Okay, some numerical results. So, okay, in all my tests, the baseline approach is to ignore the dynamic obstacles and then construct a visibility graph among static obstacles and then find the shortest path in the visibility graph. And to begin with, we will start with a simple instance where the true optimum C star can be obtained. So as shown in figure B, so we have two thin bar-like obstacles in the workspace. And the blue line is the true optimum computed by the baseline approach in this case. And the green line is the lower bounding solution computed by our approach. And just know that in figure C, between vertex V4 and V5, the cost is 0. Okay, and we can derive that for this instance, the ratio between the cost of the green solution and the cost of the blue solution is K minus 1 over K. So basically by increasing K, the lower bound become tighter and tighter, and that aligns with our numerical results. Okay, here's a slightly complicated example where we have only one dynamic obstacle moving from the center to the left. And as shown in figure B, so it's an animation that highlights the difference between the lower bounding solution and the upper bound solution. Okay, in figure C, we show that with different parameter N and K, where K is the horizontal axis, N is a different color. So we can obtain like tighter and tighter lower bound if we increase these parameters. And the bar shows the number of expansion required by A star. So in other words, like by increasing those parameter, although we obtain tighter lower bound, but the computational burden is also higher. And as you can see, the brown line is the baseline approach. So our approach soon outperforms the baseline. Okay, in figure D, we use RRT and safe interval path planning to compute an upper bound solution. And then we use both our approach, LB A star, and the baseline lower bound to estimate the suboptimality bound of the those feasible solution. And as you can see in the table, as shown in the middle column, like our approach provides much tighter suboptimality bound in comparison with the baseline approach. Okay, and then a more complicated example, we have two bar-like static obstacle and 10 dynamic obstacle as shown in the animation. And in this case, again, like basically by increasing N and K, our lower bound become tighter and tighter. Okay, and here's another visualization. As you can see, by increasing N, in this case, we fix the K and the increase N. The lower bound solution tends to become tighter and tighter to the true optimum. If you look at the upper bound solution, the red line. Okay, the dirty laundry. So if we So like there are for sure like cases where our approach failed to provide tight lower bound. For example, in figure A, if we have a static obstacle that locates in the workspace like this, the baseline approach can still capture the true optimum, but our approach will simply ignore the static obstacle because the discretization fails to capture the obstacle. And in figure B, it's another example where we have a dynamic bar-like obstacle moving from right to the left. And in this case, both the baseline and our approach actually fails to capture this dynamic obstacle. And another thing is currently we have no proof about asymptotic convergence when we increase K and N. So we haven't shown that like our lower bound will converge to the true optimum yet. We only show the empirical results. Okay, to conclude, so in this work, we consider a problem about motion planning in 2D among dynamic obstacle. We propose a framework where the key contribution is to formulate a lower bounding problem whose solution is guaranteed to be a lower bound of the true optimum C star. And we also adapt A star to actually obtain this lower bound and verify our approach with numerical results. Thank you.
We now invite all the speakers, also those that are not in this room. Or perhaps we start with a question by Jeff. You need a mic. Take a mic.
Thanks for the great talk. I had a question for Khalid.
Yeah, thanks.
As I understand it, you can choose how big your funnel library is at some point, right?
Yeah, that's true.
Is there a trade-off that you can make between your offline process and online process by how big you make that funnel library?
Okay, thanks for the question. It's like a design choice that we make based on the resolution that we want. We can just go like Manhattan distance kind of thing, or we can just go in a smoother path kind of. So that's a design consideration, what's the resolution that we want, whether you want it to be fine or whether you want it to be coarse kind of. So based on that, then we need construct the funnel library.
So I guess maybe like the runtime consideration would be why you want to make your funnel library too big, or?
So one thing is that it takes a lot of time to compute those funnels, and it's for each type of controller we need to compute a different type of funnel, and so that's our main limitation. Actually, as you said, we can try to have a sufficiently large funnel library, but still that will not guarantee completeness or optimality kind of.
Yeah, my question is for Richard. My question is, does knowing like a path through the lower bound path, does that give you any insight or information into finding a good, near optimal feasible path, or are they completely unrelated?
Yeah, that's a good question. So I think it can give you like directions or information about where the true optimal solution may locate. Because, if you look at the lower bounding solution and the upper bound solution, then like in general, the true optimum should be somewhere in the middle. Yeah, but one caveat that is like normally in these motion planning problem, you may have multiple optimal solution with the same cost. Then in that case, like with only one lower bounding solution and one upper bound solution, maybe you do not have enough information to exactly locate where the true optimum is.
This is a question for the second speaker. The way you compose your funnels is that you make them finite time, like a continuous discrete time step. But in order to really get composability, you could as soon as your funnel enters the mouth of another funnel, you could turn on that controller immediately. How would kind of giving yourself flexibility to choose the final time of your funnel affect the construction of your dynamic graph over time?
Okay, that's an excellent question. So only way we can fit in more information is by having a Q&A session. So I couldn't fit it in a slide. So it's like we grow the funnel tree backwards from the goal region, right? And we compute those funnels as the backward reachable sets. So at any time instance, we can truncate that. So even though I calculated the funnels from 0 to 5 seconds, it grows backward. And if I want to truncate at 4.5 seconds, I can do that. So that's why it doesn't necessarily need to go from all the way from 5 to 0. It can do it at 4.1, 4.2, or something like that. So that's how we make, so we don't compose it by epsilon distance every time or epsilon time every time. It's just from 0 to epsilon. It's a continuous time.
I'd like to involve the remote speakers. Marcus, I have a question for you. You mentioned that you compute the minimum enclosing sphere. Now, when you are in dimension 12, how do you do it? And is this a bottleneck in your computation?
So first of all, can you hear me?
Yeah, we hear you well.
Okay, right. Thank you. So essentially, computing the minimum enclosing sphere is actually, kind of a standard problem in computational geometry. So there are some very efficient algorithms that can do that for you. And so we actually use one algorithm that is implemented in the Seagull, a C++ library, which is a randomization-based algorithm, which essentially, so given a set of points, it approximates the minimum enclosing sphere for you. Yeah.
Wonderful
so the
answer.
method is, yes, pardon?
It was wonderful answers because it involved Seagull. I didn't know that. But I have another question. In the hit and run process, how long do you have to run it in 12 dimensions?
So that's actually, so that's actually a very good question, because those hit and run methods in general, so what we actually want to do is we want to draw a sample that is uniformly distributed within the cell. And those hit and run methods usually, they approach a point that is uniformly distributed in polynomial time, as far as I know. So in practice, we have to, for practicality, we have to limit the number of steps. So typically, we perform between 20 and 50 steps, depending on the dimensionality of the action space. So in our problem scenarios, we found that this gives us samples that are sufficiently close to uniform. Yeah.
Okay, thank you. Questions, please.
Everyone, really nice talks. I enjoyed it. I have a question for the second presenter. So I'm interested in learning about or the relationship amongst the funnel widths or generally their dimension and how they relate to state estimation and also measurement estimation as well, right? So first, is there a link between the funnel widths and also state uncertainty?
No. So we assume full state observability. So we assume we have a state estimator which gives the feedback to the controller.
Okay, but so there's no notion of state uncertainty in there.
Not in the feedback part, but in the dynamics, the like unmodeled uncertainties and those kind of, like in the dynamics and perturbations itself, disturbances. We have uncertainty baked in there, but not in the feedback part.
Okay. And the second question was kind of piggybacking off of, I think, a question that someone else already asked, which relates to the dimensions of your funnels. And for example, creating long and wide funnels that provide obstacle-free paths, right? I think that can, in some sense, help your relax your requirements on how accurate your states need to be or how accurate your measurements need to be when you're actually executing the trajectories. And so I was just wondering if you thought anything about that.
Can you repeat just specifically the question? I understood the gist of the question, but no.
Yeah, so basically, I'm thinking, so it kind of relates back to my first question, right, with state uncertainty. If you can essentially provide a link or create a link between state uncertainty, measurement uncertainty, and also the dimensions of the funnel, right? So if we're executing a trajectory, right, and we're using these funnels to say that the robot should follow this path, right? If we think about the funnel width as a measure of how allowable we can allow the state uncertainty to be, right? For very large funnels, we can say, well, we don't really care how accurate your state is, right? But for very fine funnels, you require that high accuracy, right?
Yeah. So the solution is the other way around. We know the characteristics of the controller, and then we compute the funnels. So if the controller can handle uncertainties or can reject disturbances, it can only certify a finer region of space. So that accounts for in the other way around than you asked. So if it's a very stable controller or if the system is perfect and we don't have any unmodeled disturbances then it can certify a larger region of space around the nominal trajectory. And with that, we plan. If it's or if you consider all the effects, then the certificate that we give around the nominal trajectory, that will be thin. And that's how we use that and for the planning algorithm.
Okay, thanks.
Can you hear me? Yeah, a question for the last speaker, something very simple. Just to understand, as the discretization gets finer and finer, I think that you use the letter K for the number of steps you had. Your approximate path becomes optimal, right?
So can you repeat? Like what I hear is if we increase N and K, we'll be able to capture like smaller obstacles. Is that what you mean?
My question is, as K tends to infinity, does your lower bound approaches always the optimal length? And the second question would be, do you have a guaranteed approximation ratio for a given K on all the instances?
Okay, so for the first question, currently we haven't shown asymptotic convergence. In other words, if K goes to infinity, currently we cannot guarantee that the solution, the lower bounding solution converges to the true optimum C star. And the second question is, if with a finite K, can we provide like a distance guarantee between the lower bounding and the true optimum?
Yeah, an approximation ratio for all possible motion planning instances.
Okay, yeah. So currently, no, we can only guarantee that it's indeed a lower bound, but we don't know like how far away this lower bound is from the true optimum. Yeah, so in practice, like this can be estimated by the distance between an upper bound solution and the lower bound solution.
Yeah, I was wondering in that case if you can use that. It doesn't seem impossible to get, given the geometry of your problem, an approximation ratio for the lower bound, so that given an upper bound, you can actually.
Yeah, okay, that makes sense. Yeah, like if we have tight upper bound, then like in reverse, we can estimate how tight our lower bound is. Yeah.
Yeah, okay, thank you very much.
I have a question for Mohammed. A very brief question, and I have a question for the first speaker.
Okay.
So I just wanted to find out what was the max funnel branching that you had on your system?
Funnel.
And then what was the intuition behind it?
The funnel branching, I didn't quite get.
Yeah, so if you look at one of your images, you have your branching where you have the funnels, then you have like you're growing it with trees. It seemed like you had a branching of just two. But then there are cases where it looks like you could have more branching. So what was your threshold for the branching you did?
So we don't have a threshold for the branching, but we use concepts from RRG, wherein we, given us current graph, we sample a point and then we have a shrinking ball radius from RRT star kind of shrinking ball radius. And whatever neighbors are there, we attempt to grow funnels to those neighbors. And that's how, and since the ball is shrinking, the number of neighbors technically remains constant or rather constant by percolation theory.
Then I had a question for speaker one. So I was curious about the feature space you have within your system. I'm wondering just how scalable that feature space is. And then I think in your data laundry, you talked about some limitations you had with the feature space. I was wondering if you could discuss about that a bit.
Where the feature space, actually every dimension of the feature space represents one variability point. And variability points are actually obviously given by the domain, but also it is up to the user, or it depends on the specification of the repository, which variability points you might want to integrate. So we are, as a user, quite free. You are flexible in implementing your combinators and setting up your semantic structure of the repository. Therefore, the feature space is easily extensible, and therefore new problem instances or repository definitions can be easily integrated.
Hello. Oh, so this is a question for Marcus. I really enjoyed your paper and your talk. I'm curious, did you try to push how high dimensional you can make the problems before your method starts to look like the other ones? Because it looked like it might have been converging towards like the same performance. I was wondering if that was like in, you know, dimension 20, dimension 100, or hopefully that makes sense.
Yeah, definitely. Well, that's a very good question, actually. So, so first of all, it obviously depends on the problem that you actually have. So in our case, for the 12-dimensional manipulator, so we've also tried it with 14 and 16 dimensions, but basically after 12 dimensions, you see that, yeah, none of the algorithms perform particularly well anymore. So, but yeah, that really depends on the nature of your problem, how high you can actually, yeah, you can scale it up. Yeah. So we haven't done any study regarding, okay, in general, how many dimensions can we actually handle? But I would say, so as we have seen in that problem scenario, our method tends to scale better to higher dimensional action spaces than the comparators. Yeah, but obviously at one point it will it will also break down, I suppose.
Okay, I suggest that we take one last question.
I have a question for Khalid. So you were mentioning how it's computationally challenging to construct these funnels for a broad range of nominal trajectories. So I'm curious if you've looked into contraction theory as an alternative to the Lyapunov analysis, because basically at the cost of making slightly stronger assumptions on stabilizability, you have the opportunity to very quickly compute these funnels for arbitrary, dynamically feasible nominal trajectories. It just involves like basically one sums of squares optimization, like to construct these funnels for arbitrary trajectories. So just curious if you've looked into that.
No, I haven't looked into that yet. When we started working on this, we were seeing from the Lyapunov levels a theory thing, and then I came across the contraction theory methods.
Got it.
And I didn't change the method after that. I didn't compare this because our main contribution, our main study was using those funnels to plan. So given a funnel library, we can use our planner. So it can be from contraction theory or Lyapunov theory. So one quick question for you.
Sure.
So,
yeah.
So contraction theory, can we construct backward reachable sets instead of just forward reachable sets?
It might be possible, but it's definitely much more natural to think about it in the forward reachability case.
Okay. Because in our case, we want backward reachable because we construct the tree backward from the goal.
Yeah, but I guess there are alternative ways that you can also, yeah, you might not be able to do like pre-image backchaining exactly the same way, but one other way you can kind of integrate this into the planning problems, you can actually do trajectory optimization with these contraction-based funnels kind of wrapped around it. So that's another way. But maybe we can talk more about this offline for the sake of time.
Another question snuck in, but the official closing remarks are after these sessions, but let me already say that it was a wonderfully organized conference, and it's yet another very interesting and educating WAFR. So let's just thank the speakers of this session and everybody.
Well, I wanted to see if the other co-chairs wanted to come, but right. So we are almost done, but not quite yet. So I guess it's my honor to be giving the closing remarks. Before we get into the thank yous, a couple of quick notes. As is the tradition, we'll have the papers that were published, presented here, that will be published in the Springer book. The camera ready deadline will be about a month or so from now. And you can incorporate any feedback that you got from the conference, all the interesting discussions that you've had into the final version of the paper. We are also going to have a journal special issue/issues, and the process for that will start soon. So keep an eye out for that. All right, so stay tuned. All right, so now we get into the thank you part of the program. There's so many people that we want to thank. This is on behalf of the organizing committee and all my co-chairs. A year back when we started this process, the plan was that we would not be in College Park right now, but instead we would be in Finland at the University of Oulu. And as much happy as I am to be hosting all of you at UMD, a part of me wishes that we were in Finland right now. So I want to thank the team at the University of Oulu, Finland, for all the organizing effort that they put in when we sort of started this process a year back. And hopefully we'll have a WAFR in Finland at some point soon. Want to thank all the previous WAFR chairs and co-chairs. They helped us a lot with the logistics. It's always sort of tricky to plan these things, and they help us sort of giving a good sense of sort of what to expect from the logistics, giving us sort of hard numbers in some cases, and that really helped us put this WAFR together. And then we want to thank what Dorsa calls the gods of WAFR. So these are people who started WAFR and then have sort of made WAFR a premier sort of robotics conference that it is these days. Some of them are in the audience here. So, so special thanks to the gods of WAFR. I want to thank all of you. With COVID, there was a big uncertainty of how many people are going to show up. We have sort of over 100 plus participants who registered and showed up in person, and several others who joined online. So thank you for all of you for making WAFR a success. Thanks to all the authors for submitting excellent papers, making this WAFR a very strong program. Thank you to the NSF program managers for sort of holding a special Q&A session that some of you attended today. Thank you to our stellar keynote list of speakers, Oliver Brock, Ras Kreskazid, and Russ Redrick, who gave really thought-inspiring keynotes. I want to thank all the program committee members, and really this is the program committee. We had like a whole cast of really, really strong program committee who sort of put all the papers through the ringer, through the reviewing process, ultimately sort of resulting in, I hope, sort of a very strong technical program. I want to thank all the chairs and what's unique to WAFR, the respondent co-chairs, for sort of making sure that the actual presentations went off smoothly, and we had sort of insightful discussions after each presentation. I think that's sort of it's becoming in some sense rare at conferences these days, and I'm really glad to see that WAFR still holds that spirit of having sort of deep technical conversations, even all the way to the last question that we had today. So really, really good to see that energy. A very special thanks to Maryland Robotics Center for sort of essentially hosting WAFR here and sponsoring the opening reception. I want to thank Derek Paley, who's the director of the Maryland Robotics Center. And a very, very special thanks to Anya Picard, who's here. Very few of you may have actually interacted with Anya, but none of this would have been possible without Anya here. So I think as much as you are thankful, I am extremely thankful for having Anya here. A very special thanks to all our volunteers who are also here. I'm going to call them out from left to right. Sharadeep, Prateek, Vishnu, Sharan, Alex, Sharadeep again, and Alkesh, who sort of really made sure that all the people ended up in the right places at all the right times. And we had coffee for everyone to keep this program going. All right. My last set of thanks is to the awards committee. Sort of this is perhaps new to WAFR, or at least sort of in the recent past, we haven't had this. But this year we decided we should have an awards committee, and we should present an award to the outstanding paper that's presented at WAFR. So I want to thank Danny Halperin, Dylan Schell, and Lydia Tapia for kindly agreeing to serve on the awards committee and sort of reading through the papers, looking through all the talks and picking one outstanding paper, the award that we are going to present now. So to hand over the award, I would like to invite Ken. There is a, yeah, but before, I'm going to ask you to read out the winner, but before that, actually, hold on to the drum roll, because I want to read out the reason why the awards committee decided on this paper, and then we'll go to the drum roll. So the award committee sort of decided on this outstanding paper because it combines strong theoretical results with rigorous empirical evaluation and has potential for generalizing the results beyond the scope of this paper and really making a long-term impact. So that's the reason why the awards committee decided to go with this paper. So now you can start the drum roll.
And the outstanding paper award goes to. Oh, I think okay, great. Alexander Arvis, Hong K. Dai, Peter Werner, Anand Zhang, and Russ Tedre. Finding and optimizing certified collision-free regions in configuration space for robot manipulators. Short speech is in order. No. Here you go. We have copies for all your copies for everybody. A lot of co-authors. For all the everybody's co-authors are here. Excellent. Go ahead up there, guys. Congratulations. Thank you.
And thank you all. See you at WAFR 2024.
There is, you may have heard rumors, but I just wanted to let you know that there is a rumor about 2024, and we'll keep you posted about it. But there's the possibility might be, looks pretty likely that it might be in Toronto in 2024. So we'll keep. Okay, good. I'm glad that's it. Finding some positive reaction. So we'll keep you posted on that. And I want to say again, thank you so much to the organizers. You guys have done an absolutely fantastic job.